Okay, it's loading.
Yeah, I think we started, right?
Okay, we are live on YouTube. We can start.
Okay, so hello everyone. Welcome to this second day of workshop. We will have the first session with the four speakers. We have Giovanni Amelino-Camelia, Mavromatos, Alfredo Iorio, and Salvatore Capozziello. And just let me remind you that each talk will be 30 minutes plus 5 minutes of questions. And I will give 5 minutes warning to all the speakers, basically, during each talk, just to remind you about the time. So we can start our first with our first speaker, who is Giovanni Amelino-Camelia. And please, Giovanni, you can entertain us.
Thank you. I also congratulate the organizers for this nice idea. So far, a very interesting meeting. I'm going to talk of recent research which connects to a long duration research program in a rather striking way. I'll set the stage by reminding you of the previous episodes. One of the research topics that have most intrigued me over the last couple of decades concerns the possible fate of relativistic symmetries in quantum gravity. And this really picked up in the mid-1990s already. And I was a PhD student, and later in my postdoc years, also meeting Nick Mavromatos, who's with us today, and others, we started to realize that there were some features of much studied quantum gravity theories that suggested that indeed relativistic symmetries might be affected by quantum gravity. Initially, it seemed to us that the only option was then that relativistic invariance would be lost in quantum gravity. And this remains, in my opinion, a perfectly legitimate hypothesis. Nature will tell. However, then in the coming years, it was also realized that actually there is room for the possibility that the Planck scale actually does not break relativistic symmetry, but more humbly deforms them. So a new type of relativistic laws with a transition in the logic of relativistic laws, not much different from the one that we already know from Galilean relativity to, say, Einstein relativity. This has been an idea. Both these scenarios have had actually surprising success for those of us who started it as a little underground activity. And one reason is that of all the speculations, and there are some even wilder than these ones, but in spite of how wild they are, the speculations about quantum gravity effects, usually they cannot be tested. So they are not only crazy, but they are not even wrong, which is what's worse that can happen to science. These ideas could be wrong. They can be tested, and basically now there is a wide literature on this. But the first realization that this could be done came from understanding some properties of gamma ray bursts, a class of astrophysical phenomena which we actually astrophysically don't fully understand yet in astrophysics, but as a laboratory, they became, in our view, a laboratory for quantum gravity effects, and exploiting the fact that they are very long distances. This was timely. It was established that they are typically at cosmological distances in 1997. Before then, it was thought that they would be much closer. So that helped. And then there are energies of pretty high energy. It depends. The photons can reach TeV range. The neutrinos could be even PeV energies. And coming from very far, this could test very sharply a key prediction of relativity, of Einsteinian relativity, which is the speed of light law. Actually, in these scenarios that I was mentioning briefly before, one of the most fragile aspects of our current relativistic laws appears to be the dispersion relation. In many frameworks, there is more or less robust evidence that the dispersion relation is modified, and as a result, we might have that effectively, actually, in most frameworks, is a subtle relativistic effect, a sort of dual redshift. These are theories with the Planck scale playing the role of curvature of momentum space, but effectively is an energy dependent speed for ultra relativistic particles. A tiny energy dependence because it's suppressed by some power of the Planck scale, hopefully only one power, but nature will decide if it is 1, 2, or infinite, which would mean that there is no effect. And at least if n is 1, and probably actually even if n is 2 in the long run, these effects can be tested. And basically gamma ray burst, since this is a velocity effect, gamma ray burst set up for us a good race. Velocity is best tested when you have a good race. And these are far away explosions with high energy particles so that the effect is not so weak. It is still incredibly weak, but not as weak as for lower energy particles. And these gamma ray bursts are explosions which have fine time structures. So there are micro explosions within the main event, the overall event, that could be used to test the laws. And the numbers just work out remarkably. Actually, I always like to observe what I'm with the general public, that the universe is just big enough because the, say for a particle of 10 GeV, the suppression, if n is equal 1, would be 10 to minus 18. So it still is a very small effect. But the universe is just big enough. We go as far as redshifts for the observation of gamma ray burst of 1, 2, 3, 4, in some cases even more, but bulk of the observation are in that range. And the universe is big enough because, of course, if you have a very small velocity difference, but the journey is very long, then you could test this effect. And one intriguing aspect of how the phenomenology shaped up over this, so especially over the last 10 years, the data available from astrophysics has bloomed significantly. And one interesting way to look at where we are now is found by adopting a statistical approach. Basically, first of all, we need as an ingredient, I had here the law in a flat space-time, but of course, if you did it locally, you could as well use the flat space-time formulas. But when you are using the universe as a laboratory, you cannot ignore, evidently, the space-time curvature. And so we relied so far on arguments, more and more robust, that provide different possible dependence on redshift rather than on distance, rather than on flat space-time distance. And the most studied of which is a formula first proposed by Giacomo and Piran, which happens to come out in a few quantum space-time models to be applicable. And basically, the formulas we are testing is a formula that relates a difference in time of arrival for particles emitted ideally in simultaneous emission that goes with the difference in energy with the particle, here indicated by E, and with this redshift distance that I just mentioned. I will show you the statistical analysis on a two-dimensional. There are three quantities: time, energy, and redshift. But I will show it on a planar graph, basically reabsorbing the redshift dependence into a redefinition of energy. Just I'm basically plotting the dependence of the time of arrival difference as a function of the product of E and D of Z, okay, which I call E star, so that you will understand why I'm, and it's very intuitive, I'm looking for a linear relationship between this delta T and E star in data. This type of studies were done, actually first, this setup with the something analogous to E star was in some works a few years back, maybe 10 years ago, by Nick Mavromatos, John Ellis, and others. Recently, it was reused and in some sense upgraded by a group in China, the group of Boqian Ma. And they were the first to notice that if I focus on the most energetic photons observed from gamma ray bursts, and I take the difference in time of observation between these photons and the first low energy peak, the trigger for this gamma ray burst, then I get a collection of events. Actually, these are not events from a single gamma ray burst, if I manage to explain the statistical approach. These are the few, these are 11 actually, if I remember correctly, or maybe 12. The highest energy photons seen from gamma ray bursts enter in this analysis. And the formula we are testing would predict a linear dependence between E star and delta E. The no effect formula would predict that this data would be scattered randomly on this graph, because of course, if there is no correlation, then it would just be statistics, no systematic behavior. So Boqian Ma and others and collaborators had noticed this statistical feature. With my group, we then assessed the statistical significance of this feature, which was not studied by my collaborators, and it's quite significant. Overall, if I just ask how lucky, if I assume that the standard model picture is correct, so this should be scattered randomly, how likely it is that by chance they would fall on such a high correlation distribution of points, and the probability is very small. So that's quite impressive. On the other end, and you see there are 2, 4, 6, 8 points that pretty nicely stay on a straight line. There are 3 which are not on that straight line. 2 of them, the ones which I didn't circle in red, actually there is a good understanding from the astrophysical story of the gamma ray burst that might explain why they're not on the line, and this you will see in my papers if you're curious. But I'm most interested, in order to give a balanced presentation, to focus on this this point off the line which is circled in red, because this, although the statistical significance of this correlation I mentioned is extremely high, this point, which overall has a very low statistical weight, but for this point, there appears to be no way to match it to the model. For this purpose, I show you now, these are the highest energy photons observed from one specific gamma ray burst as a time sequence and showing their energy. And the one which is highlighted by my red arrow is the one point which this burst contributes, the one that was circled in red on the previous slide. And you see that it's very difficult. I mean, it just arrives at the same time, roughly the same time, as the busiest part of the signal of this burst. So it's, and this is the reason why it's rather far off the straight line that the plot on the previous slide suggests. And it is a pretty robust reason. I mean, there is no, it's difficult to imagine a conspiracy. You should have an extreme fine tuning to imagine that this photon was emitted earlier than this bunch of lower energy photons, but then of course with the speed, or maybe earlier, but then because of the different speed, it happens to come just at the same time. Just as much as this statistical significance is impressive, the amount of conspiracy you should introduce in order to, you know, recover this data point is also very large. So the situation for this statistical analysis is rather puzzling, and I'm not claiming that I'll propose the definite answer, but it's an intriguing development that I want to discuss in relation to this situation. But first, before going to the new result, let me stress that the very fact that I'm, you know, showing these graphs and it all, the scales match and the data points are there, it means that this thing that people like myself, Mavromatos and others were dreaming 20 years ago, this exists. I mean, we have data that are relevant for these, for at least, let me put it this way, for at least the weirdest quantum gravity scenarios, we finally have data that are relevant. Now, this story, if we are extremely lucky, will lead to a discovery, but when the dust settled, most likely it will falsify some models. So this is a genuinely scientific endeavor, something, and probably the younger members of the audience are not surprised, but when Nick and I were PhD students, this was thought to be a utopia. Now, what's the recent development? Well, it actually didn't, the interesting part is it didn't come from this phenomenological situation. With some of my collaborators, we started to be increasingly concerned with the fact that this is a rather technical aspect, which I'll try to make everybody appreciate. Actually, the quantum space-time pictures that inspired this kind of formulas that I've shown, they produce these formulas in such a way that if I then remove curvature, okay, for example, in this formula, the one that is being tested so much, the Jacob-Piran formula, if I remove curvature and go back to a flat space-time, starting from this formula, I still have the effect. So the dispersion is modified, let me put it this way, in curvature-independent manner, which is not surprising probably, but as some of the theories that motivated these studies became better understood, some results, they're still preliminary, but they start to suggest that this modification of the dispersion relation might be present indeed in these models, but they are triggered by a combination of the Planck scale and the curvature of space-time. They would not be there in these recent scenarios if there was no curvature of space-time. So we were testing, I mean, a perfectly legitimate phenomenological scenario, but with some of my collaborators, we started to be concerned that we might be testing not the best, the most promising option, since some theory results were suggesting this interplay between curvature and Planck scale effects. And actually, these are not so new. You see, there are results from 2011 and even earlier. One of the reasons why my group and others did not study this idea of curvature-triggered modification of the dispersion relation is also because there was a prejudice among all of us, my group and all other groups involved, that already the effects are small because of the Planck length. Now, if they are triggered by a combination of, and now I'm listening like a phenomenologist, and I'm not sure how many phenomenologists are in attendance, but it's a very simple back of the envelope, but usually robust argument in phenomenology. I have a new effect which is triggered by a small scale. Now, if it's double triggered, it needs two ingredients in order to take off, the Planck length and the curvature. curvature of space-time in our universe is also very small scale. So the expectation by phenomenologists was that these effects would be even smaller and therefore totally untestable. This was the conceptual point that at some point, not thinking about the phenomenological situation, but mostly trying to understand if this was true, because the back of the envelope argument usually work, but in some cases, and this is one case, they actually don't work. And actually what we found is that this back of the envelope argument, this is a very recent paper from December, this argument had missed the fact that for these cosmological distances, the way curvature ends up triggering the modification of the dispersion relation, inevitably by dimensional analysis, actually, this is not back of the envelope, dimensional analysis is a serious thing. It's inevitable that it comes in by bringing also the distance traveled again. So this is to give you intuition. The formulas are a bit more cryptic, I guess, for those who are not used to the formalisms and the notation of this setup. Basically, we needed to test this idea. We needed a different dependence of redshift, one that would vanish when curvature is set to 0. Of course, we are not taking curvature to 0. The analysis will be done in our curved universe. It's just that from theory, we are getting the input that the correct formula might be a formula that then in the limit of 0 curvature removes the modification of the dispersion relation. But of course, we will use that formula instead when curvature is present, and there will be a curvature dependence. And so we found such a scenario, actually combining two of the formulas that have been competing for interest in this research area. But by combining them, there is a cancellation, and you get a pure curvature-induced correction. And I probably, for those who have not followed this, too quick for you to realize, but immediately the first, if you look at the bottom, the time delay formula is really not different from, or maybe before, for small t. You see that each time you get H0, which is a curvature in our notation, you get it multiplied by t, the time traveled. So this already suggests that curvature doesn't come at a high price, because it gets always multiplied by the time traveled, which is a big number in this game. And in the end, the formula for the time delay in the bottom is different from the one I showed you, which is actually in the two formulas in the bottom are one for our new scenario with lambda and lambda prime, and one for the I know the one in the bottom is our new scenario. In fact, it goes to 0 when z goes to 0. The other one is the general picture with the two formulas combined. One of the cases is the Piran-Jacob formula. So first of all, I mean, the part that I most want to publicize of this result from last December is that actually the folklore was wrong. So even setting aside the data situation that I mentioned earlier, it's just wrong to think that effects which are triggered by curvature would be too small for testing. The curvature triggering mechanisms do not produce a suppression. They actually produce a small suppression, a small redshift, but when you reach redshift of a few, unity, 2, 3, it becomes a formula just of the same order as the Jacob-Piran formula. So just conceptually, I think is the most important message of this recent result, which we should stop keeping far from these scenarios with curvature-induced corrections, which might appeal to some more formal theorists for reasons that I mentioned. But let me go to the implication for data, on which I close. So this is a slightly different, it's the same plots, but from a different paper. So the graphics is a little bit different. Now, instead of circling the points, I have in red the one point which was, and so the graph on the left is just a different way to show you the fact that there is this one point from gamma ray burst 09, 05, 10, which doesn't fit the analysis. This is a plot which also adds the error bars on data points, and because this was crucial for this analysis, and actually is not exactly, it's not delta t versus E star for some reason. It's a energy corrected delta t. So instead of plotting delta t as a function of energy and redshift, here is redshift as a function of delta t and energy. These are the different ways in which these graphs are made. In any case, what you would expect from the Jacob-Piran formula is the blue line that you see on that graph on the left. And so this recovers all that I said on the previous slide, so that we have a pretty good fit of the data. There are 3 points which are off the blue line, but 2 of them actually, they have large error bars and they are not too concerning, but the red point from 09, 05, 10 is significantly off the prediction. And now
you have 10 minutes.
Yeah, I'm done. On the right, you see just the same analysis, but now with the new formula, with the curvature-induced effects. It's just what is changed if you compare them is just the redshift dependence, of course. And as you see, they're very comparable in magnitude. There is, as a further confirmation that the curvature triggering mechanisms don't cost the price in phenomenology that folklore was expecting. And this is, I repeat, the most interesting part and the bring home message, I would say, of this recent result. But it's also intriguing that now the specifics of this blue line on the right, the one from our new model, actually it's pretty similar, but there is a difference as more redshifts, because the fact that, you know, you need, because you have a curvature suppression, when the time traveled gets larger, it compensates fully the curvature suppression. But at small distances, it doesn't fully compensate. So the main qualitative difference between the two scenarios is that as more redshift, the new picture predicts smaller effects. And as you see, within the new formula, even the red data point is in good agreement with the prediction. Actually, the first point, it's difficult to see maybe on this little graph. The first point from 130427A is not too far off the line, but it is now above the line. And it's already nearly 2 sigma. So we might have changed one problem for another, but from a 4 sigma problem, now it's less than a 2 sigma problem. And anyway, this is the story. I mean, this is not problem. I always think in phenomenology is not a good word. This is how the phenomenology changes if you use the curvature triggered effects. And it is amusing that the data analysis improves, but I repeat, more data will come, and maybe all these pictures, maybe they will scatter all over the graph and all these will crumble down. Whereas the main point that I made, that curvature triggered effects should not be discouraging for phenomenologies. They are just, besides a small redshift range, where, however, they don't create an apocalyptic suppression. Just you know, a significant but small suppression. Overall, they are just comparable. And this is my bring home message, and I'll stop here. Thank you very much.
Thank you very much, Gianni, for this very nice talk. So I think it's time for question. Yeah, I can see already Nick has a question. Please, Nick.
Yeah, I mean, I was clapping. I was ready to ask a question, but first it was my clap.
Okay.
No, yeah, I have
Sorry.
the question. I was ready to, since you gave me the...
Okay.
Giovanni, what is a lambda in your formalism? How do you macroscopically determine it? In other words, I understand you use it as a parameter, but for instance, I can tell you what I am thinking. I mean, you know, you may have stochastic fluctuations, for instance, where, you know, they affect the geodesics depend on curvature, and that would be one way to determining lambda. There, of course, because it's a stochastic effect, it might be suppressed. But in your case, you're thinking of classical curvature effects, am I right? Or
Yes, correct.
No, not quantum gravity curvature, that's what I mean.
Exactly. So this is, but this is actually both in well, you see it most clearly in some non-commutative geometries. For example, non-commutative versions of the Sitter space-time.
Yes.
And you see that the modified dispersion relation that you find there actually would vanish unless you do some fine-tuning. Would vanish in the flat space-time limit. But so they are quantum space-time picture, but the effects, and this is a very, I should have been clearer, the effects depend on the macroscopic curvature.
Right.
For example, in quantum de Sitter, in these toy models for quantum de Sitter that have been much studied, it depends on H, you know, the overall H, usually, or lambda, that you put in the algebra that describes this quantum de Sitter is a Hopf algebra normally. Then you will have, in these quantum geometries, we still don't know exactly how to grasp them, but you will have a notion of, which is what you are, I know from your works you're very interested in, you have a notion of local quantum curvature effects.
Right.
You know, at the level of the structure of the theory, there might be a connection, but the results, the sharp results are that the effects need the macroscopic curvature to be present.
Yeah, which I agree. That's why it's unsuppressed. That's why it's unsuppressed. I agree.
And this is something I mentioned an argument by Bianchi and Rovelli. This was not non-commutative geometry. This was inspired by loop quantum gravity. But also there, they have a mechanism where the modifications of relativistic symmetries is present only when macroscopic curvature is present. So this is the scenario that I'm looking at. But of course, you know, once we discovered as phenomenologists that the curvature is not this big suppression that we fear, the many models, I'm sure, will be studied. And this is the main goal of this presentation.
Thank you. Thank you very much. I quite agree.
Very nice. Luca, please, you can ask.
Okay, very nice talk, actually. And in fact, you were mentioning now at the end of the reply to Nick that relation. Last time we talked about this was in Chile, and you mentioned there were not so many prediction maybe from loop quantum gravity side, but the relation you used actually between the deformation parameter and cosmological constant is widely used in loop quantum gravity. My knowledge came from Lee Smolin work, 1996 originally probably. And but another example, I don't know, I want to ask you how much is important that I know you studied some years ago, and always in connection to loop quantum gravity, is the one of Kappa Poincaré. I remember, I know a work of you about polymer quantum mechanics in particular, and the formation of Poincaré algebra. And it's known in that context is widely used. There is a paper of some years ago about Reggio Ponzano model coupled to scalar field when you integrate out gravitational degrees of freedom, you obtain a field theory which is Kappa Poincaré invariant. So there is also that other possibility, I think. How much is important in this kind of analysis? How much you can test with this kind of observation? Okay, sorry for the long question.
No, thank you. But this is fields and omissions. I focused on the phenomenology because, as you saw, the main message, both the conceptual and the data analysis message, they are both of phenomenological nature. I was very quick on the theoretical motivation because this is a story I've told for 15, 20 years. Those who are interested there. But as you say, there is, in these 15, 20 years, besides the phenomenology growing, there is a growing bulk of results that provide motivation for this phenomenology. And, you know, it's, there are some results indeed where you have a picture of gravity coupled to matter, and when you integrate out gravity, quantum group symmetries, quantum group, the most natural, probably not the only one, but the most natural theoretical scenario for accommodating all these, and indeed it is the most studied, is that you still have relativistic symmetries, but they are described by a quantum group rather than by a Lie algebra. So this is what probably is not the only, we have studied weird, as you might imagine, but the most conservative idea, which also is the way in which this research makes contact with at least some approaches to loop quantum gravity, where these quantum groups symmetries are often arise. So what you mentioned are several, and it is interesting that the work by myself, Nick Mavromatos, and others was before some theorists noticed most of these results. So it's been like a little fairy tale. Of course, it misses the most important part of the fairy tale, that nature should surprise us in some way. Maybe not the way that we imagined, but something. But indeed, the bulk of results, and you mentioned a few of the key reasons why over the years, a certain community became more motivated, even more motivated to do these studies.
Okay, thank you very much. Giovanni, so thank you very much. We can postpone, there were more questions, but we can postpone them to the discussion session because we're already a bit late. Thank you very much again for the nice talk. So we can move on to our second speaker, who is Nick Mavromatos. Please, Nick, you can share.
Yes. So I can upload my...
Yeah, you can share screen. Oh, perfect.
Is that right now? Right.
Yes, you can see very well. So yeah, the stage is yours. Please, we can start.
Very good. So first of all, thanks very much. I would like to thank very much the organizers for their kind invitation to this very interesting effect, which I'm enjoying very much so far. Now, what I'm going to discuss is some aspects of quantum gravity, which I find interesting. And these have to do with gravitational anomalies. And I will try to argue that matter-antimatter asymmetry in the universe, as well as inflation, might be due to those effects. So let me start by showing a standard picture. Of course, you all know that for the past 20 years, we have witnessed extraordinary development in precision measurements in cosmology. Through CMB and supernova data, we understand now that the universe is currently accelerating. If you assume that there is a cold dark matter and a cosmological constant, the so-called lambda CDM paradigm, because this is not a model, you can explain the phenomena, the plethora of the phenomena at large scales, showing that you have 70% dark energy, 26% dark matter if you don't accept modified gravity, and you can also falsify some models of inflation. Moreover, we have seen gravitational waves from most probably black holes, because they cannot be anything else according to the experts, although you haven't seen them directly, the black holes. But for the merging of black holes can produce gravitational waves, and eventually you even have photographs of black holes by reconstructing data. What you haven't seen, however, despite all this progress, is you don't understand at the moment what's the nature of dark energy, whether there exists dark matter or what is its nature. You haven't seen primordial gravitational waves. because the gravitational waves we've seen are from low redshifts, and we haven't seen primordial gravitational waves that could give information about the inflationary or very, very early stages of the universe. And you don't even understand macroscopically what causes inflation. In other words, whether inflation is due to a fundamental scalar field or some higher curvature terms where the scalar field is an emergent field due to nonlinearities in gravity. In addition, the lambda CDM paradigm is currently in tension with small redshift data, small scale cosmologies. For instance, you have the discrepancy between the values of the measured Hubble parameter today if you use CMB data, which Planck data, which are high redshift Z=1 data, and puts the Hubble parameter at the values around 67 in the kilometers per second per megaparsec, or localized data from Cepheids, for instance, direct measurements, which seems to be in conflict, in tension with the CMB data by placing the H0 at 74. I stress that these CMB data mostly are interpreted using lambda CDM, mostly. In addition, you have also tensions in the growth of galaxies data. For instance, the current matter density root mean square fluctuations within spheres of radius 8 over the reduced Planck constant is also in tension between localized direct measurements and CMB. I'm not going to go into whether these tensions really signify new physics. It could be due to statistical effects, but it seems there is a growing evidence. So this is one of the problems. Another problem is the macroscopic understanding of matter-antimatter asymmetry. Why actually we exist? Because we exist because matter doesn't dominate, matter dominates antimatter in the sense that there is one antiproton in billions of protons, in 10 to the 9 protons. And this is the baryon asymmetry in the universe today. This is what you need to understand, which comes from either CMB or Big Bang nucleosynthesis data measurement. Zakharov had attempted to explain this matter-antimatter asymmetry by postulating his celebrated assumption that there is charge violation in the universe, CP violation, and baryon number violation, plus departure from thermodynamic equilibrium, because the universe is a non-stationary system. Unfortunately, the CP violation required to reproduce the observed baryon asymmetry is in the Standard Model, although the Standard Model is characterized by all of these conditions. This characterization is only qualitative in the sense that quantitative, the CP violation in the Hadron sector is less than 10 orders of magnitude from being capable of explaining the observed asymmetry. In the lepton sector, CP violation has not been observed as yet. Moreover, another assumption in all this theory for explaining matter-antimatter asymmetry is we assume that CPT invariance at the beginning of the universe is valid. The beginning of the universe is a fully quantum gravity effect. So this is a big assumption. Of course, if you accept this assumption, which might be honored, for instance, in some models or string theory, although you have to define properly what you mean by CPT invariance there. If you assume this invariance, it would imply that matter-antimatter would appear in would be produced in equal amount, and then CP violation would induce dominance of matter over antimatter. There are many theories trying to explain this matter-antimatter asymmetry. The simplest of them is to accept the simplest extension of the Standard Model. Instead of accepting first the supersymmetry of extra dimensions, you say that there are extra right-handed neutrinos and nothing else, and right-handed neutrinos produce matter-antimatter asymmetry in a process called leptogenesis, which means that you create a lepton asymmetry from the decays of the right-handed neutrinos to Standard Model leptons, and the corresponding rate to decaying to the anti-leptons is different as a result of CP asymmetry. And then the lepton asymmetry is communicated to the baryon number, and you produce matter-antimatter asymmetry through Svalleman processes in the Standard Model, which conserve B minus L but violate B plus L. In our approach, I'm going to argue that actually I'm going to change the geometry of the universe in the early stages so as to produce leptogenesis through baryogenesis through gravitational defects. And I will explain what this means. And we will see that the CPT assumption would also be violated geometrically. Now, all these problems that I mentioned constitute parts which since yesterday we devoted the whole session of the conference in quantum mechanics. According to Heisenberg, you cannot sometimes atomize the system, and there are cases where the parts cannot be separated from the whole, and this is exactly what I'm going to discuss in the talk. So the parts of my talk are the nature of dark energy. I will discuss a particular model of that called the running vacuum model, which was suggested originally by Solar and Sapiro. I will embed this model into strings, and I single the role of gravitational actions that exist in the ground state of supersymmetric strings, of superstrings, which are associated with torsion in the geometry. Then, in the presence of such gravitational actions, you may have non-trivial gravitational anomalies, which are vanishing in Robertson-Walker universe, but they are not vanishing when you have gravitational waves, primordial gravitational waves. The latter can condense under circumstances, certain circumstances that I will discuss. And this condensation, and that's a quantum gravity effect because you integrate over graviton fluctuations, can induce spontaneous Lorentz violation from anomaly condensates. This is the difference from the Lorentz violation that the previous speaker, Giovanni Amelino-Camelia, was talking about. But it is a spontaneous violation in the sense that you have a background which is constant in a preferred frame, the cosmological frame, and this frame is defined by the condensates. This leads to dynamical inflation without external inflaton of the type in this running vacuum model of dark energy, which I will explain. But the spontaneous Lorentz violation, it produces leptogenesis through baryogenesis in models with right-handed neutrinos, because now you have the decay of the right-handed neutrinos in this, if you like, environment which survives inflation, because this spontaneous Lorentz violation is due to the action fields background, which remain undiluted. So in this sense, the upshot of this approach, if correct, means that we exist because of gravitational anomalies. We exist in the sense that matter dominates over antimatter. Eventually, after the exit from inflation during the radiation era, dark matter, some of the gravitational actions can develop the potential through non-perturbative effects and can play the role of dark matter or part of dark matter. And because the gravitational actions are associated with torsion, you get a geometric origin of torsion. And you come back to the current phenomenology where, because we are talking about a running vacuum model, there are deviations from the lambda CDM paradigm, and then we can examine whether such models have a potential of alleviating the tensions or explaining the data. Now, what's the whole? As you probably guess, the whole that connects all these parts, I will argue, is quantum gravity. Of course, we don't know what quantum gravity is, so I will consider an effective whole, if you like. I will consider an effective theory of the universe evolution as a first step. And that is within the framework of the so-called running vacuum model of cosmology, but I will discuss a stringy version of the running vacuum model, which has some important differences, although the qualitative features are more or less equal. In this talk, therefore, I will concentrate first on describing the string-inspired model, the microscopic string-inspired model of the universe, and then I will link it with spontaneous Lorentz violation via the gravitational action backgrounds, which will lead to matter-antimatter asymmetry in theories with right-handed neutrinos. And you can find works on both subjects in this with my collaborators, Basilakos, Sola, Saben-Sako, and my ex-student, De Cesare and Thomas Bossinger. The parts. So this completes the general discussion, if you like. I gave you an overview of the approach. Now, in the remaining time, I will go briefly through the various parts in detail, starting from the vision that I have for the dark energy. In the standard lambda CDM, the dark energy is just a constant vacuum energy, which satisfies, of course, due to the Bianchi identity of the curvature, is consistent with energy conservation, energy momentum conservation. And that's why Einstein added it. However, in the running vacuum model, this cosmological term may not be constant, may vary with cosmological time, still maintaining the energy conservation. And this is the running vacuum model, which was suggested with Sapiro and Sola, although earlier in non-critical string approach, we also have the same model. The most important, the same features, not the same model. The most important features of the model is that it satisfies an equation of state of the vacuum energy, and if it is as if it were a cosmological constant, but now the lambda depends on time. And Shapiro and Sola have actually discussed a renormalization group like evolution of the vacuum energy density, which can be expanded in even powers of the Hubble parameter plus time derivatives of the Hubble parameter, but they can associate time derivatives approximately to higher powers, even powers. And this even power dependence on age is a consequence of general covariance. Now, this is the phenomenon. Originally, Shapiro and Sola and collaborators have developed this model as a phenomenological model, and this leads today to deviations from lambda CDM because, for instance, these terms are sufficient up to h to the fourth to describe the entire phenomenology of the universe. And as we shall discuss at the end, matching it with the current CMB, you get several numbers. From the evolution, you can get various eras from the energy conservation, if you like, which is valid in the presence of lambda T. Now you have exchanged the matter and radiation densities, which are denoted with a small m, of course, exchange energy with a vacuum, and you can have various eras. The de Sitter, let me start with from bottom to up. The late dark energy gives deviations from the lambda CDM through these new dependencies. Omega lambda 0 is a cosmological constant. So that deviations could be in principle observable, but I will concentrate on the early de Sitter, which you get from the nonlinearity from the h to the fourth terms that are dominant in the early universe, because Hubble is much larger today. I will argue that these h to the fourth terms are the consequence of an anomaly condensate. You cannot get them in standard quantum field theories, as was also examined by Sola, but you can get them as a result, as I will argue, of anomaly condensate. So gravitational anomalies are essential to give the inflation in this model, the RVM inflation. RVM inflation is due to nonlinear gravity effect, like Starobinsky, but different from Starobinsky, and you don't require an inflaton, an external independent field. In the RVM approach, the coefficients of nu and alpha are assumed constant throughout the phases of the universe, but in our case, as we shall show, due to anomalies, the nu is negative, and nu and alpha depend on the phase of the universe. So let me proceed now to embed this model to strings, starting from the basic analysis of the spectrum of a string. In a superstring case, which defines the ground state of the string is consisting of the dilaton, which is a zero spin scalar, a traceless spin 2 tensor, which is the graviton, and a spin 1 antisymmetric tensor, which is called Karl-Ramon field. There is a U1 symmetry of closed strings for this field, which implies that in the effective action, this field appears only through its field strength. And this field strength is not only given by the kernel of the B, but is also given by the Chern-Simons terms due to graviton and gauge fields that you may have in string theory. This term has been added for the Green and Schwarz anomaly cancellation. Because of this dependence, you can absorb the age dependence in a generalized curvature, and because the age is totally antisymmetric, you have a antisymmetric torsion part. And that's the action, that's how the Karl-Ramon field is related to the torsion. Assuming a constant dilaton throughout our discussion, because it doesn't play a role and is probably desirable from the phenomenology of string theory, you can now integrate over the H field in a path integral and promote this torsion to a gravitational action, which is dual to the torsion in the following sense. The definition of the field strength implies a Bianchi identity. Tildes are the duals, tensors, and you implement this Bianchi identity in the path integral through a pseudo-scalar B field. The path integral is over H. There is no derivatives of H to this order, and then you get this effective action where you see that the anomalies, both gauge and gravitational, are coupled to this action field B, which is dual in this sense, in the sense of the classical solution. The derivative of the B field is proportional to the field strength of the Karl-Ramon action, and that's a pseudo-scalar, because this is pseudo-scalar due to the epsilon, that's a pseudo-scalar, it's an action. We call it gravitational or Karl-Ramon action. Because the anomalies are total derivatives, if the action is constant, then it doesn't contribute to the term. You can couple the anomalies to fermions by integrating out the H field by taking into account that there is this generalized torsion that determines the coupling to the fermions, but you can also get it independently in string theory by computing amplitudes. And this leads you to the standard derivative coupling of the axions to axial fermions. This J signifies the fermion species you have in your model. So that's the model we are going to discuss. And we are going to consider Robertson-Walker backgrounds. So this term is 0. So this is our model, which couples a gravitational action. This is due to the gravitational multiplet of the string. That's why it's gravitational in origin. It's massless, and it couples to the anomalies. Let's come to the anomalies term and their physical significance. In string theory, you cancel in the compact manifold these anomalies by assuming non-gauge field here. That's the Green-Schwarz mechanism, and you don't have them. In our approach, I will keep the gravitational anomalies, and you will see what is the importance. The first important thing to notice is that this gauge field is topological. It doesn't contribute to the variations of the action with respect to the metric tensor. So it doesn't contribute to the stress tensor. That's why energy is not violated when you couple actions to this anomaly. But this anomaly spoils conservation of the stress tensor because its variation with respect to the metric gives rise to the Cotton tensor, which is non-zero, and it's a traceless tensor given here, and is proportional, as we've said, to the derivative of the action field, because if the action field is constant, this term is a total derivative and it doesn't contribute to any variation. The important point of the Cotton tensor is that it doesn't give positive contributions to the stress tensor, but negative ones, and it seems not to conserve matter. If you write down Einstein's equation in the presence of these gravitational anomaly terms, the gauge anomaly terms do not contribute, you get this result, and the Cotton tensor, the covariant derivative of the Cotton tensor, spoils the conservation, because this is always conserved due to the Bianchi identity when you take the covariant derivative. This, you may say, but that's inconsistent, so I have to consider backgrounds like the Robertson-Walker alone, where this energy conservation is valid, because the diffeomorphism invariance could be in trouble, since the T mu nu of matter is viewed as the current of the diffeomorphism invariant. That's not true. You can always define this improved tensor, and you can interpret the non-conservation of matter as an exchange of energy between your system and gravity. In our particular case of string theory, this matter is not really matter, it's the gravitational action field belonging to the massless gravitational multiplet of strings, and therefore this situation is perfectly consistent. You can write down generally covariant expressions, and there is no problem with the diffeomorphism invariance. It simply means that the gravitational action interacts with the other multiplets of the string, in particular the graviton, through these anomalies, and there is an exchange of energy. Now, primordial gravitational waves. First of all, our basic assumption in our universe is that in the very, very early stages, there are no external fermions or other matter fields, only the gravitational degrees of freedom of the string, including possibly partners, supersymmetric partners of gravitons. So this is the model. The anomalies are total derivatives. And if there are no gravitational wave perturbations, the anomalies vanish in the Robertson-Walker universe, and then you are having only a massless pseudo-scalar field coupled to gravity. That's stiff action matter, because it satisfies the equation of motion similar to stiff action, W equals +1. That's reminiscent of the stiff action matter that was postulated by Zeldovich, but for every universe, in an attempt to explain matter-antimatter asymmetry. But in Zeldovich's model, the stiff matter was just consisting of baryons, which he put by hand. Here we have actions, and we shall see how matter-antimatter asymmetry is generated. First of all, let's discuss briefly some origin of the gravitational waves. That could take me another talk to explain in details. You may have you don't want to have any matter fields here, so you may have gravitational defects in your theory, like compactified deep brains, or you name it, defects which can collapse. There are massive defects, can collapse and produce massive black holes whose coalescence produces gravitational waves. That's one non-minimal scenario, and requires inducing specific brain models for this. A similar scenario is to accept that for some reason there is some spontaneous symmetry breaking of some discrete symmetry in your model, which generates domain walls, and these domain walls because you have a spontaneous breaking of a discrete symmetry are unstable, and the non-spherical collapse produces gravitational waves. Such a situation is actually met in a simplest model within our framework, where only gravitational degrees of freedom are taken into account, if you assume condensates of gravitinos in a dynamical breaking of supergravity. Supergravity is naturally embedded in our string theory. Gravitino is the partner of graviton. You may assume that there is a dynamical breaking where the breaking of supersymmetry is at Planck scale, is not phenomenological. I don't assume phenomenological supersymmetry here. But then there is a bias in this potential, which can come by a statistically induced out of equilibrium phase transition of gravitino condensates, which means that there are no equal probabilities for occupying this vacuum due to percolation effects of the gravitino. The gravitino condensate defines bubbles of vacua, and you have asymmetric percolation effects, which then produce unstable domain walls and then collapse in a non-spherical way, gravitational waves. You can show that in this particular case, this line, the bottom of the line, because you have spontaneous breaking of supersymmetry, this potential is not at zero, but at a positive number. There are imaginary parts. You can show them in explicit computations. And this imaginary part means that when the gravitino is going to its minimum vacuum, acquires a mass, the condensate acquires also an equal mass, but there, this vacuum, because of this imaginary parts, tunnels through to the true RVM vacuum, which is arising after condensation of gravitational waves that I now come to discuss. And then you have the real inflation. You may have actually first inflation potentially due to this hilltop potential. This is not to scale here. It could be a slow moving. And this first inflation that you may have in this model is responsible for washing out any spatial inhomogeneity in the universe. And when we are discussing gravitational waves, we are going to assume homogeneous background. So that gives a microscopic origin of the isotropy and homogeneity. Let's see now how you do this. In the presence of gravitational waves, the anomaly terms are non-trivial. But you may have this condensate, which I will discuss in a minute. This condensate acts as a cosmological constant, if you like, a slowly varying variation, and you get a lambda term as a result of gravitational anomalies. So this is what I call gravitational anomalies, BRR tilde condensate. This VEV is actually integrating out fluctuations of the metric of gravitational, primordial gravitational waves, and you integrate over graviton fluctuations, which violate CP in a sense. Taking into account the total derivative of the anomaly, when you evaluate in this VEV, you integrate gravitons, which eventually have to be cut off their modes by an ultraviolet cutoff, and you assume slow varying parameters. You assume a B dot slowly varying, which you can verify self-consistently at the end. You use the total derivative. You assume homogeneity and isotropy, which is ensured by the first inflation in scenarios that I've described above, and then you arrive at an equation of motion for the action field in the presence of the anomaly of the temporal component in isotropic situation. This defines the string scale, alpha prime, which is different in general from the four-dimensional Planck scale in string theory. That's the equation of motion of the anomaly, which then you taking into account that theta is proportional to the anomaly and putting a cutoff for the graviton modes. K is the momentum of the graviton mode. So this is an approximate weak quantum gravity calculation. You arrive at this exponential wash form, exponential decay of the anomaly at the end of the inflation, if you like. At any time where t equals 0 is the beginning of this inflationary phase, the formation of gravitational condensates. In principle, this is exponentially washed out, like in any inflation, except in this case, if you have a fine-tuning, which is not so much fine-tuning, of the ultraviolet cutoff with the string scale. As we shall see, if you assume string scales of order 10 to the 3 and sub-Planckian, taking into account, of course, that data give that the age of inflation, which you assume here constant, and then you self-consistently will get it by mapping this to the RVM. If you assume this value, then you get that the string scale, in order to ensure constant anomaly, has to be the cutoff 10 to the 3 of the string scale. This string scale eventually can become sub-Planckian. At the moment, once you have this constant anomaly, you see that you have a constant Hij, the field strength of the, or B dot, or the rate of change of the gravitational action is constant. It defines.
Nick, you have 4 minutes.
Okay,
4
thank
minutes
you.
left.
Yeah, that's fine. Thank you. And this is constant and defines the preferred frame. You insist of not having Thomas-Planckian modes, and this restricts the string scale to this order. This proves the important part that I proved the dark energy of the RVM type. You see the even powers of the Hubble constant. This drives inflation. Again, this cannot be reproduced if you didn't have the anomalies in ordinary quantum field theories, and because the anomalies violate CP, you see another important role of CP in the early universe. The only difference is that now, due to the anomalies, this is a negative coefficient in contrast to the standard CDM. You can show the equation of state by studying that it satisfies the RVM, by studying the details of the cotton tensor. The important point is that if you ignore the condensate, this would be a phantom matter, because the sum of energies of the action, stiff matter, and the anomalies turn out to be negative, but because the contribution of the cotton tensor, as I mentioned, to the stress tensor are negative, but the condensate compensates for that and makes it positive. So it turns the phantom matter to a true vacuum. This leaves, as I said, one diluted exit from inflation, and this is important for leptogenesis. At the end, now I finish in the next 3 minutes. For consistency, at the end of inflation, the chiral matter is generated. It generates its own anomalies, and then they can cancel with the gravitational anomalies that you had before. This means that, of course, you have to consider a model where there's correct fermion species, and that's what's happening in string theory, is such that it cancels this anomaly. Once you cancel the anomaly, you can leave chiral or cube gluon anomalies, which could be important for making the system getting masses to the action. The temperature dependence can be studied, is consistent with current limits. I will not discuss this, and moves to leptogenesis, which is my penultimate topic. In models with right-handed neutrinos, the background is this. That's the extra term. The rest are standard. That's the background term due to the B dot, to the gravitational action, which is slowly moving. It gives a Kosteletsky type standard model extension, which at 3 level implies that if you have right-handed neutrinos, the decay of the right-handed neutrinos to leptons and antileptons is different because it's proportional to the background. And that has to be contrasted with the standard CP violation, which is through loops. This is the lepton asymmetry. B0, you assume that B0 is much smaller than the mass of the neutrino. These are some numbers which are consistent with its slow varying. And then this lepton asymmetry is converted through B minus L conserved Fallovan processes to baryogenesis. So finally, to conclude, we have discussed inflation. We have seen that in deflation, you have an undiluted action field. It produces leptogenesis. In the matter era, because of this chiral matter anomalies left over, you may have an action, fundamental action, which is of its mass could be, because this depends on the string scale, and you have this window of the masses, that's a QCD action, but you may have other actions. This, because it's related, this means that this action, this Kalbramon action, which was massless originally and it was related to torsion, now plays a role of dark matter, and therefore you have a geometrical origin of dark matter. And then you have the modern era, which you find again, due to these constraints, that a curious coincidence, you still have a slowly rolling B dot today, where the gravitational anomalies resurface because the chiral matter is diluted through the dominance of cosmological constant, but the order of the slow roll is surprisingly of the same order. This we need to understand better. This comes from this thermal evolution, as I've said. We need to understand the modern era. We have this deviation from the standard model. Now nu is positive. You can show that this is positive. This doesn't play a role in the phenomenology, because H0 is actually suppressed today, is the present Hubble constant. This running vacuum model, this new parameter, could alleviate the tensions, as you can see in the works by Solar, Gomez Valend, and other collaborators, Cruz and Moreno Pulido. They've noticed that this red, which alleviates mostly the tension, is due to some mild logarithmic dependence on this kappa, which we do have in string models as a result of quantum gravity fluctuation. So this brings me to my conclusion. I will not repeat the solution. The only thing I say is that I argued that we exist because of gravitational anomalies. due to this, which coupled to this axial background, which is undiluted. And I can paraphrase Carl Sagan who said that we are made of star stuff. We are anomalously made of star stuff. I argued that this action could play the role of dark matter. You have other actions in string theory, of course, model dependent, so the phenomenology is much richer. You can look for imprint of this spontaneous Lorentz violation due to the constant background in CMB areas. And finally, if I don't know this answer, whether you can have some understanding of this negative coefficient, which happens during inflation. But I don't know experimentally how you do it because it involves a phase transition. So thank you very much for your attention.
Thank you very much, Nick, for this very rich presentation. So I think we now have time for question. So please, you can ask. You can raise your hands, or you can also write in the chat. If there is no one, I will try. Okay, Giovanni, yeah, you raise your hand, right? Because I can see two symbols.
Yes, I'm learning how to raise my hand. Nick, one curiosity, the interval of values of the string length
Yes.
in relation to the Planck scale, does this mean, did I get it right that it's a rather small string length that you expect? Is that
yes, in this model is only in mass terms is only at most 5 orders below the Planck scale, so 10 to the 14 GeV, close to the gut scale.
Okay, so you have a large string length.
It's a larger string length than the Planck. Yeah, it's not the Planck length precisely.
So
but it's not so large. It's not TV scale. It's not as
no, of course, but it is. This would be good news for phenomenology, basically, to understand correctly, because you would have a slightly more forgiving scale to.
Yes, and in fact, if you notice, some of your models as well, your phenomenology or our phenomenology, this is the scale that you could get. That's the string precisely. The Planck scale, 10 to the 16, 10 to the 17, you reach that sensitivity, yeah?
Yeah, in fact, it's funny because actually when I fit those data in my previous slide, in my slides, I didn't take the time to emphasize, but I get a, let's call it optimistically, a quantum gravity scale, which is significantly smaller than the Planck scale, out 10 to 17 GeV.
Yeah, that's mine is even 10 to the, it is around that scale, between 10 to the 3 orders, between 3 and 5 orders of magnitude smaller than the Planck scale, precisely. And you get it because of the slow roll. You get it because of the parameters of the model. You cannot avoid it. Otherwise, you don't have the constancy.
Well, I think this is very interesting. Thank you.
Thank you.
Any other question? Okay, if not, let's thank Nick again. And we can move to our third speaker, who is Alfredo Iorio from Charles University. And he's also one of our member of the advisory board. So please, Alfredo. Hi, you can share your screen.
So I share my screen, right? Is it working?
Not yet.
Not yet. So, is it working now?
Yeah.
Okay. Just let me go full screen. Excuse me, it's taking. There you go. So can you see full screen?
Yes, perfect.
Okay. All right. Thank you so much, everyone, for having me. And now I'm on the other side. I'm a speaker rather than I would not define myself an organizer, but a worker of this sort. Okay, so this is a meeting organized by young people, and as you see from my first slide here, this is a game for young people too. I mean, this is a beautiful thing. I keep using it in my talks because I loved it from a few years ago, and I keep using it. I think it's actually an advertisement for a movie or a cartoon movie. That is about hunting quantum gravity with analogs. Okay, so you need a little imagination here. So I like you to use it in this talk. Okay, so let me go straight to the point because I have time, but not so much time. I'm trying to measure my time. So it is going to be sort of three parts. The first part, I'm going to attempt a general discussion about why analogs are important for probing unknown physics. So in my view, they can be taken more seriously than just amusing reproduction of known phenomena. And I'm going to use, since this is a very highly debated thing, especially in the area of philosophy of science, of serious philosophy of science. And I hope that some of the philosophers I have pointed to the talks are in the audience now. Then I'll move to the one particular case, which is the other way. I mean, my history went the other way around. I first bumped it into how graphene could actually reproduce some high energy phenomenon, and then I tried to learn about the basics of that. And the first two parts will be sort of very general. And I know that from our community, people like to see concrete equations and stuff like that. I'll try to be a little bit more concrete in the specific case here, where I will refer to some recent results that we published last year, along with Gaetano Lambiase, Fabio Scardigli, and Pablo Pais, who are probably listening to the talk. Okay, I don't know if you actually see everything clearly here, because I keep seeing things on the screen. Okay, yes, so
we can see. Yes.
You do. Okay, so this is the analog bit, and I use as an introductory slide a beautiful picture taken by a photographer which is based in New Zealand or Australia, who used to take pictures of waves because they look like mountains, and he has many of them. And okay, so this is something I like to watch every now and then in my office. Okay, so here I'm going to give you it is my attempt to do some philosophy, okay, here, so you be a bit patient with me, but I'm going to do it by using a beautiful lecture written by Feynman, well, probably written by some of his students, but given by Feynman, which is I think chapter number 12 in its third volume second volume of the Feynman Lectures on Physics, and it's how electrostatics can be used, I mean, as a reference frame for various different things. Okay, and here you have a list of these things. Okay, the flow of heat, the stretching membrane, the diffusion of neutrons, irrotational fluid, illumination of plane. In these 5 cases, Feynman, so he just starts from scratches and he builds up the equations, and he ends up always with the same equation here. Okay, well, variation of the theme, because you have to rename stuff. Okay, the rho is no longer the charge density, is something else. I don't know, this the density of the drum or whatever, and he ends up there. Okay, and this is the first part of his lecture that I think everybody knows about, and it's summarized here, is taken literally from the lecture, and it's summarized usually with the statement: same equation, same solutions. Okay, and this is something that you may picture like that. So you have these 5 cases, and they all refer to some electrostatics. So if you want to do some electrostatics, you can either do it directly, or you can actually go. You see my pointer? You do? Yeah. Yes. Yes, it was a yes. Okay. So you can actually do it. Electrostatics, you can go. If you prefer neutrons, you go neutron diffusion, and then you have some sort of answer. But all these arrows here are completely undefined. These are left to art. Okay. And of course, the art of Feynman was very big. So people trusted him, and that lecture became famous. But that's it as far as let me say the fame of this lecture into our community. That's where it stops. But there's a second part of his lecture that probably people haven't read carefully or at all, from my experience at all, which is the fact that looking for some sort of criterion. Feynman goes beyond that and says, I want to ask even more questions now. Or why is it happening? I mean, how can we give some meaning to these arrows here, these black arrows? And we actually are in physics. We know in theoretical physics, we know how to swap one system with another. Okay, and do calculation in system A, and knowing how to pass this calculation over to system B. We know the concept of symmetry, where actually this system are so, I mean, this criterion is so tight that the action is the same. Or we can use a variation of the theme, like duality, where the actions are no longer the same, but they look like very much each other. So you have a map, or even something more elaborate, like a connection, I mean, correspondence between correlators and exactly, no. You don't have to go from scratch and so on and so forth. So this thing is not applied as yet to in a systematic way to analogy. Okay, so here is where Feynman goes on with this thinking, and I recommend this reading very much, because I think that he gave me us, let's say our group, two things. One thing was to push towards trying to find very, I can say, solid reasons on how analogs should talk to each other. I mean, why something is analog to something else. It's only a matter of two equations being similar, or can we establish something tighter, something stronger, something more reliable? And I'll show you, hopefully, if I rush a little bit more, how this applies to the case I have been studying. And also another case why we're grateful to him, because he gave a name to certain structures that are at the fundamental, say, what we may call the fundamental constituents of nature, that he started positing only on the basis of this this reasoning, okay, about why analogs are actually reliable. And he gave the name to this thing, he called them axons, and you will hear about that later in this conference. Actually, probably the last talk of the conference is about these axons in a purely quantum gravitational way, but that you will not hear about analogs. You will hear only how these things can be actually implemented or inferred from the Begerstein idea. Okay, so in picture, this is like moving up electrostatic also to this line and looking for some common structure. Okay, so here is some literature. I know that this is going to broadcast. It's broadcasted on YouTube, so people who are interested can just stop there and read it. I have time to go all this. Okay, so this is the Feynman electrostatics, and this is a work by the philosopher of science. Okay, now the case of graphene. Okay, the case of graphene is the one that we've been working on since a while now. It's about 10 years altogether. So what is it that I'm talking about here? I'm talking about the most two-dimensional object in nature, which is made of carbon atoms. It's an allotrope of carbon. Okay, so these white and black spots here, they're not white and black carbons because they don't exist. Carbons are all the same. Okay, but they are sitting in different sublattices. Okay, and it's very well known that if you want to describe the physics of the electrons jumping from one side to the other, you have to use, well, you may use some different methods, but the method is usually adopted is to use this just called the tight binding Hamiltonian. Okay, where this eta 1 here is what usually is called T, is the hopping parameter, and you see you have two families of creation and relation operator, which are actually fermionic, which is I and B. All right, and by the structure here, you can describe how this object jumps from one side to the other. All right, so what you usually do here, this is super well known, so I'll go very fast on this. What you usually do here, you Fourier transform. So the very same Hamiltonian you saw a moment ago can be written this way with a function, not a Fisher function, but it's a specific function which encodes all the information about the geometry of the lattice. Okay, I call it 1, the F, and the eta for reasons that you see in a moment. Well, probably at the end of this part. Okay, this is the function, how it looks like. So as I said, the geometry is into this SI, excuse me, how actually they look like. And if you want to describe, our condenser matter friends want to describe the physics of this object, they look for a solution to this equation, okay? Because this will tell what sort of object is this. If it's a conductor, a semiconductor, or whatever. And solutions of this equation here, which are the dispersion, I mean, we'll give you the dispersion relation, exist, and they're given by these 2 points. They're actually 6, but only 2 are non-equivalent. And when you write this Hamiltonian near to that point, that's what you get. Surprise, surprise, this is a Dirac-like structure, okay? So you're not in a relativistic setting. VF is not C, it's 1/300 C, but that's how it looks like. Okay, this story is super well known. Sigma, these are two-dimensional objects. Okay, so the vectors here are always in the plane. This is a super well-known story. Okay. The only step that we took here, we took it seriously. I mean, we took this relativistic structure seriously. We said, okay, let's think that this is a three-dimensional relativistic system. H bar was set to 1 at some stage, so I don't have it anymore. But I keep an explicit expression for the speed. Okay, the characteristic speed is not the speed of light, but it's VF. I put all together. You have various choices, and if you have the patient to wait till the end, you will see certain references where we actually take into account all these different choices. But you can put all together and treat these instead of 2 Weil Dirac, you can have 2 Weil spinors, you can have 1 Dirac spinor all together, and you have this. Okay, fine. So the step we took is where I didn't know at the time, but then I learned that I was using a sort of a strong analogy, okay? Meaning I was searching for a criterion on how to link this action, which is a space-time action, or if you like a different morphism invariant version of these, to this one. This one is taken sort of for granted. I mean, people would buy it, okay? I just had a discussion this morning with one of the guru of the story, which is Paco Guinea. We were chatting about something else, and he was the one that I convinced that if you take a certain specific limitation on the action, then you can actually accept it. Okay, so but then we have to find a criterion on how to go beyond that, how to implement this. And well, Weil symmetry, which is a way to connect metric to essentially a conformal factor, when you use it for the cases of conformal flatness, links this action to the flat. And this is what you see in the picture here, okay? You can change the metrics, but then you have a certain criterion here, which is the Weil symmetry that connects this to the flat case. So we are in 3 dimension. As I said, I was able to sell to Paco Guinea this metric, flat over the time, no time dependence. You ask for conformal flatness, well, it's a lot of stuff, but you still find something interesting because the condition boils down to have surfaces of constant Gaussian curvature, and that's it. This is the sector of positive curvature. It's essentially 1, but you can add some more stuff if you allow for certain singularities. And here is a family of infinite. There are infinite of them, starting from this arrow up to here. There are infinite number of surfaces of negative curvature. This particular one is very nice. It's been discovered by Beltrami. It's the first pseudosphere, but this is not why it's nice. It is nice because if you do calculation in there and you're careful, and you actually try to build these things really of graphene, that's why you see this picture all over the place here, then you can try to make some predictions based on field theory and Carver space, well, actually, in a Rindler kind of space-time, and you end up with this prediction, which is a prediction based on, I mean, it is like a Rindler effect, okay, in this context, with a specific temperature, which goes, you see here, over the curvature R. Okay, good. But I know I'm running out of time, and I would like to see much more. What I like, so let me say that up to here is quantum field theory in Carver space, but this is a meeting on quantum gravity somehow. So why I claim that you can go beyond that? Well, this is already quite amazing that you can find something like that. Okay, and we were actually quite surprised when that happened. We really bumped into that. I was coming from the Weil side symmetry, or conformal symmetry, like Carlos, who's listening to the talk, might remember, Carlos Nunez. Okay, but then I bumped into that, and then I thought, wow, but this is Rindler, so we can do that. So this is quite interesting already, quite a lot. But this is something one step only, because we can go beyond. You can write that Hamiltonian there, which I actually only can imagine because my Zoom here is covering that age. But you see, it's made of an infinite number of terms, of which I only showed you one, the first one. And if you go beyond, you go to F2, that by chance is given by this formula instead of the 1, you can go beyond that. And you can include effects where a parameter depending on the lattice spacing, so on this sort of fundamental length, is popping up in your Hamiltonian, okay? So your Hamiltonian here still has a sort of Dirac structure, but you have to go farther up in the second order, and you have this L here. And so you can take this Hamiltonian with this commutation relation where your deformation is in the Hamiltonian, but not the commutation relation. You can take the other view. So this is just a summary of a picture of why this graphene object, although it's such a simple object, okay, can even have this feature. And this is on the math side, but on the physics side, all I'm saying is that if you look at the dispersion relation, you see this is E versus K, the full, I mean, not P, the whole K, the whole momentum here. This is the, let me say, the whole energy spectrum. You have the whole energy spectrum at your disposal. What I was telling you about when curvature is present is this regime, which is a very large wavelength. Okay, when the wavelength is bigger than R and bigger than lattice spacing. But what everyone knows about is that if you go, so not curvature include, you can be in this regime where you know you have this Dirac structure here because you have wavelength much bigger than L, but then you can keep going and keep including some granular effects more and more into the system. Okay, so all of this was perhaps you know, amusing but sure you're not convinced because you haven't seen anything specific. Okay, you just saw a bunch of formula. Now I'll try to be a little bit more specific. This is a summary of our you know say some key references on the thing. The first one is a very old review, but I recommended by Paco Guinea and discoverer of graphene actually also, Novoselov guy. And if you want to learn about the basics, please go there. And this is where the thing of the Weyl symmetry started, and then work with Gaetano on the Hawking Guru thing. And these are all the recent work with some of the recent work with my collaborator Pablo Pais. And we have more stuff, but okay. So let me go now in the rest of the time. How much time I have? 10 minutes?
You have 14 minutes.
14 minutes. Yeah. Super. Okay, so in this 14 minutes, I'd like to show you one particular example, okay, which is a very peculiar black hole, which is already peculiar because it's in 3 dimensions. But we even go to a specific regime of that black hole, and I'll try to now explain how, you know, how you have to use all the symmetries at your disposal and all the peculiarities at your disposal. Try to fine tune in such a way that you can use this very simple object as a probe for quantum gravity. I'm not claiming you can answer all the questions, but I claim that certain questions can be answered. All right, so what I'm talking about is the m = 0 graphene BTZ, okay, Bagnados, Tattelbaum, and Zanelli black hole. And I show you here a picture, okay, that I will tell you quite a lot about this picture in a moment. You actually saw it already, but you haven't, probably you won't recognize it immediately. Okay, so so let me start from a story which I essentially have learned from some of my collaborators, which are listening to me right now, like Fabio, and I don't know Gaetano if he's tuned. And it's about the gravity-induced GUPs. You know how the fact essentially that if you want to localize a particle by you know, a bunch of photons, and these photons have an energy E, okay, well, you should also consider the fact that this energy can be, you can associate to this energy a sort of a radius beyond which you cannot go. Okay, so you cannot localize beyond that radius. The idea is that well, it's all Gedanken, of course, and that's why it's beautiful to go in there with graphene, because graphene you can measure stuff. Well, the Gedanken thing is that you actually try to probe the measurement. You form a micro black hole. Okay, this is something that is usually referred. I mean, is formalized in this fashion. So this is the first bit is a standard thing. You see, the bigger the R is the energy here. The smaller is this delta x when beta is 0. But with beta non-zero, you have that it's the other way around. Okay, E is upstairs. Fine, this is all known. Then you can do some algebra in using the you know, rotational symmetry and so on and so forth. And you have this modification of the general of the uncertainty relations. Okay, this is the stuff written in n = 4. Fabio and alone, and then with collaborators, they've been working on higher energy. Then we met. They said, but you are doing a lot of lower dimensional stuff. How happens? And why don't we do some graphene thing over here? But then I said, well, how about your GUP? Can you actually do anything with n = 3 or n = 2? Well, there are issues there. There are issues in 3 dimensions, even more in 2 dimensions. These issues are essentially related to the fact that you can go up in dimension and you keep all your standard geometric tensors, the Weil tensor, the Riemann tensor, and so on and so forth. They get more complicated, they have more components, but they don't, they don't blow up or something. Well, when you go down in dimensions, it's the other way around. They actually do blow up. Okay, Weil tensor, for instance, is identically zero. So you have to, be careful. So RG is actually undefined. You cannot really define in general an RG unless you rely on this beautiful solution, which is the BTZ black hole, which indeed exists in 3 dimension. Here I write again the line element of this solution. This is standard fashion of writing black hole matrix. Okay, so you have an f of r squared and the same object 1 over the same object, with this f of r defined over here, where all the important quantities of the game are included. Okay, the mass, the angular momentum, and lambda. Lambda is quite essential here because you do need to have some negative cosmological constant to have the solution. You cannot just set this to 0. But as you will see in a moment, you can actually do the other thing. You can actually set the mass to 0. Okay, and you still have something. Of course, it's very peculiar, but it is not the vacuum solution. Okay, it's not the bottom of the spectrum. So the horizons are found in the usual way. You take f of r and ask it to be to 0, and you find those two solutions. R plus is the event horizon. Okay, and you have black holes when this parameter is greater than 0, which also tells you that J must be like that. The extremal case, as you can see from the bottom line here, is also quite interesting. This is what you may find defined as a peculiar massless black hole. Okay, because you see, it's not the well, you should not expect here Minkowski, but you should expect that an anti-de Sitter as the end of the spectrum. But this is not anti-de Sitter. This is something more interesting. Okay, so we take 0, J, and for non-zero mass, we've been able, in a paper that I will cite at the end of this part, to find the gravitational radius. Okay, so even though things are very much more complicated in lower dimension, if you think that this localization process forms a micro black hole, which is a BTZ, and you take the simple statement that J equals 0, you can define your RG as an R plus. But when M is equal to 0, you can still think of doing it by redefining this RG like this minimal length L. But this minimal length is completely theoretical. Then we have nothing to hook at. You would like to hook it to the Planck length, okay? But you have nothing. Oh, it's just an external input. Now I'll show you that if you play this game in graphene, you have a very natural way of seeing what this capital L is. Okay, so first of all, you have to notice that the J equals 0 BTZ is conformal to a space-time which is made of this hyperbolic pseudosphere with this line element, okay, times R. So you glue R time like that, and this is as I show here in this parenthesis is one member of this family of constant negative curvature. Don't be. I hope it's clear. My notation is clear. I don't define it too much. But this capital, little r, lowercase r is a constant. Okay, it's something that it can vary, but you have to you changing your space time. All right. While the variables are differently, the notation is different from the variable. Okay, so this is the line element for this object over here, and you see here a C parameter, which sometimes is overlooked in differential geometry, elementary differential geometry. So let me write it again. So this is like just a surface of revolution with the radial coordinates, which is this thing is the radial coordinate square. So let me rewrite it. I call the radial coordinate r a rho. So that radial as this C cosh of u over r, which this radial coordinates has a maximum and a minimum. Okay. So the minimum would be over here. You see, on the corner, you always have the picture of that object in a particular limit. Okay. So the rho minimum is
5 minutes. 5 minutes.
5 minutes. Okay, I can make it. So this C is the minimum of rho, and the maximum rho is given by that. You can you have a minimum and a maximum, which is somehow typical of the surface of negative curvature, because beyond these values, okay, the coordinates become imaginary. Okay, so you always have some sort of boundaries. Okay, and these boundaries not all the time are so clean like here. You see little circles here, but when they are, we invented a name. We call that the Hilbert horizon. That's an abuse annotation of naming. Let me say. It's not an horizon in the general relativistic sense. Okay, it is a boundary of the surface, but we want to stress that that boundary is unavoidable. Okay, we cannot avoid. This is a very deep theorem of geometry. We set this contrast to 0 now, and you take the BTZ and you write it this way. Okay, with J equals 0, and it is an easy task. So you take this factor because you want to try to get close to this structure. So which is time r and the spatial part given by that. So the overall line element is going to be dt squared, and then plus du squared, something like that. So the first thing you do, you isolate dt squared. And how to do it? Well, you take away this factor. Okay, and what is left in this ds squared is, as I said, dt squared, and then the rest. Okay, minus because you have the signature. All right, so you see that r plus is just the event horizon. So what you do, you redefine your coordinates, and you call du this way with a new radial coordinate with capital R, no rho anymore. And then you link this new radial coordinate to the old one, to the rho, through this equation. And that's it. You have a system of very simple differential equation. You solve them, and you find capital R in terms of u, which is given by this expression. You see, R plus hyperbolic cotangent of this object. You put it back into rho. So I show you step by step. And there you go. So you see again that the radial coordinate has got exactly like the one of the hyperbolic pseudosphere. That's what you want to prove, that this is conformal to that. But with C equal to L. I mean, what it was called C before, now it's L. So we have a meaning. We know what that L is. Remember, capital L minus 1 over capital L squared is the cosmological constant. Is that object that we wanted to find the physics of. And here is the minimum of this hyperbolic pseudosphere. But if you want to really be consistent, okay, what do you have to do? You want to go into this limit. It's only in this limit when C over R goes to 0 that indeed your Hilbert horizon, this boundary, reaches, coincides, or I'll show you in a moment what I mean by that. So physically, let me say, coincides with an event horizon. And if you do that in this limit, okay, you immediately see what's the meaning of C. Because when you actually take this limit, in the limit of C over R going to 0, this surface becomes this surface. And as I said, this C is the minimum of these, is this point. And if this is made of graphene, you cannot go beyond C equal L, the lattice spacing, or something of the order of the lattice spacing, because that the structure would just break. So you have a clear physical meaning of that. Capital L is, let me say, lowercase l, the lattice spacing. So in graphene, if you realize this structure, which means you go in a lab and you build up an object with that shape. This is something I always found quite amazing. You don't have to shoot an object up in the sky or do something very complicated. You should do something that is mechanically difficult, but it's doable. It's, let me say, conceptually easy. If you actually do that, then you have realized a structure, careful, which is conformal to the BTZ through this equation, okay? And with all the constants here related to something you have in your physical system. The cosmological constant is minus 1 over L squared. This is the lattice spacing. The mass is given by this expression. The horizon is given by this expression. As I said, you have to go in that limit, in the limit of L over R going to 0. Well, in that limit, you can write the Hilbert horizon in terms of R. This is the general expression, the exact expression. It's true all the time. And you see that the Hilbert horizon, which is where the surface ends, is equal to the event horizon times this function. When you can, for instance, approximate, you can write that second, the curvature is such that it's 10 to the NL, and the RHH, the Hilbert horizon, is given by this expression. So they are really much the same. The only thing you have to do is to take a big enough object. So all is consistent. In this limit, you have given meaning to everything. Okay, fine. So the reference for this particular part is this paper, which was published last year. which, as I said, with this gentleman on board. And here, just let me give you some credits, not just to them. You see Gaetano over here, but then to my closest collaborator over the last year, which is Pablo Pais, with whom we wrote a string of papers on these things. And then Luca, which has joined us already a bit more than 1 year. And Giovanni Amelino, which now left, is on the one hand, I'm sad because he left us. On the other hand, I'm very happy for him because he's now working in Tenerife, which is not a bad place to be. And with Giovanni and Luca, we've been, and the late Martin Scholz, actually with Martin, we started this adventure. We've been thinking of how to use the analogs the other way around. I mean, getting inspiration from graphene to try to say our own word on how the fundamental picture should be on the quantum gravity side. Last thing, I was sort of earthed by universe, since you are also involved. We are also, editing a quantum gravity phenomenology issue, where I'm proud that part of the issue will be dedicated to analogs, but not only. I mean, we have Martin Boyovald on board, Singh, who's also with us, and Bombelli. So we have both sides of the story. So if you feel like you want to contribute, there is still time. This deadline will be changed to something beyond the summer. Okay, let me close with this picture of my collaborators. Thank you very much.
And thank you very much, Alfredo, for this nice talk. So we have 4 minutes for question. So please, you can ask for, we have 3 minutes and a half for question. Let me be precise. So
Nick, go ahead.
Yeah.
We have, so Nick, sorry. It's good.
No, yeah, it's fine.
Luca, I was doing your job.
No, I think he was
sorry.
clapping. He was clapping, no?
No,
I'm fine. Yeah. So it's okay for me now to speak or not?
Yeah, sure.
Okay, yeah, sure. Thanks.
You were clapping or not? You were clapping or I want to know if you were clapping.
Well, first of all, I'm clapping, okay. But I'm asking a question as well. Sorry. Very nice approach, very nice talk. Did you think of incorporating gravitational anomalies in your analogs?
Of course. This is something...
because, as you know, I mean, you should in principle, once you have the metric, you could see. So can you test, for instance, models that I was talking about? For instance, if you could test a gravitational anomaly using graphene, if the metric is of that form. You have to, of course, has to be a specific form. So I don't know, but for graphene, but...
Absolutely, yes. The answer is yes, and we're actually working on it. I actually had a question for you, but I postponed it to the discussion.
We can
chat after Salvatore's talk. Yes, we can. You should think this way, which is a little subtle, but I mean, it's not straight into the gravitational anomalies, but it goes very much there. Think this way: Weil symmetry, which I use to do my solid analogy, otherwise it's just blur, okay, is using the diffeomorphism invariant version of the action, okay? Now, if you want a diffeomorphism invariant version, you need diffeomorphism invariance, at least at the formal level. And once you have it, you take scale symmetry and you promote it to Weil symmetry. So these two processes of having diffeomorphism and Weil invariance, they should commute. So I can, for instance, I have different, and then I mix the theory, the diffeomorphism covariant, and then I have Weil invariance, or vice versa. Well, you find that in certain situations, which are the ones we're looking at, this does not happen. This was discovered by Roman Jakiv, who saw a paper of. Hello? I'm beyond at the time. I mean, yes,
no,
you
sorry,
can.
Your connection was cut.
My connection.
No, I was hearing it fine.
So I go.
It was mine. Okay, sorry.
You're fine. Yeah. To me,
okay. We can discuss in the now in a moment much more in detail. But the idea is that one way to do it is to see whether you can move both nodes. Okay, the Weil and the diffeomorphism. Because if you cannot, you find a situation where you have a choice. You can either see a Weil anomaly which is interesting, but not so much. Or you can see a gravitational anomaly.
Very nice.
Or sometimes you can see even both. There are
Right.
people from Germany who a couple of years ago have been publishing something in the interplay. But yes, I mean, in principle, you can, absolutely.
Very nice. Very nice. Thank you.
Thank you.
We also a question from Luciano.
Okay. So first of all, Alfredo, thank you for having shown the picture of Gaetano Lambiase back 20 years ago.
It's the only one I can find. I'm looking, I'm asking him, he'll never give it to me. And I'm looking, so in this picture looks as young as my student, Pavel.
Yeah, but also thank you for a no hair Luca inside in the picture. So, okay, apart from this, because I was, okay, talk was really nice, and in particular, I was thinking about the connection between the generalized uncertainty principle and the BTZ black hole. Well, according to the solution that you've shown, it seems that there is a cosmological constant there. So I always think it was, apart from the generalized uncertainty principle, there is also another generalization, which is the extended uncertainty principle that accounts for minimal uncertainty in position. And so a modification which also entails an X in the right-hand side of the Heisenberg uncertainty principle.
Yeah,
and
yeah.
typically, okay, when you, here, you have also something which does not depend necessarily on the energy only, as the RG expression, but also on X. So, and typically, at least for n equal 4, this kind of generalization is related to the presence of a non-vanishing cosmological constant. So I was thinking, probably, can this be inserted somehow in this discussion? Or I don't know if you're familiar with the other, the extended uncertainty principle or not, but
I'm not. As I said, I learned that from Gaetano and Fabio about the general. I mean, I know vaguely, but on the so for instance, I know that this one we're looking at right now uses spherical symmetry. If you don't have spherical symmetry, then you may. I guess you can start having something that may depend on the X. I don't know whether this is. But to go to your question. It is this. I would not use the word unfinished because the paper is self-consistent, but that part could be probably part of the paper because we didn't write. See, here I didn't show you how to. Here I show you how to go from this delta X to this GUP down here, but I didn't show anything similar for the other thing because we don't have it. So I would really love to go in that direction and learn how to use this result, which is, I think for me, it's very nice. It's simple. I show you all the steps. Okay, I was not cheating. I went all the steps till the end, and I show it to you that this is so natural because you do have a physical reason there to stop at this value. Okay, otherwise, why you should stop? And the nice thing is that you can fine tune your not so much. I mean, you can play with your parameters so that you have a natural capital L equal to the lattice spacing and a natural reaching of the horizon. You don't have to go. You see, we made the estimates, and I even talked to experimentalists at some point. You don't have to go kilometers. You need microns. An object big. So this is something doable in principle. So to answer your question, I don't know how to actually do it, but I don't think anyone knows at this level, at least. And it's a good idea for a paper, if you like.
Sure, why not? Okay.
Okay, very good. So there was also a question by Gaetano, but we can postpone it to the discussion session. So Alfredo, thank you very much again.
Thank you.
From everyone, on behalf of everyone. So we can move on now to our fourth speaker and the last speaker of this session with Salvatore Capozziello. Salvatore, are you there?
Yes, I am here.
Hey, how are you?
Fine. And happy to stay with you.
Ciao, Salvatore.
Very nice. May you see the screen?
Yes, we can see. Can you do full screen?
Yes. Is it okay? May you see it?
Just 1 second, maybe it's loading.
Okay.
Well, we see black, basically, just black screen.
Well, there is a clock, so I think it's loading. I see a small clock in the left
Okay.
in my screen, but
Salvatore, can you see the standing screen or?
Yes, I see the screen, but may you see the motion of the?
there is black and a small clock somewhere on the left.
Very strange.
I think you have a Mac, right?
Sorry, what?
Do you have a Mac as a?
Yes, I have a Mac.
Okay, so I think it's the same problem. When you do the screen sharing, maybe you need to select desktop.
Okay.
Yeah,
okay.
maybe
I am going to go out. I have to go in the. I cannot move. Oh, okay. Desktop in the sharing.
Maybe you need to stop the sharing and start it again. Yeah.
Okay. Desktop. This one. Okay. May you see it?
Yes. Let's try with full screen again.
Yeah. Is it okay?
Yes, perfect. Okay.
Also, if I move?
Yes, it works.
Okay.
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 So please.
First of all, congrats to my friends for this very, very nice congress in which you are really joining up all people working in very different topics. So in my talk, I would like to convince you that the effects of non-local gravity can work at infrared and at ultraviolet scales. And then, according to this, very likely, some issues like dark energy and dark matter in particular, that are strictly effects that works at infrared scales, could be in some sense obtained by the gravitational issues, and in particular what Nick mentioned before. In some sense, with some kind of gravitational anomalies, in some sense you can have a very comprehensive picture of the universe. And today I would like to show you that this kind of feature is quite common in several theories of gravity. And then the invitation of this talk is that just try to take into account these non-local effects, which could work not only at the cosmological scales, but as I will show at the end of my talk, also at the galactic scales. So the outline of my talk is this one. I would like just to point out some features related with locality and non-locality. Then I would like just to discuss a little bit what does it mean non-local theories of gravity. Then I propose a way, an approach to work out this kind of models, which sometimes can be very, very, very cumbersome to be worked out from an analytical point of view. And then I would like to propose this matter-symmetry approach, which seems very profuse in order to get a solution. And then I will give some examples. For example, we have non-local theory starting from scalar curvature, for example. We have non-local theory related with the topological invariance, for example, the Gauss-Bonnet invariance. And then, from a completely different point of view, this kind of local theory, non-local theories can be obtained also in very different approach. If for example, you take into account this teleparallel gravity, which is a very, very profuse approach, because it is not using at all the equivalence principle, and then it is very good in order to be matched with quantum field theory. And finally, I would like just to give you some astrophysical tests by which this kind of theories could be probed in some sense also in the framework of our galaxies. Okay, so all of you knows very well what is locality and non-locality. I like to say that locality means states, while non-locality means in some sense interactions, dynamics. And then you know, all of you knows very well that the classical theories are local, and then classical mechanics means taking into account points on a tangent or a cotangent bundle. While, for example, conformal field theory means tensor fields over a manifold. On the other hand, from non-local point of view, you have quantum theories, which are non-local. You can have the Born interpretation, the Heisenberg uncertainty principles, and then it seems that they are conflicting each other. But we will see that in enlarging our approach, it is possible to solve out this kind of conflict. Non-locality in physics means, for example, taking into account some fundamental interactions which are considered non-local. And in particular, as soon as you are considering one loop effective action, immediately you have this kind of non-locality emerging in physics. In particular, the Euler-Heisenberg-Lagrangian, which is this one, is a very standard approach in order to show non-locality from some point of view. On the other hand, you can have also the Yukawa-Lagrangian. Also, the Yukawa-Lagrangian is give rise to an effective action. And then in this case, the non-local operator is just given by this box operator and by this propagator in some sense. So these are very well-known and very, very good examples of what does it mean non-locality in physics that cannot be ignored from a fundamental physics point of view. So in some sense, what we have that local action means that it is a functional only on local fields, and then you have algebraic functions of fields or their derivative, which are evaluated at single points. On the other hand, you have non-local action, and then you have a functional of non-local fields, at least one, and in particular, you can have a function of these fields evaluated at more than 1 point, and then they are very transcendental function of fields and their derivatives. If you want a very good introduction and a very comprehensive introduction on this, I suggest you the PhD thesis by Luca Buoninfante, which is very, very good and very well written in this perspective. From this point of view, you can see that, for example, GR must be changed and quantum field theory must be changed if you want to join together these two very, very fundamental aspects of physics. In particular, you have shortcomings in general relativity, and all of us knows very well that you have shortcomings at large scales from one side and at small scales from the other sides. But that means nothing more than you have shortcomings at ultraviolet level and at infrared level. So at the moment, in my opinion, no theory is capable of solving these problems at once so far. So if you wanted to link together these two approaches, I mean gravity at ultraviolet and at infrared scales, you need something in which some common feature can be in some sense expanded at both in both limits. Okay, so in particular, we are facing the problem that there are no evidence from dark energy and dark matter at fundamental level. Now there is this claim for the anomalous spin of the muons, but it is nothing else but an indication. But the final answer saying that dark matter and dark energy can be some new particles at the moment does not exist. So the question is, the dark side can be in some sense solved by non-locality, in a sense that dark energy and dark matter could be at the very, very fundamental level, nothing else but the manifestation of non-locality of gravitation at this kind of scale, at astrophysical and cosmological scales. As you know, there are several attempts in this direction. In particular, you have several local extended theories of gravity. In some sense, they can be formulated in the so-called Palatini formalism or in the purely metric formalism. So you have scalar tensor theory, you have higher order theories. In particular, you have the Starobinsky model, which is very successful in order to address inflation. But you can have, in some sense, a plethora of theories considering the fact that you can take into account a multi-loop expansion of gravity, and then you can take into account all the terms coming from this kind of interactions. Okay, so the procedure is well known, and at local level, several of these theories could work as extension of general relativity. But taking into account the non-local counterparts of this extended theory of gravity, what we can do? We can try to see if it is possible to construct some infinite derivative theories of gravity, or some integral kernel theories of gravity. In a sense, let us try to see if it is possible from a gravitational point of view, considering extensions which can be related with the two main approach that you have in non-local gravity, in particular in terms of infinite derivative theories and in terms of integral kernel theories. Then just to give rise to an analog, and according to this analog, let us try to see if it is possible to work out this kind of theories. In particular, what is an infinite derivative theories of gravity? In this case, what you have, this is a sort of a prototype of this kind of theory. You can start from some infinite derivative Lorentz invariant action, which depends on scalar fields, and then you have that these terms, it is a standard general operator depending on the distance, and this is a sort of prototype of this kind of theories. Then you can work out this by some Fourier transform. You can reparameterize this kind of theories, and then you can get this formal approach by which you have that the operators can act on a given field phi in such a way. So if you know the form of the operator, in some sense, you know how it is acting on a given field. On the other hand, you can construct the infinite derivative theories of gravity. In particular, there is this very nice paper by Biswas, Gerwig, Koivisto, and Mazumdar, in which they take into account the fact that you can construct a most general gravitational action in 4D, and then you can take into account quadratic curvature and ghost-free terms. And it is interesting to see that in some sense you can get your theories taking into account a sort of scale by which you have the mass that is working in such a way. So just to end up, what you can do. So you can take into account some infinite derivative theories of gravity, and then you can work out, considering the fact that you have some super renormalizable and unitary theories, in particular these papers by Modesto and his collaborators are in this direction. They admit a regular black hole solution. They have a maximal ultraviolet complexion, and in particular there is an extension of the Starobinsky model taking into account this kind of situation. It is very interesting, the point that I would like just to stress here. As you can see here, these exponential terms giving the operator by these people is put by hand, because they see that it gives rise to some super renormalizability. I will show you in a moment that this kind of terms can come out from some first principle, because it can be recovered from Noether symmetries. So it seems that symmetries give rise to a good approach in which you can get this kind of super normalizable operators, but starting from some conservation laws. Okay, so why you can take into account this kind of approach? The first approach in this perspective was given by Desiree Woodard, which tried to develop a sort of non-local cosmology in this paper of 2007, in which they just put a term, and this kind of term is the one that you can see here, and what they say is that this kind of term can give rise to some acceleration effects. In some sense, they try to address the accelerated expansion of the universe and then the dark energy just by taking into account this kind of terms. And in the paper, there are some numbers which can be related with this approach, And then, in some sense, they claim that according to this approach, you can have an indication for accelerated expansion. So my question is this just a chance, or this is a general feature that you can have in non-local theories of gravity? So our investigations started exactly from this point. And then, in particular, we tried to see if it is possible to consider some main theories of gravity, in particular, theories in which you have extension which are curvature-based, extension which are torsion-based, and extension based on topological invariants, in particular with this Gauss-Bonnet invariants. And then let us try to see if it is possible, according to this, try to get cosmological solutions in which you can have accelerated expansion from one side. And finally, try to see if, starting from this kind of theory, is it possible to reproduce, for example, also the galactic dynamics. So this is the research proposal that we are trying to study now. In order to get this, we started from the nether point symmetries that these girls developed in more or less 100 years ago. So let us try to see, instead of choosing this kind of non-local theories, just like a toy model, is it possible to find out their form if starting from some first principle? In particular, the existence of nether symmetries give rise to conserved quantities from one side, and from the other side, it fixes the form of the effective Lagrangian, and then eventually, at the end of the process, give rise to exact solution. And then we developed the so-called nether symmetry approach, by which the recipe is nothing else but this. Is it possible to consider a related point like, in particular, cosmological Lagrangian? You can search for some nether vector and searching for eventually this kind of Lagrangian which shows nether symmetry, then derive the nether point symmetry, and then obtaining a system of partial differential equation fixing the form of the symmetry and fixing also the form of the Lagrangian. Starting from this, you get for free a reduced dynamical system which can be integrated, and then you get exact solution. With the people working with me, we developed several of these kind of Lagrangians, and the answer is quite good, because anytime that a nether symmetry exists, it is possible from one side integrate the system, and the Lagrangian has a physical meaning. So it seems really that the nether theorem is a sort of first principle, which is saying us, please, when symmetries exist, it is not just for simplifying your life, but also because they have some physical meaning. So let us go to the topic of this talk, and in particular, let us try to see if with this machinery, in a sense, with this nether symmetry approach applied to non-local Lagrangian, is it possible to work out some theories, some effective theories that eventually can show cosmological solution, and this kind of cosmological solution could be in the Desert and Woodard approach and giving rise to dark energy behavior. So we started with a curvature-based extension, which is this one. So what is the procedure? We take into account a very general Lagrangian of this form. We perform a formal localization of the field, and this is the formal localization. And then at a certain point, we get some Lagrange multipliers inside the effective action. And these Lagrange multipliers can be strictly related with the fact that we are working out some kind of scalar fields, and these scalar fields have a direct origin in relation with the non-local terms. So if we apply this process to this kind of Lagrangian, you get this point-like Lagrangian, in which, as you can see, you have two Lagrangian multipliers, and then you can get a sort of effective mini superspace in which these two fields has a strict meaning, which is related from one side with the scalar curvature, from the other side with the localization procedure that we worked out before. Okay, so you can get, if you are interested in all the procedure, I just give you some snapshot of this because from an algebraic point of view, it's quite cumbersome, but essentially the situation is this. You get a sort of Netter vector. If you apply this Netter vector to the Lagrangian, to the point-like Lagrangian that I showed you before, you get some solutions by which you can fix the form of this function f from one side, and you can reduce the dynamics. And then at the end of the story, if you take into account the whole system, you get 28 partial differential equations. It's something not so easy to deal with, but taking into account symmetries, it can be reduced. And then finally, we get these two kinds of objects. As you can see here, immediately we get that there is this exponential function, but please remember that the phi is defined in such a way. So as I told you before, the Netter symmetry are fixing the form of the non-local term in this way. And furthermore, there is another nice feature, which is this one, which is related with the fact that you have a logarithmic behavior. And then you can get a sort of terms related with the regularization of your fields, related with the fact that the Netter symmetries is giving rise from one side from a sort of renormalizable terms and from a sort of regularization terms. Then you can consider, for example, the first case, if you take into account the first case, and then the first case with a simple choice of this function, which is a class of function essentially, give rise to nothing else but the non-local extension of the Starobinsky model. In some sense, you get the Starobinsky model plus a non-local term. There is a very nice paper by Starobinsky and Mazumdar working on this, but they just put these terms, logarithmic terms, by hand. In this case, it comes from a non-local extension. Then immediately you can get the cosmological solution, and as you can see here, the cosmological solution are very nice solution because you get an expansion, which is a sort of inflationary behavior, and a sort of power law solutions. But the interesting point is that these are nothing else but particular solutions, because the system is quite involved. But the point is that you can solve, in some sense, the system. From the other side, you get essentially a similar situation. In this case, you can have that you have nothing else but standard general relativity plus a minimally coupled scalar field, but we know that this kind of scalar field is nothing else but the non-local terms. So in some sense, you can get a sort of regularities, and in this case, for example, we get a radiation like solution. So in some sense, the Netter symmetry allows us to get a radiation-dominated universe, starting from this approach. In the other case, in the sense that you can take into account the second case selected by the Netter symmetry, also in this case, you can choose the form of this GR. GR is a function. You can work out in the same way the solution, and also in here you get, for example, exponential expansion from one side, and in some sense you can get for free accelerated expansions. The other case that can be developed, I like a lot this case because this case is ghost-free by construction, and also in this case you can consider interesting. You can take an interesting solution eventually related with the general relativity. In particular, it is very nice to point out that you have a Gauss-Bonnet invariant that you know it is trivial in 4 dimensions, but it is interesting that the existence of nether symmetry select this kind of solution. This kind of solution, in some sense, in cosmology at least, can give rise immediately to standard GR. So GR can be considered a sort of further terms related with this specific case related with this approach. So also in this case, we considered a very general Lagrangian. We work out exactly the same procedure. I don't want to bore you too much, but also in this case, it is possible to get a formal localization of the terms. You can get the form of this Gauss-Bonnet invariant in terms of the Hubble parameters and of the standard cosmological parameters. And also in this case, you get two effective fields, one related with the Lagrange multipliers and the other one related with the non-local terms. And in the same way, you can work out the procedure. And then, in this case, the situation is richer because you have 37 partial differential equations. But you can get cosmological solutions which can be related with relatively simple terms. In particular, as you can see here, you get a sort of power law term. This term is not effective because in 4 dimensions it doesn't work. And this is the contribution related with the non-locality. It is interesting that also in this case you have an accelerated expansion, and in particular a very nice term. You can convert, you can regain the standard, the starting variables, and this is the action that you can get. So,
Salvatore, you have 5 minutes.
Oh, sorry, how much?
5 minutes.
5 minutes, okay. So in this case, as you can see here, it is interesting to see that the nether symmetry are selecting this kind of terms. I will go a little bit fast. And as you can see here, you can have also power law terms. In particular, you get also the standard matter terms. And then you can work out all this. And then it is a very, very general feature, the fact that you can get this kind of accelerated solution, or in some sense, the standard Friedman solution. So what happens if you put by hand this term into the action? It is interesting that putting by hand the standard gravity into the action, you do not get symmetries, and you can recover standard gravity starting from symmetry, but if you put by hand the Hilbert-Einstein action, you cannot get the same situation. Okay, so last case is this one. In this one, what we are taking into account? We are taking into account the so-called teleparallel gravity. Why it is interesting? Because it does not require the equivalence principle. We have no time now in order to develop in detail this theory, but it is quite interesting because it is possible to take into account a sort of affine theory, and in particular you have to take into account the so-called Weissenbach connection, and the theory deals with the torsion instead of curvature. In some sense, it is a gauge theory for the translation group, and these are the main ingredients that you can have into this kind of theories. Also, in this kind of theories, what you can work out a situation which you recover the standard general relativity by taking into account these boundary terms and putting it together with the torsion scalar. And then it is very straightforward to work out a sort of extension, in which you have that, like in standard gravity, you have FOR, in teleparallel gravity, you have FT, and so on. Okay, so non-local gravity, in this case, can be worked out just taking into account the non-local version of this operator. You can work out a localization procedure also in this case. You can get some Klein-Gordon equation for these further terms, and then you can get the cosmological Lagrangian exactly like in the previous cases. Now you have these two fields, which is the torsion and the boundary terms, which have to be taken into account. And as you can see here, also here you get some nice, interesting solutions. And then also in this case, you can have expansion, which can give rise to the standard Friedmann expansion or to the Sitter expansion, and so on. So the final issue is that what we are saying, please take into account non-local terms, because you can get all kind of cosmology that you need in order to get phenomenology in relation with it. Finally, just some snapshot on this. How we can say what is the good theory of gravity according with these non-local terms. In this paper, we developed some astrophysical consideration according to this, and also in this case, we select the theory taking into account nether symmetries, but in this case, we use the spherical symmetry, and we performed a post-Newtonian analysis, and in particular, we constrained the free parameters taking into account stars orbiting around our galactic center. And then we can get some constraints which can be related immediately, as I will show you. So we have exactly the same procedure. We take into account, in this case, the Desert and Woodard action, just to give an example, but it can be developed also for other Lagrangians. We get this kind of point like Lagrangian, but in this case, in spherical symmetry. And we get some interesting solutions related with this kind of Lagrangian. And in particular, what you get is, this is the important issue that you have to take into account. We have corrections, and this kind of corrections can be investigated from the point of view of observations. And what we have done, we in particular with this, my student, with Kostas Dialektopoulos, we developed this kind of results, and these are the situation that you get. In particular, we can fit the Keplerian orbit around around Sagittarius A, taking into account this kind of approach. And it is interesting that it seems that taking into account non-local terms seems to fit better the orbits of this kind of stars around Sagittarius A that don't taking into account non-local terms. So non-local terms seems to be constrained at astrophysical level if you have a strong field situation, but you need some constraints coming, for example, at astrophysical level. Now we are developing the same approach, but in this case we take into account the whole galactic dynamics, trying to see if it is possible to address better this point, this selection. So, conclusion. In conclusion, what you can see, you can reproduce, in some sense, both ultraviolet and infrared cosmic evolutions if you take into account non-locality. Okay? It is possible, in particular, from the mathematical tool, which can be taken into account in terms of the so-called nether symmetry approach. Why it is interesting? Because it allows to select a physically relevant cosmological model. It is relevant because he allows you to derive exact cosmological solution, and it is interesting because it allows you to constrain solutions by means of experimental observation. What are the perspectives? From a theoretical perspective, you see that it is interesting to take, we have to search some approximate cosmological solutions capable of mapping the whole Hubble flow also at high redshift. In some sense, we need the cosmography for this kind of approach. You need to study in details the renormalizability and the unitarity of this, and then we would like to see if they are related and how they are related with this nether symmetry. From an experimental perspective, what you need? You need to take into account more data and try to see if this kind of data can fit better non-local terms. In particular, there is, in this paper, we started this program. And furthermore, and this is the main demanding task, we would like to see if it is possible to constrain this kind of theories also at astrophysical scale in particular, or for example, in terms of the gravitational multi-messenger approach. Thank you so much for your attention.
Okay, thank you very much, Salvatore. So there is time for, I think, one question. So okay. Please, you can raise your hand. Oh,
okay, there is Alfredo.
Alfredo, please, you can ask.
There is Alfredo.
Hello, can you hear me?
Oh, yes, very well.
Ciao, Salvatore.
Ciao, Alfredo.
Oh, very nice talk. Thanks a lot. So, my question is quite general. That's why I waited a little bit for some more technical ones, more technical question. It's about the role of torsion. I had the same question similar question for Giovanni this morning.
Okay.
And now, this is, let me say, you are probing various models and seeing which one, which criterion, why telluric parallel gravity would be better than theories with no torsion. Do you have a criterion for looking for torsion?
Yes. The criterion.
Okay,
yes, there is a lot of work on this. I try to show you my. Okay. So these are some motivation in which you can consider, for example, torsion. So the motivation are essentially, I don't know why. Okay. Okay. So in some sense, what you need is the fact that if you take into account this torsional approach, what you are saying? You are saying that you don't need that the geodesic structure from one side and the metric and then the causal structure are strictly related to each other. This allows you to extend your dynamics and taking into account affinities instead of geodesics. Why this could be interesting? It could be interesting because you don't need, for example, strictly the equivalence principle. And then if you can relax this, you can say that, for example, equivalence principle needs that you need locality. From the other side, if you don't need the equivalence principle, you can relax this hypothesis and then you can go toward the quantum gravity in a very straightforward way. This is one of the motivation. Another motivation in this sense is related with the fact that you can take into account a sort of gauge theory in which you consider the translational group. And then, in this case, you can really deal with gravity under the standard of any other gauge theory. However,
the Ashtaker approach, like
yes, exactly. In some sense, it is really related with the Ashtaker approach. It is more related with the so-called Poincaré gravity. In the Poincaré gravity,
Wigner has papers on that on the 3 dimensions, right?
Exactly. In this case, you deal with gravity, taking into account. So, in this sense, this kind of teleparallel gravity could allow you to deal with gravity under the standard of the other gauge theories. And then people just saying that because this kind of gravity is in some sense related with general relativity, because you can recover general relativity directly, but it can give rise, you can relax the very, very demanding starting principle of general relativity. And then people is just trying to investigate this. Furthermore, you are not related with the Levi-Civita connection, but you are considering this Weissenbach connection. The Weissenbach connection could be, in some sense, not so strict like in the Levi-Civita, because in Levi-Civita, you are fixing the metric and you are fixing the affinities and the connection. In
and
the
torsion must be zero.
Exactly. Exactly. While in Weissenbach, you are not doing this. So in some sense, you are in some sense more degrees of freedom that you can play with, and starting from this, you could get some nice effectivities. However, there is at the moment no final probe from one side or the other side which are saying you this is the correct picture. There is a big debate on this. If you need a curvature picture, a torsion picture, or a non-metricity picture. There is also another approach which is non-metricity. So only God knows what is the true theories of gravity.
And if I may can we now go into the discussion or just?
Yeah, I would say let's move to the general discussion.
We can
so
because
we can
okay.
Because then the question is. You said that you recover Einstein general relativity at some point, then you do have torsion zero. So you have it as an equation of motion.
This is a very subtle point, because you recover standard general relativity when you are considering a boundary term, in a sense that as soon as you are taking into account this boundary term, like you can see here, this boundary term, in some sense, allows you to switch from torsion to curvature. And then it seems that the curvature is related with this boundary, in a sense that the boundary gives you the possibility to recover exactly the same theory. It is interesting.
It's like extrinsic curvature. It's like
exactly. It is interesting this point that at the level of field equations, if you take into account torsion or if you take into account curvature in terms of field equation, in terms of the Euler-Lagrange equation, they're exactly the same. But in terms of action is not the same, because, for example, if you take into account F over gravity, or if you take into account Ft gravity, you see that Ft gravity remains of second order, while F over gravity, in metric picture, remains is of fourth order. So in some sense, it seems that torsion can give you, can represent better the dynamics according to this picture. However, some people is saying that you have geodesic structure, you can investigate a geodesic structure, and there is no final claim that you can violate the equivalence principle at fundamental scale. So, according to this, you need to consider both theory. However, the debate is very rich in this. For example, there are several black hole solutions in teleparallel gravity. There are several cosmological solutions. So there is a very good discussion according to this. So the final discussion, Alfredo, is what is the real picture of gravity? I don't know.
Of course. No, it is quite interesting as a general story, of course. But quite sort of recently, again with Pablo, who's in the audience here, we discovered that we can indeed have some torsion, even in this very simple situation of graphene. Wow. We have to do some exotic thing, but it's something not so exotic as well. Well, we may have torsion.
Yeah, but this is interesting because graphene means that you have some defects. Having defects, you have torsion.
It's exactly in the lines of what you said.
Exactly.
Meaning, the idea is to essentially have a Stecker kind of thing or Witten kind of thing in 3 dimensions, where you have the gauge field associated to local Lorentz is the connection, the one associated to the translation, the field binds, and the field strengths are curvature on the side and torsion on the other side.
Exactly. But this is really natural, because what you are saying is that, for example, in graphene you have defects. The defects means some characteristic length. When you have characteristic length, if you are producing a sort of parallel transport, you cannot close the path. According to this, it is a feature which could characterize your structure from a dynamical point of view. So I agree completely with you. It is a very natural way in order to see. Very likely torsion could be.
Guys, just 1 second.
It
would be nice if we start, let's say, the proper discussion, because it's becoming more like a discussion focused on this last talk. So maybe we can just maybe stop the sharing and start the discussion with all the speakers.
Yeah, but we cited Nick and Giovanni. And
actually,
they can come in on torsion anytime.
No, actually, before moving to new questions and more general discussion, I would like just to go back to some pending questions that there were during the talks. So there was a question by Lorenzo Maccone to Giovanni, but I think that Lorenzo left. If I'm not wrong, let me check. Yeah, he left. Then there was a question from Alfredo to Giovanni. Maybe you can ask now the question, Alfredo.
Yeah, it was essentially on torsion, Giovanni, because you were describing these beautiful experiments on the curvature-induced effects. Since I have torsion in mind lately, I was just wondering whether you do have anything in your pipeline on torsion. And listening then to Nick and then to Salvatore, I think that there is stuff to look at.
Look, this is a very good point, and it's something else that I have in my drawer, in el cassetto, as we say, for some time. For the moment, it took, as a phenomenologist, quite some courage to allow for these effects being triggered by curvature and facing this double price to pay, which then turned out to be, now that worked, actually, for example, it could be very interesting. I haven't seen it, but I'm sure the zoo of quantum space-time pictures is rich enough. It would be good to have a toy model where torsion actually triggers.
I have it.
Oh, that's a precious reference for me. It doesn't have to be. This I didn't put on. I'm now seeing my slides, but I'm not the one.
I think you should share, no? For.
Oh yeah, no, but I don't need them. Funny that they came up without me. So please, also in private, I hope you have. I had your email at some point. Maybe you have mine, or through the organizers.
Yeah, we do have some
it
content.
Would be good. It would be good to have some reference. Then, in my view, they're always toy models. I mean, it's not so important. The motivations part, I read, but the important thing is for phenomenology to have toy models where you start getting a feeling of how the mechanism can work. But surely, I think the result I discussed should encourage a broader range of phenomenology. Again, with torsion, you might have the same concern, that perhaps torsion is already perhaps a small effect in the context where you can do good measurements, and then the Planck scale effects are also small. But I think after the lesson I learned toward the end of last year, I realized that we need to do the calculations. So yes, I have it in my agenda, and I'll be happy for any suggestion of models from various parts that give me a feeling of what's out there, what are the typical features we could look for in phenomenology.
You mean phenomenology of torsion, Giovanni?
Well, in my case, I would be interested in scenarios where, you know, what has been discovered that I mentioned in my talk is that in quantum gravity, there are some classes of quantum gravity effects which require macroscopic curvature as a seed. It's not so much as, you know, And
Yeah.
I like the model. That's what I wanted to say. Like the model I'm presenting. I have torsion because of an action field. Which, let me intervene here because I don't have to wait because that question was actually to Iorio, if you don't mind. So can I say something here?
Please.
Yes, please.
Before we
discussion
go
time.
because that was that was
So
because
free discussion. Everyone, it's
free discussion.
Salvatore
Everyone
has removed his
all together.
all together, like Mediterranean.
all together.
No, Salvatore has removed his. Can you put back Salvatore's last comment? That's what I wanted to intervene, but earlier.
What you mean my
your last one with the d mu t mu when you put the equation of motion d mu t mu. In any case, I can say it in words, but you wrote for the teleparallel gravity. I think was the one that. But in any case, what I wanted to say is the following, answering also Giovanni's point. And Alfredo's. We have a torsion which is due to an action field. It's a totally antisymmetric torsion.
You needed this?
Yeah, this one, absolutely.
Okay.
Perfect. Okay. So you see, this T mu in my case is epsilon mu neuro sigma, eta neuro sigma. So, okay. And the d mu is the Bianchi identity, which is 0 if you don't have anomalies, but it is the anomaly term, RRT.
Perfect. Yes.
That's what I wanted to say. And for Giovanni, is precisely, which that's why he asked me the question, in fact, during my talk, precisely this model has an action field as a torsion. You may not think it is a torsion, but it can be absorbed in a generalized curvature, and it behaves like a torsion, but a totally antisymmetric torsion. Salvatore was talking about more general torsions, not only totally antisymmetric.
Because unique, you have a field coming from strings, right?
I have a field coming from the gravitational.
This B mu nu, you call it.
Is this B mu nu, which is the spin one.
And then it goes into the connection.
And that goes to the connection.
It enriches the connection.
Because its field strength, the curl of B is the torsion. The curl of B or the modified, if you have anomalies, this Chern-Simons term.
And that's what okay. Mm-hmm.
And that is why I ask you in graphene.
So it's dynamical in the sense that it's projected from dynamics up above.
Absolutely. Dynamics up above. Of course, in graphene, as correctly Salvatore said, if you have defects, you would expect this. Of course, you would not expect it in the spectrum. You would expect it more like a torsion rather than an action field. But you may have a pseudoscalar excitation in graphene. And in that case, you have exactly my type of torsion. But that I don't know. That's what I wanted to ask you.
Nick, according to this, I have a question for you. You can consider this as gravitational anomalies.
Yes.
Exactly this.
Exactly
so this is extremely important.
Because you see, this is the curl. Okay, in my case, T mu is epsilon mu neuro sigma, H neuro sigma. The curl of B. So when you put the d mu, T mu, that would be the Bianchi identity because the H would be, so you have d mu, and then it would be 0. But if you modify it with the way I said, if you modify the curl of B, the H, the torsion, curl of B plus the Chern-Simons, you get the anomalies. You get exactly the gravitational anomaly. So this is my modified cotton tensor, if you like, when you go back to, and since you mentioned the boundary, because the torsion couples to bound, the anomalies coupled to actions, if the action is a constant, it's only if you have a boundary term that plays a role. Otherwise, it doesn't.
And that's why you have Chern-Simons, because
that's why I have the Chern-Simons.
That's why, yeah.
So it's interesting that to say. Sorry, I interviewed because I wanted to ask. So I'm sorry. That's what I felt.
That's discussion. That's good.
No, Nick. The point is that I like a lot is that this kind of anomalies can give for free the dark side. This is very interesting. So people, not us, but people are searching for new particle, strange particle.
There you are.
And at the end of the day, they haven't.
And also your non-localities, precisely. It may be a dynamical thing. That's what I'm saying. You don't have inflation. You don't have an inflaton field. It's due to the dynamics. That's precisely. I mean, who knows? As you said, we don't know whether it's correct. Who knows what is correct? But it's geometrical in origin. That's what I like. It's geometrical in origin.
But you had a question for me, Nick, at some point?
This one, how you could have a pseudoscalar excitation like my action in your graphene, or it may be just the torsion due to the defect. But of course, that's
what we do have at this time is. A coupling of that spinner, this massless object, which is a quasi-particle, it can couple non-trivially and non-identically zero to the fully antisymmetric part of the torsion.
And that is exactly my action.
That we can
That
do.
is exactly my action. Perfect.
Yeah.
Perfect.
Yeah.
Then you have the analog. Then you have the analog. Very good.
Yeah. What we
because
don't
that's exactly what the action does.
What we do not have yet is the gravitation. I have Salvatore on this side of the screen, and you.
Well, yeah, of course. That's exactly my question. What's the gravitational part?
We don't have the gravity theory yet. Meaning that there we have some ideas, but still we haven't went into proposing let me see, a geometry gravity theory. You know, in the spirit of the work of Gaetano, Volovic, Hagen, Kleiner, these people have put forward gravity geometry description of elasticity.
Very good.
And that's the same program of Salvatore, Ashtekar, and that's it. But then each time you connect a gauge field to a generator, you go one step down, which you don't do in usual theories, because you identify a defect. Okay, you do translations, field binds, you do rotation, spin connection, and that's it in standard gravity. But here you also identify the dislocation defect, the disclination defect, and that's how you build up your thing. This we still don't have. We have clues, but still we have a.
But I guess through your metrics, you might get the.
What we do have is this coupling, and this is something new because
people
have thought about that. This Madrid group, Boss Mediano, all the people, they have thought about that, and they have found a geometric obstacle given to the 2 dimensions. Essentially, you need a 3rd dimension to wind around.
Very good. And then your chiral matter, then you have a graphene, maybe do exactly the scenario I was saying, cancelling the anomalies.
And what we have our way out, which that's why we finally found a sort of solution, is that we are planar with the object, but we have time.
Yeah.
3rd dimension. So you have to think of winding around time, and this you can do with the particle antiparticle, going around, which makes a sort of a time loop.
Very good.
Okay, this is roughly the idea. So we do end up with some non-zero coupling.
Very good. Very good.
Yeah.
Alfredo, I have a very short question.
Sorry, just one second. There was during the talk of Alfredo, there was a question pending from Gaetano Luciano.
Sorry,
Salvatore, go on.
No, it's very straightforward. What is the analog in the graphene representation of an eventual Vierbein? Is it possible to construct a sort of affine representation in your analog picture?
So the first thing is that you have to kill fear, because we are dry here.
Yes, okay, dry bind. Okay.
That's a joke.
Okay.
But then, I mean, we do have a metric there. So I think you can do the usual story with the metric and try to split it non-univocally into dry binds here and there. So you can do everything. The way to do it is again, I mean, I would refer to this paper by these people, especially Misha Katanaev, the guy that comes to Corfu very often. He has this paper where he builds up step by step through deformation of the membrane a metric tensor, and it shows that if you deform the object elastically, then you let it go and the metric is gone. This corresponds to building up a metric whose geometric tensor are 0. The Riemann tensor, everything is 0. So it's just trivial. If you really want to have something that lasts, you have to make a non-elastic, what they call a plastic deformation. Plastic means defects. If you actually do that, then so the idea there is to link the field binds, or dry binds, actually we said, to this, I always got it, this disclination defect, okay? I mean, the ones with the Burger vector, the non-zero Burger vector.
The Burger vector.
The Burger vector. Because the Burger vector, the Burger vector is the integral of the torsion over the loop, right? And from that, you can extract.
So you can construct the teleparallel analog.
Precisely.
Yes, exactly.
The more natural thing that is teleparallel. Because you have both kinds of defects. You have it.
Yeah. There is Gaetano. Sorry.
Gaetano, please, you can ask now.
Thank you, Luca. Thanks to all the speakers for their very nice talk. My question is for Alfredo. Thanks for the very nice introduction about Feynman.
Thank you.
And my question is, my curiosity is, can you explain a bit more the deepest reason behind this analogy between two completely different worlds? I mean, why do we expect this analogy beyond mathematical issues, beyond mathematical inequalities?
I cannot see from the audience whether Radin Dardashti is around. Radin is a brilliant philosopher of science with whom I've been chatting a little bit. These people do brilliant things, and he will probably use the proper words. So you have to be a little patient with me if I don't use the precise technical words. The idea, though, comes from Feynman. And when the ideas come from Feynman, they're very straight. You know, this guy had this beautiful thing. I keep watching his videos all the time on anything. He says, I will tell things in his words. Okay, so that's the thing. I also try to give you pictures of that. You need a common structure to all the guys, all the theories, all the system you want to link. Otherwise, it's just a coincidence of a fortuitous coincidence of equations. I mean, when people say same equation, same solution, you know, it's just a shortcut. It's just a motto. I don't have anything against that. Okay, it's a good statement, but it's very superficial. Because what if you are probing electrostatics with I don't know the drums? Huh? You are probing a known system with another known system. They are both known. You have access to both of them. No problem. So you may get in situation where you don't want to get into very high electric fields. Okay, I do the drums, or vice versa. You don't know, so you can choose. But here you don't really have any deep reason. Okay, you don't learn too much because you know both theories very well.
Yeah, sure.
Now, if I am talking here in this audience, it's because you want to probe quantum gravity. Now, no one knows quantum gravity. So here I'm doing something different. I'm pushing, I'm stepping up the level because I want to say to you, look, with analogs, you may be able to probe the unknown using a known system, a system you have in your lab. The only way to do that is that you're sure that both systems refer to the same underlying structure. Otherwise you cannot do that, okay? So it's only, if you take the view that, the Jackson view, that gravity is a fluidodynamic phenomenon, then you can use fluidodynamics. But you have to know, you have to commit yourself on the theory and say, oh, okay, I'm chasing fluidodynamical version of these, okay? And there are examples out there. There is actually, I've been doing my PhD with the late Lachlan O'Rafferty there in Ireland, and his last published paper, his second last was with me. The last was with Schroeder Villacota, who's going to contribute to that issue of universe. And they had found there a duality transformation between an explosion, supernova explosion, out there in the sky, let me say, okay, and the implosion of a plasma under some laser pressure, let me say. They found a precise duality. So they had a rule there on how to map things happening here into things happening there. And what is the common structure? The Euler equation of hydrodynamics. So once you have this common structure, then you know that if you do things in this system, it's corresponding to this system. And if you don't know what's happening here, okay, you can use system A and the results of system A will go to tell you what happens to system B. Okay, that's how far I can get into philosophy. I don't know if I answered at least a little bit.
Yes, thank you. No, but my question is, why these systems should be, I mean, I don't know if there is an answer, why these systems should be somehow equal, should be described by the same physics?
It's a fantastic question because it allows me to say that this doesn't happen all the time. And there are people out there who claim that this is happening all the time who are not doing a good job to analogs. This is happening. That's what I tried to say in the beginning. If you have a map, a duality, a symmetry, something, you show it to me, and you are explaining to me the criterion, it's only then that you can say, I do things in system A, they correspond to system B. Otherwise, everything is like everything else, and it don't get anywhere. Okay? So my collaborators here will know that we take a long time before we publish any paper, precisely because we want to see up to which point we can tell things, beyond that point we cannot tell, and what is this common structure that is so and this is an open issue as far as I know. Again, if Radin is in the audience, he may intervene. I don't have a unique answer for that. I have an answer case by case. I can tell you case by relativistic flat space. I have seen the Weiss symmetry. That's because O'Rafferty long ago taught me about that. Say, look, this is an interesting thing with no physical application. I look into graphene. I found it. That's it. So I can have a criterion. I can tell you, how to relate these various metrics. But this is really ad hoc. There is no, let me say, something satisfactory still on the general. Say you all the so some criterion which holds all the time.
Alfredo, sorry, I would like just to, since guys, in 20 minutes we started the second session, but we still have 3 questions or comments. I would like to give the words to Luca, Ali, and George. So 3-4 minutes each, and then we take 2 minutes break and we start the second session.
I have to leave, unfortunately. So I have to teach. So I suppose there are no questions for me, if you don't mind.
Yeah, I don't know if I don't know if
otherwise later on in the evening or.
Yeah, okay.
I have exactly the same issue by Nick. I have to go. Sorry. Okay. I will prefer to stay with you.
Me too. Okay, me too. By far, but unfortunately.
I have not lecture. I have a concorso. It's worse.
It's worse. Mine is a course.
Good luck, Salvatore.
Good luck. Guys. Thank you so much. We will connect later.
Ciao.
Ciao, ciao.
Luca, please.
I want just to do a comment or remark. I think it's related to what also Luciano wanted to say before, because it's related to the Luciano's comment to Alfredo's talk. Actually, can you hear me?
Well,
yes, I can.
Okay, good. I always check. No, it's interesting the comment, because it's also related to what Giovanni said at the first during the his talk, first talk of the day. That it's known that the presence of cosmological constant could be also a consequence of Q deformation. In that case, Giovanni mentioned the paper of Bianchi and Rovelli was SU2Q group. So the formation of rotation group from SU2 to SU2Q. And but could be also SU11Q or other Q deformation, I think. And this clearly it could be also implied to the formation of commutation relation, or Q deformation of commutation relations. And so I think that's a way to implement what Luciano was saying. For example, natural way could be to do something like a Q deformation of graphene tight bonding model, for example. That could be very strictly related to what Luciano was saying. And then you can find also some extended uncertainty relation or something like that.
In that case, probably you would obtain the deformation of the uncertainty relation as a byproduct and not as put by hand, in a sense. If you start from this, I guess. That's what
natural, but you naturally gain also cosmological constant. It's
yes,
the same. Or you start from cosmological constant, then you get probably this extended uncertainty relation. But if you start from modified uncertainty relation, and this is known since long time in the quantum loop gravity community, for example, you get cosmological constant. So I think this is a way could be implemented in this tight bonding model, for example.
Yes.
Okay, next paper, Luke.
George, please. I need to unmute, please.
Hola, Jorge.
Hola, Alfredo. Thank you very much for a very nice talk. I have a very naive question. When you write down the cosmological constant as 1 over L square, or minus 1 over L square, this L in general relativity remains, it's related to the radius of the universe. So it's an infrared cutoff. In the case that you're discussing, the L is the space, the lattice spacing. So it's some sort of ultraviolet cutoff because you cannot go smaller than that. Is the fact that you can connect it to things related to the conformal symmetry that you have in your system?
It is, well, conformal symmetry, yeah, that's a very good question, of course. On first part of the question, the answer is phenomenological. That, as perhaps we discussed that at some point, but you see, the thing is that you want this the structure to hit the event horizon. So the boundary there wants to go as close as possible to the event horizon. So you have to go in that limit. And the throat there of this pseudosphere, it cannot be smaller than L. Actually, L is even too small. It should be order of L. I don't know in the practical case it would be 3, 4, 10, but something of that order. So this is how we end up with that ansatz, let me say, about the. It's very natural, okay, on the graphene side, because there you do have a lattice spacing. So and if you try to undo that, you just break the object. So you have a natural scale in that sense. On the other hand, about conformal symmetry is very important there. It's very important there. Indeed, how can I say, what I was showing to you is something conformal to your black hole, only conformal to that. It's not, so if you shape the graphene in that form, then the line element there is a conformal factor times the BTZ conformal factor. So now you have to decide which one is the physical space. Okay, so if the physical space is a BTZ, then all you said is it applies exactly. But if the physical space is the other, then you have to consider everything together. So in that case, you should redefine your constants. Okay, so I don't know if this answers your question, because there are, for instance, let me say, for one thing I remember now by heart is another case with another pseudosphere, which is the elliptic pseudosphere. In the elliptic pseudosphere case, the space-time there is conformal to de Sitter. And de Sitter is positive curvature. And you say, how can it be? You have negative curvature in the pseudo. It is a pseudosphere. Well, it can be because you are split the things in two through the conformal factor. So on one hand, and the meaning of quantities change depending on which side you're talking. And you can keep going. You can keep going, of course. You can use another conformal transformation there. They're all related until the one that brings you where you find it to be more convenient for your description.
Thank you very much. Thanks.
Thank you.
Yeah, so since we are still in time, and I thought that we would have finished just at let's say 3:15. I will take the advantages from this silence to ask to say something maybe. So in this session we heard a lot about quantum gravity phenomenology, I would say. Okay, and so what I'm going to say, I think, is especially related to Giovanni's talk. Okay, so in that case, for instance, we were basing let's say some possible quantum test of quantum gravity by looking at this modified special relation. Okay, so my question or comment, I don't know if it's a question or comment, is let's suppose we really confirm that we see some modified special relation. Does this really imply that we are seeing quantum gravity? Because, for instance, if I think about quantum gravity phenomenology, what I would like to have is some kind of test which would tell us about some intrinsic quantum nature of gravity. For instance, yesterday, we saw some very nice proposal to test quantum gravity, where the speaker were telling us about superposition of gravitational fields. So in that case, it's some kind of really intrinsic feature which is purely quantum and does not depend on the quantum gravity approach that you're using. It's just low energy, basically quantized gravity, which all the quantum gravity approach should recover. So when we speak about, like, for instance, the special relation, can we really say 100% that we are seeing quantum gravity? I mean, it could be something else maybe, which is still non-gravitational quantum feature. Okay, so this is mainly to Giovanni, but it's more open, let's say, common question.
I can start a discussion on this if you like. I think what you said is always true. I mean, even if what we see is a signal in some detector, in a telescope, in a calorimeter, and that signal we attribute to a certain mechanism. So it's always, of course, to a different extent in different branches of phenomenology, but it's always the case that you first see the first manifestation of some new physics, and you have a first tentative interpretation, which in the case of dispersion relations at the present time, because of the bulk of work which has been done, might be quantum gravity. And then, however, you need but for every, I mean, to a different extent, but there is no smoking gun. That is a dream of theorists. The reality of data is that you find evidence of a signal, of an anomaly, of an experimental fact that doesn't square with what we already know, and that's a fact, and that's where knowledge is brought forward. Then we try to understand where it comes from, and we need other measurements, and we need theory works. So I think that's not very different from the dispersion relation and other fields. One peculiarity of quantum gravity, which is unlike most other fields, is that we think, and that too should be scrutinized experimentally, but we think we have a rough idea of the characteristic scale. So if you find a modified dispersion relation and the scale of the effects is set by a scale which is somewhere in the neighborhood of the Planck length, you would be encouraged to think that it's quantum gravity, but you still need other effects. It could be, I have seen papers actually after the interest from the quantum gravity side, there are papers on some types of dark matter that could produce in vacuum dispersion. And of course, these models do not have the Planck scale as a characteristic scale, but if you adjust the density and the properties of the dark matter, it might happen to be just of that order. So on one end, my philosophical position is that knowledge goes forward when we discover a new phenomenon in nature. And that's really what I would like to do. I'm not really looking for, quantum gravity is where I suppose I have some ideas, but whatever comes, that is.
No, I totally agree with that. I mean, for sure, it's new physics anyway, but in principle, it could be just classical gravity.
So then I think it's more, it's underestimated how now you will follow the G-2 debate. Okay, there is this excitement, and what is that? Oh wow, there will be 1,000 papers, rightly so. So I think but let's get there. I mean, if we get there, that would be splendid. But I think it's always true. Your question is well posed, and you look for an effect with some motivation. You might find the effect, and that effect could come from somewhere else. I only underline that in quantum gravity, the sad part and the happy part both are the Planck scale, if we are right. And I repeat, we cannot be sure. But if it's true that the Planck scale is somewhat relevant, then there will be an extra help in trying to attribute the effect to quantum gravity if we find that scale. But it could go, I repeat, either way. You can find that it is Planck scale, but then maybe some dark matter or some other weird stuff happens to conspire to give Planck scale. And on reverse, as you saw from Nick's talk and actually my data, Actually, if you have you can find a scale which is a few orders of magnitude below the Planck scale, and you think, oh wow, that's too low to be quantum gravity. And then, but I don't think it's so peculiar of dispersion relation. And I guess for the youngest member of the meeting, following the G-2 debate, which will start now, will be educational from that point of view. I mean, there will be all sorts of hypotheses, and ultimately the anomaly might go away and all that.
Thanks. Okay, it would be nice to discuss more on this, but we have 5 minutes left before the beginning of the second session. So I think this is the right moment maybe to say, let's have a break of 5 minutes and
lunch.
Lunch maybe, I don't know what, but
at this latitude here.
Yeah. And yeah, we start again in 5 minutes at 3:20 Central European Time, summer Central European Time. Okay. So see you soon.
Ciao.
Summertime.
Luca.
Oui.
Io vado un attimo, lascio il ritorno tra poco, perché devo tornare a casa.
L'ho detto, ma fa partire Luciano la registrazione.
Ah, vabbè. Yeah.
Ok, ci manca il secondo speaker.
Ok. See you soon.
Bye bye.
In 10 minutes.
Luca, do you stay here?
Yes.
Io.
Luca Smaldone. No, Luca Smaldone.
Yes. Sono in chairman.
Okay. I go for lunch, just a few minutes and I come back.
Tranquillo.
Victor, do you need to...
Lascia acceso magari, così non ti devo rifare poste, cose spegne.
Sure. Sì.
Yeah.
Very good, Victor.
Nice. I will pick something.
Don't spoil, Victor, don't spoil.
You can also leave it on screen, actually. Because
I will leave it on screen.
Yeah, but from the first line. So
show us the conclusion.
It will be a talk of 2 minutes.
That's better. We gain some time.
Okay, I'll pick something to drink. I come out in 1 minute.
No, parla Victor, che ancora non c'è lo speaker. Dopo di te. Mancano 2 minuti. È il segnale orario.
Ok, sono tornato.
Ok, partiamo tra un minuto.
Sì, va bene.
Luciano, ci sei?
Sempre vigile.
Ok. Mica riesci a vedere se c'è il nostro secondo speaker, che non lo trovo?
Ho notato, stavo cercando pure io, mi sembra non ancora, quindi in realtà, siccome c'è il terzo...
Al più nel caso scambiamo.
Sì, no, a parte vero, potremmo anche chiedere, perché se non erro collabora, no?
O posso io parlare per un'ora?
Se vuoi.
No, no, grazie.
E già Cost, tra l'altro, si può aprire il microfono.
Okay, I guess that we can ask. Barbara, are you here?
I'm here.
Okay. So, do you have any news about Achim? Because we didn't see him here. He should be.
Oh, he should be here. He should be here.
Okay. Well, in the worst case, actually, we can also switch your talk with him.
Okay, but I don't think
just in case. Okay. No, just to know that. Thank you.
Okay.
Okay, quindi
I think we can start.
Probably we can wait just another minute, so to let other people enter, probably. Just one more minute.
I don't think many people will enter more in this moment.
Oh, you'll never know. So
just another minute and we start.
Yeah.
Okay.
I guess
I think we
you can.
Start.
Okay.
Start.
By the way, Barbara just wrote in the chat and said that Agim will be here in 3 minutes.
Okay. I will check.
Okay, thank you for the info, Barbara.
Thank you very much. Okay. So I think that we can start with the first talk of this second session. And the speaker is Victor Bittencourt from Max Planck Institute Lab of Light Science, right? Erlangen. So Victor starts.
Okay, so first of all, I would of course like to thank the organizers of this conference. It's been such nice putting like everyone together with like different expertise from different areas, and I'm no different. So today, what I want to talk to you is about basically frame transformations and quantum correlation. So this is the title that I gave to my talk. It's basically how frame transformations do affect quantum correlations shared between degrees of freedoms of particles, for example, between spins. And this is, of course, a whole area of relativistic quantum information theory. But here I will focus more on some fundamental aspects, the formulation of the problem, and I will try my best in this half an hour to give like a brief review of the subject. And I will cover from the basic setup to some gravity effects that you can get by just considering frame transformations. Okay, so I will jump right into what my framework is and what I'm interested in here in this talk. I'm considering two subsystems, if you want, A and B. They can be like spin of particle A, spin of particle B. They can be momentum of a particle and the spin of the same particle. It doesn't matter much. And what I want to understand is what happens when a Lorentz boost is performed. So then another inertial observer see this system from its perspective. What happens to the quantum correlations shared between the subsystems, right? And this is important for some applications, of course, in communication, in metrology. I won't enter that much in those matters, but there is this review that is quite old by Perez Interno, but it still holds very well. And the key concept here is that, okay, so you have these two things, but what are those two things? What are A and B? What encodes the correlations? Are they spins? Are they momentum? What they are? How do I describe these states from like a relativistic quantum mechanics point of view? How they transform under frame transformations? This, of course, comes down to the representations of the Lorentz group and of the Poincare group. So we all know that, for example, particle states, they belong to irreducible representations of the Poincare group. So this will be the first thing that I will cover in my talk. Basically just a fast review of the irreducible representations of the Lorentz and the Poincare group, and why do we use them to understand how quantum correlations change, or let me say how entanglement changes when a frame transformation is performed. And this has many other consequences that I will comment, and many other questions on the vicinity of this problem that are very interesting. So let's go and just then see our irreducible representations of the Lorentz group. So, and here in this whole talk, when I talk about the Lorentz group, I am talking about the proper Lorentz group, okay? So we get, of course, the representations of the Lorentz group by looking to the generators of the set of transformations, which they are given by these m mu nodes here in the coordinate representation, which is the representation that defines the Lorentz transformations. And basically we can break these in like generators of rotations and generators of boosts, but they don't form a closed algebra. In fact, you have like to combine them to define operators that do form like a closed Lie algebra that resembles the algebra of angular momentum. And then basically you start to look like to other representations of this algebra, to other realizations of these algebras. And of course, if you have like an algebra that is the algebra of angular momentum, and you have like basically two copies of those, you can basically label the representations of the Lorentz group by two numbers, which I call here J plus and J minus. They can be integers or half integers, of course. Then there are the simplest representations of the Lorentz group, which some people call the fundamental representations. They are the representations that is 1/2 0, which I call Xi, and 0 1/2 that I call Chi. And they are actually, in more technical terms, the spinorial representations of the Lorentz group. They are what we call the Weyl spinors. So they are basically the building block of the zoo of spinors around the world. So with them, we can construct Majorana spinors, we can construct Dirac spinors, and so on and so forth. But we know that particles, they are represented by the reducer of the Poincare group, which include translations as well. Of course, to construct the irreducible representations of the Poincare group, we need to know the irreducible representations of the Lorentz group. But the thing is that translations, so the generators of translations, which is basically four momentum, it forms an invariant subgroup of the Poincare group. So then you can use this method of induced representations to construct all the irreducible representations of the group, and then you basically classify them by the two Casimir invariants, which is the mass, is just p squared, and this W mu, which is actually the, let's say, the modulus of the Pauli-Lubansky 4 vector. The mass is fine, everybody understand what mass is. So Pauli-Lubansky, if you look to give an interpretation to it, there is a way that is, okay, let's just look to massive particles in the rest frame of the particle. What happens with this guy here? What you see is that basically the vector part of the 4 vector is proportional to the generators of rotations, to angular momentum, which is the generators of the little group. So that's why we associated this W to actually spin. So if you are in the rest frame of the particle, the only thing it has in terms of angular momentum is spin. So then there it is, the recipe to construct the irreducible representations of the Poincare group. So for a given 4 momentum, you know that the independent components of the Pauli-Lubansky vector form the algebra. This is the algebra of the little group of P mu. I will introduce a bit more detailed little group soon. Then for every irreducible representation of this little group, we can derive an irreducible representation of the Poincare group by successive applications of Lorentz transformations. And finally, of course, as I already said, so the irreducible representations of the Poincare group, they are characterized by the eigenvalues of the Casimir operators of the group. So far, so good. This is textbook knowledge, just to give a refresh on your minds. Then now we can construct these particle states. So now we go and we use these irreducible representations to construct the states that will somehow encode the correlations that we want to study. So for massive particles, we just say that the state belongs to one of the irreducible representations of the Poincare group associated to a spin. It has a 4 momentum. And then the question now is, okay, so we know that under Lorentz transformations or under Poincare transformations, this state will transform according, of course, to a unitary operator, so a unitary representation of the group. Then what is this U of lambda here? So what represents in the space of these states the action of a frame transformation? To answer that, we consider like this, let's say, chain of successful transformations. Of course, here we are starting from the rest frame of the particle. So this actually is only valid for massive particles, but for photons, you can kind of construct some similar arguments. I won't do it here. But basically the idea is that if you look on how this guy goes to this, is just a representation of a Lorentz boost. So you go from the rest frame to the frame where this thing is moving with momentum P. Then you do this Lorentz transformation that you want to know, right? And basically by just using the properties of the Lorentz group, you of course write this guy here in terms of the state in the rest frame. And this is actually the trick, because you again can use the properties of the Lorentz group to decompose this transformation here in terms of something that is a representation of just the transformation of the momentum from the rest frame momentum, with something that is a representation of this thing here. So what this thing does, it picks K, my 4 vector in the rest frame, it transforms into P, right? Then it do this Lorentz transformation, lambda, but then it do the inverse thing and bring this lambda P back to the rest frame momentum. So this can only be a rotation. And this is what is called the Wigner rotation. And actually the set of all Wigner rotations for a given momentum form the so-called little group. It's the Wigner little group. And why is this a powerful tool for us? I mean, it's a powerful tool, but it's more like this is how things works, but it turns out that is actually a very powerful tool, because when we look on how then a given state transforms under a frame transformation to another inertial frame, this transformation law basically tells me that my P and sigma, so sigma here denotes the spin part of this state here, and the definition of the spin part can be a bit tricky. It basically transforms into the momentum in this other reference frame, but then the spin part is just rotated. So this D of W here is just the representation of this Wigner rotation in the space of these spins. So I didn't specify here if sigma is a half or whatever. So this is general. For spin 1/2, of course, you can show that the little group is given in terms of the SL to C. And then you can just write it like straight away. Okay, I know that this will be the form of this D of omega acting on the spin part of a wave function. Here for now, I'm being a bit sloppy with notation and how I say things, but the physics is quite that. And this omega here, this is what we call the Wigner rotation. So what happens then is that when you do a frame transformation in a particle state, so a particle state here understood as something belonging to an irreducible representation of the Poincare group, you basically change the momentum to the momentum in this transformed frame, and you do a rotation on the spin. Now, the interesting thing is that this rotation here, this rotation angle, it actually depends on the momentum of the particle and on the transformation. So it's a momentum-dependent rotation. And this is what have some key implications when we take a look on how entanglement transforms under Lorentz transformations, for example. Okay, actually, these Wigner rotations, they have a physical interpretation, very nice, given by Pablo Saldanha in this paper in 2012. And basically his argument is that, okay, so to understand physically what this Wigner rotation means, we just have to look on how one would prepare such state. And then he just thinks about this Stern-Gerlach apparatus. So basically your particle has like whatever polarization in the spin part, it passes through a magnetic field. You know your spin will be polarized along parallel to the direction of this magnetic field. And basically what they do is, okay, so then I can write in the rest frame. So after my particle is polarized, I go to the rest frame of the particle. Then I can basically write this state, you know, so I can denote the spin part instead of like by spin or by a superposition, I can just denote in terms of the Bloch vector describing the spin state here. And this Bloch vector will be, of course, parallel to the magnetic field, which is actually a function of the transformed electromagnetic tensor to the rest frame of the particle. Then what he argues is that, okay, so now let's look to the state in a transformed frame. And then basically what he concludes, which makes a lot of sense, is that the Bloch vector in the transformed frame is just a rotation of the Bloch vector in the not transformed frame. But then this is where the interpretation comes, right? So why then Wigner rotations happen? You can understand this as a dependence of the quantization axis that is being used to describe the spin part of the state on the momentum. And then basically the idea is that different observers, they will compute this measurement apparatus using different quantization axes. So this is what gives these Wigner rotations. And then, of course, this is also related to a very fundamental question in this whole story, that is, how then I define some measurable spin operator that doesn't have this problem. So this is an interesting question that I will I will just comment, but I will not address here. You will have some nice references for it, nevertheless. So let's see a very simple example on the framework that we are considering now. So you have in a reference frame a spin particle with spin 1/2, and somehow you manage to prepare it in this state here. So let's say its spin is pointing up in the z direction in this frame, but it is in a superposition of momentum, so in P and Q. When you do a frame transformation to another inertial frame, well, what happens is that this part of your state, the spin will be rotated by something that depends on P, but this other part will rotate by a different angle that depends on Q. So you start with a separable state and you end in a different reference frame with an entangled state. So this is like the most basic kind of effect that people start to talk about it, like in the beginning of the 2000s. And in fact, so what you conclude for all of this is that if you look to the reduced density matrix for the spin, so let's say you trace out the momentum, there is actually no covariant transformation law for the reduced spin density matrix. You transform and you get some different thing, you cannot relate then by some simple transformation law. And then there is also this question, but okay, can I define a spin density matrix by defining suitable spin observable such that I can have like something that has a transformation law? And this is, again, a question that goes a long way, but which is very interesting. So what we conclude is that, okay, Wigner rotations, they can entangle the actually spin and momentum of particles. There is another small issue here, not small, but here I just assume that I can separate the momentum from the spin parts of the state, and this is a bit delicate. But let's carry on. So when you consider two massive particles in a singlet state, for example, this bell-like state, here these halves and minus halves, they are denoting actually helicity, so it's basically the projection of the spin into the direction of the momentum. And this was actually one of the first papers on the subject, and they were already using a different spin operator, so to say, which is given by this. But what was interesting is that basically they just conclude that if you calculate like a Bell observable, the value that you get from this is dependent on like the momentum of these particles, of the rapidity of the particles. So they are basically saying, okay, the degree of violation of Bell's inequality is dependent on the reference frame in which I see these pairs. And this is again a bit, okay, thanks. And this is again a bit sketchy, right? And it will be solved in the literature. Again, when you consider two particle states, a Lorentz boost can entangle them, provided that they are like in a superposition of momentum. And you need to have entanglement between spins and momentum to generate create some spin entanglement. Okay, very nice. There are many other questions that were addressed in this framework. Some of them are here. In particular, related to this violation of Bell's inequality, there is a paper that came out recently by Bruckner. It is written wrongly, which kind of deals with that problem using a contour reference frame approach. What I did in this framework was to consider what happens when you consider superpositions of B-spinors, which are solutions of the Dirac equation. Those are a bit different than the irreducible representations of the Lorentz and the Poincaré group. They belong to a different representation of the group. And they actually carry two intrinsic degrees of freedom, which is spin and intrinsic parity. if you have like any questions regarding to this, I will be happy to answer in the discussions. The fact is that when you do a boost in such states, you have kind of a change between spin entanglement and it's kind of your entanglement that was only between the spins redistributing to the other partitions of the system, somehow like what happens in the other cases. And yeah, even with this bispinorial approach, we can reproduce results in the literature. There are connections. We can calculate what is the rotation angle that the DCT eigenstates have in terms of the Wigner rotation. So now I will take the last 8 minutes of my talk to say a couple of words about gravity effects in this context. And here, of course, what we are interested in is that, okay, so can gravity affect somehow spin correlations, or how gravity affects spin states? But then here, how I define spin states in curved spacetimes? Well, for that, you have to introduce a local inertial frame, which is defined in terms of these guys here, which are the phi-abine. And they basically do this job for you. They help you to define a local inertial frame. And basically, what you can see is that these phi-abine, of course, they are not unique, so they can be connected by these local Lorentz transformations. And we define spin 1/2 particles in this context as one particle states that furnish the spin 1/2 representation of this local Lorentz group. This is nice because then we can just pick everything that we know about the Lorentz group in flat spacetime and just use in terms of the local Lorentz transformations. So this is true, for example, for Wigner rotations. They work exactly the same. And this is also nice because if we know what is like the evolution of a given spin state, we can construct explicitly how the state will evolve by just concatenating local Lorentz transformation. So it's a kind of straightforward proof that, you know, in infinitesimal change in the momentum is actually a local Lorentz transformation. You can just put that in terms of a local Lorentz transformation. And then in order to construct like a proper time evolution over like a given path, you just concatenate these infinitesimal transformations that are given as well in terms of local Wigner rotations. So this is really nice. You basically get the idea is that you discretize your path and then you just consider like successive applications. You end up with a series that actually converges because of some properties of the group. So then basically to understand how spin states evolve in curved spacetimes from these perspectives, this is the procedure. That's fine. So you can do that, for example, for the Schwarzschild metric. I won't go into the details here. This is a paper by Ueda. But the conclusion is that when you consider the evolution of pairs, and they are like at, you know, in the origin of your proper time perfectly anti-correlated, they seem to lose this perfect anti-correlation with time. Of course, this is like an apparent effect. The transformation is unitary, you don't have anything of that, but it's because of how Wigner rotations work in these curved setups. What we did was to consider how extended theories of gravity that Salvatore Capozziello just told a lot of very nice things about them, how they are manifesting this Wigner rotation framework. I won't go into the details, but basically what we considered was like, of course, weak field fluctuations over the metric. Then we consider the same setup, an EPR source, and we look what happens with this apparent loss of perfect anticorrelation. So then we could compare to the GR case that is already known. And actually, our conclusion was that the contribution due to the extended models, for some extended models, can be decoupled from the contribution from GR. And this is a quite nice result. But furthermore, inside this contribution of the extended models, we can identify some contribution that is due to violation of the strong equivalence principle. So just to end up, we actually, we took a look on 4 models in the paper, but only two of them give contributions that are not null, with his like 4th order gravity and the goes free infinite derivative gravity. For one, you have a contribution due to the violation of the strong equivalence principle. For the other, no. Basically, you can compare these contributions to the contribution that is due to GR, and you see that they are super small. This guy here is already small, so this is a bit okay, yeah. It's a small effect anyways. But it still is something like very fundamental regarding how these quantum correlations, or they somehow are modified by these extended models of gravity. So, as my father said, just a summary of the opera. In this talk, I just wanted to give like a brief overview on how Wigner rotations and the structure of the Lorentz and Poincare group are used in the study of quantum correlations in relativistic settings. There is a lot to talk about that I didn't talk, so if you have questions, just go on. This last part can be used somehow for proposals for tests of gravity models. Of course, it's already a very small effect, so you should take that with a lot of salt. But somehow the scenario is complementary to some studies of how gravity affects wave functions. There is like a very recent paper by a group in Canada that is on arXiv, which is super good. I recommend you to go and check it. And with that, I want to give my special thanks to my collaborators, in particular Luciano and Gaetano. They were like the driving force behind this last part. Massimo Blasoni, of course, Gaetano Landias and Fabrizio Illuminati. And my long-time collaborator, Alex Bernardini from Brazil. With that, I think I just finished it on time, right? So thank you all. I'm more than happy for answer any questions now.
Perfectly on time. Yeah, we have 5 minutes for question. Okay. First question, it seems from Barbara Soda. You can unmute yourself because you're close. So.
Actually, I just used the clapping. I'm like, so.
Okay.
Thank you.
Are there? Okay, one question from Luciano.
Yeah, thank you, Victor, for your nice talk. Well, I would like to ask you something about the first part, actually, because, of course, when you analyze the interplay between direct representation and when you apply a Lorentz boost on it, basically, it's as if you're moving in the context of relativistic quantum mechanics, in a sense. But by means of this kind of reasoning and this kind of formalism, is it possible to have some even small access to the quantum field theoretical regime? Because I know that one of the difficulties in the context of quantum information is actually to extend all the considerations in the context of quantum field theory. So I don't know if this kind of analysis may be eventually generalized in that realm, and if it may also help to develop this field.
Well, so one of the best hints that you get is the treatment in terms of bispinors, because they are just the mode functions that you get from a field theory, but still they are single particle relativistic quantum mechanics. Okay. Whenever someone asks me about that, I prefer to be conservative than to talk about things I don't say. So I would say that in order to contextualize all of that in like a quantum field framework, you have to work with the quantum fields and just see how the ideas of entanglement translate to that, which is also a pretty complicated question by itself. And there is also the question when we talked about these effects on curved spacetimes. I just say that a particle is belongs to representation of the local Lorentz transformation, but I think you guys know better than me that it is hard to define a particle as a representation of a field in a curved spacetime. Right? There are some problems there.
Yeah, sure.
But I think my message to take home is that this is, for all purposes, a very effective description. Okay. Which can be useful in treating some experiments, for example. Yep.
Other questions or the raised hand? Oh, okay. There is in chat one question from Gaetano Luciano.
Thank you, Luca. Thank you, Victor, for your very interesting presentation. My question is more on the last part of your presentation, at least qualitatively. You say that, okay, with this formalism, one can try to test experimentally extended theories of gravity. Could you elaborate a bit more on this, just from the qualitative point of view?
So, of course, I won't say it's a feasible experiment, it's not, but what one would do is, okay, so you have your EPR source, it emits the pair, one guy goes to the left, the other goes to the right, they go on like a circular orbit, then you have observers at some other point. And they will basically do a Bell test, but with the direction of the measurements they will take is just simply taking into account, the frame rotation. And what they will see is that they get a degree of violation of the Bell's inequality, so they get an amount of spin correlations, if you want, that doesn't match what they expect. And this is exactly what we talked here. So in fact, you have these corrections due to the curved spacetime. And if you have if gravity is actually an extended model, you will have corrections on top of that will be very small. So it's kind of a correlation measurement on the spins. Now, a way that would be more appealing to experimentalists maybe would be to propose a test like this and to look to these type of effects with photons. But then, okay, the setup is different. Photons will not make a circular orbit and so on. But still, what might be interesting also is like to not think about exactly these effects in pure gravity. You need like very strong fields. We can also look to analogous systems, which is also a very promising thing. So how those things are translated there. What new could we explore there?
Okay, thank you, Victor.
Okay, I think we are in time, so it's good. We thank Victor again. I have curiosity, but I take for discussion session. And next talk is one of Achim Kempf. Okay, can you share the screen?
Worst case scenario. Hello, everybody. I just had a power cut here, so I'm on my phone. I'm switching on my laptop now. Please give me a minute or so.
Don't worry. We are in time.
Okay. Gosh, you see, there's some construction going on in the neighborhood, and I had a power cut for 1 second, but that killed the PC.
Well, in the meantime, just to let Achim fix everything, probably if Victor is still here, you can do the question, Luca, so that we can already anticipate something. I guess.
Yeah, in the
So-
meantime, that's great. I wanted to start the discussion.
No, actually, not, well, as soon as Achim is done, probably we can postpone it. But in the meantime, you know, just to feel the.
Sure. Yeah. Now, Victor, I wanted to ask you because I know that in case of flavor states, for example, for neutrinos, the flavor states not belong to irreducible representation of Poincare group simply
Yes.
because they don't have definite mass. In fact, we try to fix this, to look at this, looking at spontaneous violation of Poincare symmetry on flavor vacuum in quantum field theory. So how it should work what you are saying about transformation of entanglement, because you know a neutrino is also a classical example of entangled system in the where quantum information properties are widely studied nowadays. So
yeah, so that's actually a very interesting question, because of course the point is that there you have like a superposition of different masses, which is tricky. But there is one approach for this that might be helpful, which is this quantum reference frame approaches that can somehow deal with such type of situations. I don't know exactly about the details of the formalism. I entered in contact with it like 1 week ago, but it might be worth to take a look. But the idea is that basically it's like you also have like a superposition of Wigner rotations at the end of the day, you see.
sure.
But yeah, it's a more involved setup.
The neutrino has entanglement, which is related to kinds of entanglement. I would say static entanglement related to the fact that the combination of neutrino state with different masses, and dynamical entanglement, which is due to their time evolution correlation, which can be studied by Leggett-Garg inequalities. We can continue later the discussion.
Yeah, sure.
Achim is ready, or?
Yes, I am essentially ready. Just a sec, I'm just making it full screen here. Okay. Now I'll switch off my phone.
Okay, Luca,
yes, I must make him once more.
Make him pause probably the other.
Sure.
In the meantime, I'll let him activate the sound.
Okay, perfect. Now you can share it.
Okay. Achim, if probably Achim needs more time to fix these technical issues, probably we can.
Okay, we can switch. Maybe
I don't know. It's up to him. I don't know if.
It's up to him. How would you prefer?
How long is it going to take?
Oh, Achim just texted me. Yeah, we should probably switch to docs. That's what he said.
Okay, so we can change a little bit the program, and Barbara Soda will do from University of Waterloo to next talk, and Achim Kempf the first one. So go, Barbara. You can share your screen.
Okay.
Okay, so as said, now we have talked of Barbara Soda from University of Waterloo. Let's start.
Okay, thank you. Hello, everyone. I'd like to thank the organizers for giving me this opportunity. I'm going to talk about acceleration in quantum field theory, and I'm going to present 3 new phenomena. So, as you said, my name is Barbara, and I did this work in collaboration with Vivishek Sudhir from MIT and Achim from University of Waterloo and Perimeter. Okay. So usually in quantum mechanics and quantum field theory, acceleration doesn't come up. Acceleration doesn't appear to fit naturally into the framework of quantum physics. But there is an example where we understand it very well, and that's the Unruh effect. But as probably everyone in this audience knows, this effect is very small and it hasn't yet been measured. So one might ask, is there more to acceleration-related effects? Oops. And the reason why that is an important question is that acceleration is related to gravity through the equivalence principle. So if we want to understand quantum physics together with gravity, we should probably understand more about acceleration-induced effects in quantum physics. And so here I will present new acceleration-induced phenomena. I will tell you about how combining these new phenomena leads to increased measurability of the Unruh effect. And at the end, we'll discuss a little bit about how this gives us insights into gravity-related effects. Okay, so the broad picture of this talk is as follows. Light-matter interactions give rise to 2 kinds of transitions. There's resonant transitions and non-resonant transitions. The resonant ones are the usual, absorption and emission. They are strong and they happen around us every day. And probably everyone knows that these kind of transitions can be stimulated. And people do this every day in quantum optics in order to increase the rates of absorption and emission. They turn on the laser and thus increase the probabilities of these transitions as much as they want. On the other hand, we have non-resonant transitions, which are the unusual ones. They are the ones that give rise to the Unruh effect and the Hawking effect. We all know that these effects are weak, and so these transitions are also weak, but they're still there, and they can be activated by acceleration or gravity. So what is new in this talk is that I will show on the resonant side of things, I will show that the resonant transitions can be modulated with acceleration. And this will give rise to a new phenomenon called acceleration-induced transparency. On the non-resonant side, I will talk about how these non-resonant transitions can be stimulated as well. And this will make the non-resonant effects more measurable. Okay. So the way this works, as I said just now, we know that resonant terms can be stimulated by lasers. What is new here is that non-resonant terms can be stimulated as well. So what we'll do is we'll first stimulate the Unruh effect by the presence of photons in the quantum field. A problem that will arise then is that we'll see that this also stimulates the resonant terms. And we don't want that because we want to just stimulate the Unruh effect if we want to measure it in the lab someday. But there is a solution to this problem. I will show you this new effect of acceleration-induced transparency helps us to suppress the resonant terms to 0. And the outcome that we are left with in the end are just strong non-resonant terms, and in particular, we'll get a strong Unruh effect. So let's set the stage. Let's talk about the standard Unruh effect. I will talk about it in the framework of the Unruh detectors. So you can talk about the Unruh effect in a different framework, for example, with Bogoliubov transformations. But here we deal with Unruh detectors. So the setup is that we have a two-level Unruh detector. It has an energy gap omega. And then we have a scalar quantum field with its usual free Hamiltonian. The interaction Hamiltonian is written here. The coupling constant G, we assume it to be very small so that we can work in first order perturbation theory. And then the Unruh detector interacts with the quantum field along its trajectory. So this is the trajectory of the detector. And if we then zoom into the interaction Hamiltonian a little bit and look at what it's made of in details, you'll see that it consists of resonant terms and non-resonant terms. So the resonant terms, the ones responsible for absorption and emission, they're these ones. And we can see, for example, we can see how they work. Either, for example, a photon is created in the quantum field, and at the same time, the detector gets de-excited, or the other way around. The field loses a photon, but the detector gets excited. Okay, so those are the usual ones. And the non-resonant ones work in a different way. For them, either at the same time, both the detector and the field get de-excited, or both of them get excited at the same time. Okay, so in Unruh effect, what we look for is this type of a transition, where the detector and the field start out in their ground and vacuum state. And then after a while, at the end of the process, the detector gets excited. Those are typically the amplitudes that we calculate. So we do the calculation, as I said, in the first order perturbation theory. And this is how the amplitude looks like in the end. So we see here the coupling constant G. We see the frequency of the scalar field. But the most important part of the amplitude is this integral, I plus. I'll call it the non-resonant time integral. And it's defined here. You can think of it as the Fourier transform of a phase function that comes about from the trajectory of the detector. Okay, so it's a Fourier transform of the phase function coming from the trajectory of the detector. And it's the most important part of this amplitude. We probably all know already that this time integral I plus is equal to 0 for inertial motion. So we won't see an Unruh effect if the detector is moving inertially, but it's non-zero for a detector that's moving non-inertially. Now for the new effect, which is the stimulated Unruh effect. How does that work? So the setup is the same as in the case of the standard effect. We have the Unruh detector and the quantum field. Interaction Hamiltonian is still the same. But the new thing now is that in the standard effect, the field started out in the vacuum state, whereas here the field starts out in an excited state. In this case, just for convenience, it's a Fock state of the field. So we look at this transition. The detector is in the ground state, the field is in an excited state, and then we see what's the amplitude for the detector becoming excited. We calculate this amplitude and see that it consists of two parts. The first part is the Unruh-like part. Why do I say this? Well, this part comes about from the non-resonant terms, and this I plus non-resonant time integral also appears. Now, interestingly, we get the square root of n plus 1. And the square root of n plus 1 comes about, as opposed to the standard Unruh effect, because the field started out in an excited state. So these are the same n's. And this will increase the probability of seeing the Unruh effect by a factor of n. There's another term in this transition, which is the resonant term. It comes together with the resonant time integral, which is defined in a similar way to the non-resonant time integral. And this is going to later show to be a little bit of a problem because we want to get rid of the resonant contribution. So to compare, whereas the standard Unruh effect starts out with the field in a vacuum state, in the stimulated effect, the field starts out in an excited state. And if we check the probabilities, we see that the probability for the Unruh effect to happen is increased by a factor of n, where n is the expected value of the number of photons in the field. Expressed in this sentence, probability of excitation is enhanced by n. All right. And just if you're wondering if there's anything special about the fog state, I can say that I can show you similar results for field initially in coherent and thermal state. So if, let's say, field starts out in a coherent state alpha, and you calculate the probability of this transition, you'll see again that the probability for the Unruh effect is enhanced by absolute value of alpha squared. And we all know that that's the expected number of photons in the field. And similarly for this thermal state, again, the probability is enhanced by the expected number of photons. And it's shown in my paper that this is true for any initial state. The only thing that matters is the expected value of photons in the field. So I mentioned that, yes, this is great. We've shown how the probability for the Unruh effect is enhanced by a factor of n, but we still have this resonant term contribution, which is a problem. So we'll want to get rid of this contribution. The key to this is in these time integrals, the resonant time integral I minus and the non-resonant integral I plus. They are, as I said before, some kind of Fourier transforms of phase functions coming from the trajectory. If the problem was to eliminate the non-resonant integral I plus, we know how to do that quickly because we know that I plus is equal to 0 in inertial motion, whereas I minus can be non-zero in inertial motion. But we have the opposite problem of we want to get rid of I minus, the resonant contribution. So can we get rid of that contribution? And luckily, the answer is yes. There are trajectories for which the resonant time integral is 0, while the non-resonant time integral is non-zero. And the reason is that acceleration impacts not just non-resonant contribution, but also the resonant contribution. And this leads us to this new phenomenon of acceleration-induced transparency. So acceleration-induced transparency is going to allow us to cross out the resonant contribution, and we are only left with a clean, strong Unruh effect. So the way this new phenomenon of transparency works, I can show you in this very simple model of the simplest trajectory that you can think of. The motion of the detector is as follows. It moves first at some velocity v0, then abruptly changes to a velocity 1, and then finally it changes to a velocity v2. And so the question is, can we tune this trajectory so that for some energy gap omega of the detector, this time integral, the resonant time integral I minus is 0. In order to answer this question, we have to actually perform this integral. And so this is what it looks like. Looks a little bit complicated, but we don't have to look at it in details. I can just tell you that there is a choice of parameters for this trajectory, which results in the resonant time integral being equal exactly to 0. And so we know that for the detector with gap omega following this motion, we know that it will not get excited due to resonant terms. At the same time, because the I plus integral is non-zero, we know that for a detector following this trajectory, if it gets excited, it's definitely due to the non-resonant terms. And so this is how it looks like in a graph. If you look at the graph which shows the I minus integral, the resonant integral, we see two large resonance peaks corresponding to the initial and the final velocity. But in between those peaks, there's this point where if we zoom in, we'll see that at this point, the integral I minus is exactly 0. At the same time, I plotted the absolute value of the non-resonant time integral, so the time integral responsible for the Unruh effect, which is non-zero. And so if you think about this in the context of stimulation, where we can make the Unruh effect very, very large by using the presence of photons in the field, we see that at this point, we can make the Unruh effect extremely large, but the resonant terms will not contribute at all, because even though they are being stimulated, the time integral is pressing them exactly to 0. And if you're worried about me using the term exactly 0, we don't have to think of it in this way. It doesn't have to be, analytical 0. You can think of it in as small as possible. So we can make these two integrals be separated by as many orders of magnitude as we'd like. And so another thing that you might worry about is that this trajectory I just presented is unphysical because it involves abrupt velocity changes. But there are, of course, more realistic trajectories with the same transparency phenomenon. And for example, this trajectory where we have periods of accelerations and decelerations. And again, I can tell you that there is a tuning of parameters where there is a detector gap omega such that we can make the resonant time integral as small as we want. So again, we have acceleration-induced transparency. So summary so far, the first effect out of 3 that I announced initially is that the first thing is that we can stimulate non-resonant transitions. So this is the first effect, which is a stimulated Unruh effect. And I showed you that these stimulated transitions are n times stronger. We were faced then with the problem that we want to see just the non-resonant contribution, so the Unruh effect contribution. So we wanted to get rid of this term, the resonant contribution. And we can do this by using acceleration-induced transparency. Okay. And so in the end, we are left with only strong non-resonant terms, in particular strong Unruh effect, which leads us to a new method to measure the Unruh effect in lab. And finally, the third effect that I promised in the beginning is the catalyzed Unruh effect, which is a very interesting effect. And this is how it works. So in this effect, the detector starts out in a ground state and the field starts out in a coherent state. And at the end of the process, the detector gets excited, but nothing changes in the field. It stays in the same state it was in the beginning. So effectively, oh, thank you. So effectively, the field serves as a catalyst for the detector to get excited. It's kind of an interesting effect. And you might think, this is interesting, but is it exotic? Is it marginal? How much does it contribute to the total Unruh effect? In order to understand that, we need to compare the probability for the catalyzed Unruh effect to happen, which is here, and the probability for the total Unruh effect. So we get an expression like this. It's a bit messy, but we can simplify it significantly by using acceleration-induced transparency, meaning we just set I minus to 0 in this expression, and we get a simple expression like this. And we see if the number of photons in the field is large, and it is going to be large for some small lasers, it's like 10 to the 16, we see that this ratio is essentially equal to 1. So the catalyzed Unruh effect contributes to almost all of the Unruh effect. Okay, so to summarize, I showed the 3 new effects: the stimulated Unruh effect, the acceleration-induced transparency, and the catalyzed Unruh effect. I also showed how combining them leads to improved immeasurability of the Unruh effects, which is shown here schematically in this formula, where stimulated Unruh effect is n times larger than the standard Unruh effect. The question is, how big is n? Well, n for a small laser pointer, for a pocket laser pointer, is easily 10 to the 16. And so this is very important, because if we're talking about measuring the Unruh effect, we need to leap across many orders of magnitude. So this could help us move significantly forward in this effort. And finally, the question is, what do these new results suggest for gravity? So in this talk, we saw that resonant terms are strongly affected by acceleration. But now we can think, this clearly indicates that resonant terms are potentially also strongly affected by gravity. Meaning, if you have matter moving around in some gravitational field, this could, moving inside the gravitational field, could affect its rates of absorption and emission. So we could have a possibility of gravity-induced translucency, or even in some fine-tuned cases, we could have gravity-induced transparency. And also, we saw that non-resonant terms can be stimulated. In the gravitational context, this means that Hawking radiation and other horizon radiation could also be stimulated. For example, for black holes, Hawking radiation could be stimulated by radiation in the accretion disk. Of course, this is all new work, and so I cannot go into many details about this. But if you want to read more about what I've talked about in this talk, you can have a look at our paper that's on arXiv. So that's all, and I would like to thank you for your attention.
Okay, thank you very much, Barbara, for this nice talk. And check if there are questions. You have time. I will propose to do 5 minutes of questions, and then we postpone just to recover time. Postpone to discussion. The first question is from Luciano.
Okay. Hi, Barbara. Thank you for your nice talk. So what I wanted to ask is just curiosity, actually. Does the Unruh temperature get affected somehow by the number of photon used for the laser for the stimulation? I guess not, but this is just a curiosity. And does it then depend also on the acceleration that you use? Because in the trajectory that you showed to get rid of the resonant term, you have different values for the acceleration. So how does the Unruh temperature get affected by this? And just another side remark, if it is possible, then as you were looking, I'm looking at the outlook now, if this can be used, not in the near future, I guess, but can it be used, at least in principle, as an experiment, as some sort of test of the equivalence principle, this kind of approach?
That's okay. So I'd like to, can I do this? So if you look at the trajectories that the kind of trajectories that you need for acceleration-induced transparency, These trajectories do not, well, generically speaking, we don't know about all the trajectories, but they do not include eternal acceleration. So you will not get a thermal state at the end of all this. So if you like, we could call these effects Unruh-like effects. That would be the answer to both of the first two questions. Because if you don't have a thermal state, then so the third question you asked was, can this be used to check equivalence principle?
Mm-hmm.
Can you elaborate a little bit more? What do you mean?
Well, in a sense, because in the outlook you said that, for instance, you can think of something analogous also for the Hawking radiation and so on. So if one thinks of some sort of equivalence between the two things, at least in principle, with a thought experiment, is it possible to check if these two predictions give you the same thing, or if there's some difference? Because there is a paper in which a PRL, which I don't know how many years ago it was published, but it relies on the equivalence between the Unruh and the Hawking radiation. It is usefully done in literature to see whether equivalence principle holds or not. So that's why I was just asking if with this implemented scenario that you have exhibited, something more can be said about that.
Mm-hmm. Okay, so we haven't thought about this yet. I can say that this doesn't go. This just all of this fits into the framework of standard physics. So if we would use gravitational effects, we would use GR, and the GR is consistent with the equivalence principle. So we haven't thought about this yet. So this is all very new and it's work in progress. So, okay. Did you have any ideas?
I think
next. Continue.
No. You can go with the next.
Okay, so next question is from Victor, which can also unmute himself, I think.
Okay, so yeah, thanks a lot for the very nice talk.
Mm-hmm.
I have a question regarding, okay, so in your model, you basically have like a two-level system coupled to a photon field. So you can imagine that your setup is, I don't know, like a cavity, and you put like an atom inside there, and then you just accelerate this whole thing, right? More or less. So what happens now if you start like to put like more two-level systems there? So does those effects can create, for example, some sort of collective phenomena between your two-level systems, or something like that? Like generate entangled states between the two-level systems, or when you have like I don't know, an atomic cloud or an ionic cloud, does it generate like some exotic state of matter because it is accelerating somehow?
Okay, I don't know about the details of that, but okay, so since I come from the RQI community, and I'm assuming this audience is not RQI, for example, what you can do if you have two Unruh detectors, you can harvest entanglement even from the vacuum. So you don't even have to have, photons present in the field. So that's one thing you can do. I mean, that's the phenomenology of what you can do with Unruh detectors is vast. So you're asking, you can create entanglement between the multiple two-level system in this way and so on. Yeah, you can do many things.
Okay, and in the case where you have like vacuum, can you have like, I don't know if what I will talk makes sense, but can like these acceleration effects induce like phase transitions like to a super radiant state, for example? Or although I'm not sure because you are going like to accelerated frame, so basically you go like to a thermal-like state, but I don't know. I was thinking more along these directions as well. So
yeah, that's an interesting question. That's an interesting question. I don't think that has been done, but sure, yeah.
Okay, thanks.
Okay, if there are no other questions for the moment, I think we can go ahead. Just a little late, so a little delay. And we can pass to the contribution of Achim Kempf.
Hello there, can you hear me?
Okay, good. We can see your screen.
Wonderful. I have to start by apologizing. This was a worst case scenario. Just a minute before I was supposed to be on, you see, there was a power cut because there's construction next door, and it completely messed up my PC. Anyway, I hope that you can see my slides now. Can you? Okay, very good. Yeah, you seem to be.
Yes, yes, we can see.
Okay, very good. All right, so thank you for the kind invitation. I will talk about the question why quantum gravity is so hard. Well, one of the reasons is, of course, power cuts, as we just found out. But apart from that, why is quantum gravity so hard? Now, let's think back. When general relativity was developed, it required abandoning deeply held beliefs about the absoluteness of space and time. And when quantum theory came along, it too required abandoning deeply held beliefs about kinematics and dynamics. Now, quantum gravity is so hard, and this suggests, of course, that there might again be some deeply held beliefs that may need to be abandoned to make way for the development of quantum gravity. So what could be such deeply held beliefs that we may have to abandon? Well, I want to challenge one of them today, and that's what may be called the stage and actors belief. The belief, the intuition that space-time is a kind of dynamical stage on which actors in the form of matter are moving. The big question then, of course, is what picture could supersede this picture? If space-time is not a stage and matter not actors that move on that stage, if that's only a low-energy approximation, then what would be the true story behind it? What picture could lie behind it? Now, that's a difficult question, and we need some hints. And I think we can get some hints by thinking about what might be viewed as odd about the stage and actors intuition that we usually have. So let me list a few things that I think are a bit odd about this stage and actors picture, and maybe these hints help us then to go beyond the picture. Let's go back to the basics of how we describe a space-time. As Einstein explained, we are supposed to take rods and clocks and build coordinate systems, and that's the big link between the mathematics of general relativity that describes space-time and the physics of the tools that we use to map out space-time. Look at the properties of these things. Well, first what comes to mind is that rods and clocks, whichever way we build them, rods and clocks are not canonical things. They're not things provided by nature. It's something we have to make. And they're not in themselves covariant, even though we can use them to eventually measure out covariant things. They're not themselves in any form canonical or covariant. And nature doesn't provide anything rod-like or clock-like at subatomic scales. And space and time seem to be much closer than rods and clocks are to each other. Space and time are mathematically very close. They only differ by a factor of I or a minus sign. But if you compare rods to clocks, rods and clocks are very different. They seem to be more different than just a minus sign or perhaps a factor of I. And then let's move on to the coordinate systems that we build using rods and clocks. Coordinate systems are useful, but they're ignorant, for example, of the entire drama that happens on the light cone. When an event is either inside or outside the light cone of another event, then this determines whether or not there can or cannot be a causal relationship between them. It makes a huge difference, but coordinate systems don't care about that. 2 points could be arbitrarily close in a coordinate system, and yet in completely different worlds in the sense that they could be in or outside a light cone. And then once we have coordinate systems, quantum gravity requires us to mod them out. Because when we have coordinate systems, then they affect the way that the metric tensor, for example, looks like. And then when we want to path integrate over geometries, we have to path integrate over the metric, but the metric tensor describes not only the curvature, it also depends as a function on which coordinate system we use, but we don't want to path integrate over the human choice of coordinate system, so we have to mod out by the coordinate system at the end. So what I would like to pursue today is the suggestion to abandon rods and clocks and coordinate systems, and indeed the notion of manifold for space-time altogether. Now, clearly, if we try to do that, we have to consider what the ramifications will be. And one ramification, obviously, is that we have to reconsider what happens with diffeomorphisms. The diffeomorphism invariant is important. But if we want to abandon rods, clocks, coordinate systems, and manifolds, what happens to the diffeomorphism group? And what I'm suggesting here is not to break the diffeomorphism group, but to enlarge it vastly, namely to a much bigger group, which is the unitary group, which describes spaces independent. And I'll get into more detail about this soon. But let's start from the very basics. So we're challenging here the idea that we need rods and clocks to map out a space-time. Now, how can we replace rods and clocks? Well, nature has actually provided us with a canonical tool that can replace rods and clocks in order to determine space-time distances. What I'm referring to is the quantum fluctuations in the vacuum of quantum fields. The quantum fluctuations of a field are correlated from one location in space-time to another location in space-time. And why is that? Well, imagine we consider two locations in space-time, two patches of space-time. If they are time-like or null to each other, then the quantum fluctuations in one patch are correlated to the quantum fluctuations in the other patch simply because of propagation. Doing one patch will propagate to the other, and therefore what happens at each location is correlated. But also, even if the two patches of space-time where we are considering the quantum fluctuations are space-like to each other, then too the quantum fluctuations are correlated. And the reason there is that the vacuum state is an entangled state. And it is an entangled state because the local oscillators of the fields are coupled to each other, and coupled harmonic oscillators in their ground state are in entangled ground state. Now, what I'm mostly want to use here is that the amount of correlation that exists between the quantum fluctuation in one region and the quantum fluctuations in another region depends on how far these two regions of space-time are apart from each other. The closer they are, the stronger are the correlations of the vacuum fluctuations. The further away they are, the weaker are the correlations. This is captured, for example, by the two-point correlator, G2 of X and Y. And in lowest order perturbation theory, that's just the Feynman propagator. But of course, in general, it's a complicated thing. Now, G2, the two-point correlator, is generally a complex valued biscalar function. And its modulus, its magnitude, its amplitude is the larger, the closer X is to Y. Also, the correlations diverge at the light cone, on a light cone, and the sign of the correlation function is also changing. So the two-point correlator is definitely sensitive to whether we are inside or outside the light cone. It diverges and changes sign as you cross the light cone. Well, what is important for our purposes now here is that the two-point correlator, because its magnitude depends on the space-time distance, can serve as a proxy of space-time distance. it can serve as a measure of space-time distance. And this suggests that in general relativity, the metric tensor G mu nu might be replaceable by the two-point correlator. So wherever we normally use the metric, we might be able to use the two-point correlator. The reason being that the metric's purpose is to tell us about small space-time distances, and the two-point correlator tells us about space-time distances, small or large. So can we formulate general relativity with two-point correlators instead of rods and clocks? So instead of rods and clocks, what we would do is we would observe and count quantum fluctuations in one location, quantum fluctuations in the other location, and then calculate what the correlator is between them. So can we do that? And the answer is yes. And the reason is that the metric tensor is expressible or calculatable from the two-point correlator. If you look at this equation here, on the right-hand side, you have the capital G2, that's a two-point correlator. And on the left-hand side, you have the metric here. This is a result that I published with Siavash Sambegi and Mehdi. And so what do we have here? We have a prefactor that's geometric. So D here in the gamma function, capital D is the space-time dimension. And I will assume here that the space-time dimension is larger than 2. For space-time dimension capital D equal to 2, there's a slightly different formula that involves the logarithm. Okay, and then we have to take the second derivatives, two derivatives of the two-point correlator taken to some power here. And what I want to point you to is that the power is negative because D, the space-time dimension, is larger than 2. So therefore, we have to take the two-point correlator to a negative power, then take the derivative with respect to x and y, and then the coincidence limit x going to y. In this way, we are extracting the short distance information contained in the two-point correlator and transform it into the information that the metric represents. So we are here recovering the metric tensor from the two-point correlator being a biscalar. Important here is that the power that we take of the two-point correlator is negative, which means that the I epsilon prescription doesn't matter because the propagator, the two-point correlator, has poles in the denominator, but if you take it to a negative power, they are zeros in the numerator, and then you can take the limit for epsilon going to 0 before anything else. So the boundary conditions don't matter. You could do this not only with the Feynman propagator, you could also do it with the advanced propagator or the Italian propagator, and so on. The conclusion so far is that we can express by space-times, if we want to, as usual, as a differentiable manifold M on which there is a metric tensor G, or as usual, for example, as a differentiable manifold M with a connection. But as we just saw, we can also describe a space-time as a differentiable manifold with a two-point correlator on it that's completely equivalent. However, we still need a coordinate system in this description here, right? Because the two-point correlator is still a function of x and y. We're working with coordinate systems. We still have diffeomorphism invariance here. We got rid of the rods and clocks, but we didn't get rid of the coordinate systems yet. So how can we upgrade and get away from coordinate systems? Why do we want to do that? Well, because we want to path integrate over geometries. And we couldn't do that with the metric tensor because the metric tensor depends not only on the geometry, it also depends on the coordinate system. And then summing over all metric tensors would involve not only summing over all geometries, but also over all choices of coordinate systems, which are human choices. And it makes no sense to path integrate over human choices. And similarly here now, the two-point correlator is a function of the metric, but it's also a function of the choice of coordinate system. We want to get rid of this. So the capital G, the two-point correlator, still depends on the geometry and also on the coordinate system. So what have we gained by going from the metric tensor to the two-point correlator so far? Well, what we've gained is this. While the metric tensor is simply a covariant symmetric 2 tensor, in contrast, the two-point correlator is an operator on a Hilbert space, right? Because it is a right inverse of the D'Alembert operator, which is an operator on a Hilbert space, namely the Hilbert space of fields, the fields that we are summing over in the path integral. And we do know how to extract basis-independent information from. That's what we can do now. That's what we will do now. We will take the two-point correlator, view it as, I mean, it is the right inverse of, it is a right inverse of the D'Alembert operator. And then we can calculate the spectrum of the propagator or the spectrum of the D'Alembert. It doesn't matter, they're inverse to each other. It's better to work with the spectrum of the D'Alembertian actually than the Green's function, two-point correlator, because the two-point correlator is not necessarily self-adjoint operator. The D'Alembertian always is, but it's right inverse not always, and that's because we can add homogeneous solutions, and those homogeneous solutions generally mess up the self-adjoint. But remember, we don't need to care about the I epsilon prescriptions, so we can work with any one of those right inverses, but we can also just work with the D'Alembert. So it seems we have achieved something here. We take our two-point correlator, view it as an operator, and then consider its spectrum. We extract its spectrum. The spectrum is independent of the choice of bases in the space of functions that we sum over. The spectrum, therefore, must consist of geometric invariants. If you change coordinate systems, you're not changing the spectrum of the D'Alembertian at all. The D'Alembertian is a scalar operator. So it seems that we have extracted the geometric information that is contained in the two-point correlator cleanly. And we seem to have arrived at the old discipline of spectral geometry, which is older than generativity. Remember, spectral geometry was founded by Hermann Weyl, who asked how much about the shape of a geometry, such as a manifold, can you hear in the spectrum of a wave operator on it? So we can now ask, what's the answer to this? Does the spectrum of the D'Alembertian contain all of the geometric information that we want? And the answer is no. Remember, spectral geometry is asking questions such as, can you hear the shape of a drum? And the answer is, unfortunately, no. Not always. Sometimes you can, sometimes you cannot. But you can't rely on it. So something went wrong here. We started out with the two-point correlator, and we know it contains all of the geometric information. We want to distill that geometric information out of it. We did so by taking the spectrum of it, and now we have too little spectral information. So we have too little geometric information. Where did we lose geometric information? How did that happen? It's an important question because it can also, if we can answer that question, we can also fix spectral geometry. It can be done. So here's how this goes. Let me review the problem. The problem is that on one hand, the two-point correlator we know contains all information about the metric because we can reconstruct the metric from it. But the spectrum of it does not contain that information. What is the spectrum? The spectrum of the two-point correlator is the two-point correlator in its eigenbasis. And G2 of x and y is the two-point correlator in the position basis. Somehow in its eigenbasis, it doesn't contain all of the information. How did this happen? How could it be that the spectrum consists of geometric information, but not all of it? The answer is this. When we take the spectrum of an operator on a Hilbert space, the spectrum is invariant under the full unitary group of the Hilbert space. We can change bases whichever way we want. The spectrum is unaffected. But the invariants that we wanted are the geometric invariants. But geometric invariants are invariant only under the diffeomorphism group. You see, the unitary group is way bigger than the diffeomorphism group. Consider, for example, changes of coordinates. Any change of coordinates is a change of bases. But not every change of bases is a change of coordinates. For example, a Fourier transform is not a change of coordinates. A Hermite transform is not a change of coordinates, but they are all unitary. So the unitary group is way bigger than the diffeomorphism group. By modding out the unitary group, namely by calculating the spectrum, by modding out the unitary group, we had a too stringent criterion for keeping invariants. And so we kept too few invariants, and we lost some of the important geometric invariants in the process. That's why spectral geometry, by going to the spectrum of a wave operator, we are modding out the entire unitary group when really we wanted to mod out only the diffeomorphism. Is there a solution to this? And there is. And it's because nature does us a favor. Now, what favor does nature do us? Well, it does us the favor that there exist not only 2-point correlators, there also exist non-trivial higher point correlators. Fields generally interact with each other.
10 minutes.
Did you say 10?
10 minutes.
Yeah, thank you. Okay, so nature also gives us higher than 2-point correlators. And these higher than 2-point correlators, again, are abstract operators acting on the Hilbert space of fields. And they have a very special property. Namely, they are local. This is not required by mathematics, but nature provides it to us. Nature has only interactions, as far as we know, that are local. And that means that these higher point correlators, these vertices, when you look at them as abstract vertices, as abstract operators in the Hilbert space of fields, they could take any shape, but in a positional representation, and only in a positional representation, these vertices become products of Dirac deltas in order to express locality, in order to express that interactions are local in quantum field theory. That's important because it means that if we know the abstract endpoint correlators for n larger than 2, then we know implicitly what the positional bases are in the Hilbert space, because they are those spaces in which the higher order correlators are diagonal, in which they are products of Dirac deltas. But that means that if we are given the abstract 2-point correlators, the abstract endpoint correlators in the Hilbert space, then we can reconstruct the entire space-time manifold and the fields that live on it. And how do we do it? Well, we diagonalize the n larger than 2 correlators. We can do that. We know that all the interactions are local, so there are positional bases. And then once we know where the positional bases are in the Hilbert space, we can take the propagator, the 2-point correlator, write it in a positional basis. And then we have the 2-point correlator in a positional basis, and we have a formula for, from that, calculating what the metric is. Now, let me reformulate that in terms of spectral geometry. In terms of spectral geometry, it means this: you may not be able to hear the shape of a drum unless you hit it hard enough. Because if you hit a drum hard enough, then what happens is that the amplitude gets so large that you get into the nonlinear regime, into non-harmonic oscillations, which can be rewritten as harmonic oscillations plus self-interactions, right? And then we have that situation. And you see there is extra information in the nonlinearity of oscillations on a drum, for example. Now let's go back to what our actual ambition here was. We wanted to find an alternative to the stage and actors picture that would kick in at the Planck scale. Of course, at low energies, the stage and actors picture is pretty accurate, but maybe we have to go beyond it at the Planck scale. And what do we get as an alternative to the stage and actors picture from this perspective here? Well, what we get is this: the diagonalizability of the vertices of the endpoint correlators is not guaranteed mathematically. There is no spectral theorem for higher point correlator functions. It is because nature does us a favor that these higher point vertices are local, that all interactions are local in nature. Nature does us a favor there, as far as we know. But as we approach the Planck scale, there is no guarantee that actually these endpoint correlators really are diagonal. You see, we all have thought about the prospect that if we approach the Planck scale, the very notion of distance might change. For example, there could be generalized uncertainty principle. There could be all sorts of things happening. The very notion of distance might fail. And here we have now a new mathematical way of thinking of how that exactly could happen. Indeed, what could happen is that these endpoint correlators simply can no longer be diagonalized. That only approximately they can be diagonalized, but not properly. They're not really products of Dirac deltas exactly. But that means we can no longer just take the 2-point correlator, write it in a positional basis, and then calculate a metric. So as soon as it happens that the endpoint correlators for n larger than 2 can no longer be properly diagonalized, we do no longer have a representation of our correlators in terms of fields that live on a manifold. So the fields living on a manifold picture is a representation of a more abstract mathematical structure, which is the set of the tower of endpoint correlators. And these endpoint correlators can only approximately be represented as field correlators on a space-time manifold, but generally, we just have these correlators. At low energies, yes, they can be represented as fields on a manifold, but maybe not at very high energy. So this means that at the Planck scale, the anticipated failure of the stage and actors picture takes the mathematical form of the failure of a traditional representation of the endpoint functions. This is, by the way, quite similar to how in first quantization, in quantum mechanics, the position and momentum functions, number-valued functions, are ordinarily pretty useful for, I don't know, for building rockets, for example, and in ordinary mechanics. But if you really push it and go to the mechanics of atoms, then of course you can no longer represent the x and the p operators, which they really are, as commuting objects. Then it really matters, and the representation theory breaks down, and you have to use a different representation theory. Okay, so the failure of the stage and actors picture has a mathematical representation in the form of the failure of a mathematical representation in the usual form of matter fields that live on the space-time. Now, if therefore all of the physics is encoded in the endpoint, in the abstract endpoint correlators, which at low energies can be represented in terms of field correlators on the space-time manifold, but at high energies, they're just abstract correlators, then we have to ask, what determines these correlators? If they are the heart of it, and obviously that's an information theoretic concept. Correlators are really just asking to be studied information theoretically. So what are the laws that govern these correlators? Now, when the Gn are really correlators, well, then it must be of this form, because all correlation functions are of the form of a sum or integral over some variables that fluctuate with some weight function, right? So if they're correlators, abstract correlators, they have to take this form with some weight function, where the d phi is the measure that we integrate over here. Now we know from our low energy physics, from our standard model, what this weight function is, at least at low energies. It's of course simply e to the power I times the action, right? And this is simply the path integral. We've just seen here that, yeah, well, if the Gn are correlators, then they have to arise from some form of path integral. And we know that from experience that the weight function is e to the power I times the action. Now, in order to illustrate what I said so far in my talk, let me give you a simple, quick example of where everything here is played out explicitly. Super trivial example. Let's say we consider the action here for Klein-Gordon field and gravity. That's what we want to quantize, Klein-Gordon field and gravity. Then what does the action look like? Well, the action of a Klein-Gordon field, massless Klein-Gordon field, is of course down here at the bottom right, integral over phi, Dano-Bergson phi. But we want to write it not only coordinate system independently, we also want to write the basis independently, right? We are upgrading from the diffeomorphism group to the unitary group. So what we do now is we write this action here like that. It is the trace of 1/2 the Dano-Bergson operator acting on the field vectors here. Now, I wrote here cats and brass, but of course, these are not the states of the quantum field theory. These are just the notation is simply an abuse of notation. It's really just saying these are vectors, abstract vectors in the Hilbert space of fields over which we path integrate. I'm not the first to use that notation. Schwinger and De Witt and many others have used the same notation before in order to write things in a basis independent way. So we can write the action in this basis independent way, and we can plug that in here. But we want more than just a Klein-Gordon action. We also want gravity. How can we include gravity in the action? It would seem to be very hard. We would have to express somehow the Ricci scalar. But actually, it's very easy, very straightforward. And nature does us a favor here. Here's a simple possibility to include gravity in our action. First, let's assume that there's a sharp ultraviolet cutoff. You can view it as a regulator. You can view it as a natural ultraviolet cutoff. Let's call this cutoff lambda. Then let's use a result from spectral geometry that goes back to Gilkey, and then Hawking popularized it. And what they showed is this. And this is for the special case of Euclidean compact Riemannian manifolds, but there are more general versions of this too. But let's focus on the Euclidean case for now. What has been shown there is that when you have an ultraviolet cutoff for a Euclidean Riemannian compact manifold, then by ultraviolet cutoff, we mean there's a cutoff on the spectrum of the D'Alembert. Then you can ask, how many eigenvectors does the D'Alembert have up to the maximum eigenvalue lambda? And that number, the number of eigenvalues, is the dimension of the Hilbert space at this point. And the dimension of the Hilbert space has to be some sort of universal scalar. And it was proven, it's a result of spectral geometry, that it is of this form, which is intriguing because this integral form here starts out with a cosmological constant, then the Ricci scalar, and then higher order curvature terms. The cosmological constant comes out too large. The Ricci term comes out exactly right as the Einstein action if the cutoff is chosen to be exactly the Planck length. If lambda is the Planck length, then this prefactor is exactly the Einstein action. And the higher order curvature terms, which are not part of the usual Einstein action, are very highly suppressed. But we'll take them along anyway here, just for the illustration purposes of this example. And in any case, we know that any interacting quantum field theory on a curved space-time will induce in the renormalization process all kinds of higher order curvature terms anyway, so we can't get rid of them anyway. So we might as well keep them. And if we do that, then it means that the Einstein action, together with the higher order curvature terms and the cosmological constant, are really just the dimension of the Hilbert space. In other words, the trace of one. The trace of the identity operator is the dimension of the Hilbert space, is the number of eigenvalues that you still have of the D'Alembert. This means that we can write the action of the Klein-Gordon field and gravity as the trace of some multiple of the identity operator plus the Klein-Gordon action. In other words, gravity's action is reduced to just a leading constant in the action. The action can be viewed as an expansion of all sorts of fields, and the leading constant term, just the identity operator, with the prefactor mu, which has to be chosen, 6 pi Newton constant to the power 1/2, that reduces, if you write it down in a positional basis and spell everything out, use the Gilkey-Hawking formula, then this reduces to the Einstein action plus higher order curvature terms plus the cosmological constant plus the usual Klein-Gordon action. But in this Hilbert space invariant form, in this formulation where we upgraded the diffeomorphism group to the unitary group of invariances, the action of the Klein-Gordon field in gravity just reduces to this very simple trace here. And now let's do it. Let's actually do the path integral of it. Let's calculate the partition function for this simple example. What do we need to do? Well, we need to integrate over all fields, all Klein-Gordon fields, and that takes care of the matter. We only have Klein-Gordon matter here. We need to integrate over all possible geometries. How do we do that now? Well, integrating over all possible geometries is now at the integral over all possible spectra of the Laplacian with capital N eigenvalues. And we have to sum over all possible N, over all possible numbers of eigenvalues that we can possibly have below the cutoff. And in this simple example, I am assuming that the Klein-Gordon field is not self-interacting. So this is a much more simple situation. But in principle, self-interaction should be considered as well. And then you would have the higher point correlators also to worry about. But then I can probably no longer do it non-perturbatively. But here we can do it non-perturbatively. We can actually carry out that entire path integral. So let's calculate the partition function then. What is it? It's the sum over all possible numbers of eigenvalues that we still have below the threshold, below the cutoff. Then we have the integral over all possible values that the eigenvalues can take within the allowed eigenvalue interval within the cutoff. And when we integrate over all possible values of all eigenvalues, then we get every spectrum n factorial times, because we didn't take care of the relative ordering of the eigenvalues, so we have to divide by n factorial. And we have to integrate over all field configurations. And here is what we integrate over. That's just e to the power of minus the action. It's the Euclidean in this case. And here, this is still a representation which is basis independent. But we can choose a basis, a convenient basis, for example, the eigenbasis of the Laplacian. In this case, the Laplacian is replaced by a sum over its eigenvalues times eigenvectors. And what we get is that the matter fields, the Cairngorm fields, are represented by their coefficients. And then the path integral over the matter fields becomes simply an integral over all the coefficients of the matter fields. And then we also have to integrate over all spectra, lambda, and over all numbers of eigenvalues. And all of these many integrals and this series can actually be done. It's just simply this case. And the result is that the partition function is e to the power of square root of 8 pi lambda times e to the power minus mu. And from that,
sorry, we are out of time. So
yeah. Okay. This is the last slide. Summary. So what did we do? We upgraded the diffeomorphism invariance to unitary invariance. How did we do that? We replaced rods and clocks by 2-point correlators. The 2-point correlator can replace the metric. And the 2-point correlator, together with the higher point correlators, abstractly given, not necessarily in a position basis, but abstractly given, will determine what the position bases are, what the metric is. And then, if so, if we do this, then at the Planck scale, the stage and actors picture can fail. And it fails in the following way. The n-point correlators do no longer have a basis in which they are diagonal. Therefore, we can no longer write the 2-point correlator in these positional bases, because there are no positional bases anymore. And so we can no longer reconstruct the metric. It can only be done approximately. But we can still maintain that the physics is described by the bunch of n-point correlators. And then the calculation of the n-point correlators is naturally done from path integrals, just by virtue of them being correlators. And then using the Gilkey-Hawking results of spectral geometry, we can include gravity. And in simple cases, we can actually do these partition functions and calculate expectation values. Also, the expectation value calculation hasn't been done yet. And for interacting cases, of course, the path integral will be much more complicated. And the path integral, if you remember, is usually analytically ill-defined. And I would like to just point out that in the next few days, my collaborators, David Jackson and Alejandro Morales, and I will put a paper on the archive where we help that situation by rewriting the path integral not as an analytic integral, but as an algebraic combinatorial integral, which is no longer sensitive to these analytic issues. Okay, thank you very much for your attention. And I apologize again for the catastrophic start of it all.
No, don't worry. Okay, I think we are out of time for the questions, but we can start directly with the discussion session. And so I think we can start from Achim.
Shall I unshare my screen?
Unshare your screen, yes. So question from Gaetano Fiore is the first one. Okay, ask to unmute.
Yes. Thank you very much, Achim. It was a beautiful, extremely stimulating and pedagogical also talk. Really.
Hey, Gaetano, very nice to hear you after so long.
Yes, very nice for me. One question. I guess that if you use instead of the scalar field some other field, a spinor field, say, you would be able again to recover information about the metric. First in a classical framework. So if you do in a classical framework this. So you start with the metric, you introduce correlation functions of the scalar fields, and then let's say of the spinor fields, then there must be a relation between these two sets of correlation functions due to the particular choice of the metric. You agree? So are you able to abstract this relation between correlators of different sets of fields so that you can get rid of the metric and formulate it directly as a relation between correlation functions of, say, the scalar fields and of the spinor fields, something like this, which can be then taken to be true also at high energies and so at Planck scale.
I think this is a very beautiful question. Two parts, and I understand that this is a two-part question, and I very much agree with the first, but not so much with the second. So I understand that first you're saying if you have two kinds of fields, let's say some Klein-Gordon field and some Dirac field, then you can use each of them to reconstruct the metric.
Yes.
And since both of them live on the same space-time, you ought to be reconstructing the same metric. And therefore, there have to exist relationships between the correlation functions derived from the Klein-Gordon field and those derived from the Dirac field. And yes, I think that's beautiful. And I don't know exactly which shape that would take. I think it's very interesting. Basically, what you're saying is that given that they live in the same space-time, there must be relationships between them, and that's cool. Yeah, I don't know what equations you get there, but it's very nice. That's the first part. The second part of your question was whether you can use these relations to get rid of the metric. And I would say, I already got rid of the metric.
No, I meant, to get, I mean, so you don't use the metric anymore. You have two different sets of correlation functions with some constraints, relations between them. Yes.
Yeah. But you're right. There ought to be some sort of Bianchi identity type things. You see, the Bianchi identities ordinarily express, of course, diffeomorphism invariance, and now everything takes a different shape. And the Bianchi identities are to resurface in some new form, and maybe they are what you're referring to.
Yeah. Very well.
Very nice.
So before we had some questions from Gaetano Luciano to Barbara, and so I give priority to this question. Can I mute you?
Do I know the question already, or can I read it?
So actually, I've seen that Gaetano did not have his earphones, so probably now you can ask him again to.
Okay, sorry. Okay, so thank you to the speaker for the very nice talk, and my question is for Barbara. And so, if I well understand, you are saying that at least in principle, we may detect the Unruh effect or something like that, even for small acceleration, right? Provided that we consider grid values of n, right? Is this your message?
Yeah. By simulation.
Okay, so that will be very interesting. And my question is, do you have any idea of how large should be n to detect, for example, the Unruh effect even for acceleration of the order of Earth's gravity?
Okay, so we haven't calculated yet the exact numbers. For example, this paper is about the toy model where you have, the two-level Unruh detector and a scalar quantum field. So the next step will be to do, a full electromagnetic calculation and so on, and then we'll get an idea of real numbers. But I'll just say, if you can jump by 20 orders of magnitude, or between 50 and 20 orders of magnitude, it's promising. But I cannot talk about exact numbers now.
So I think in principle, you are saying that even if we are in a lift, we may detect the Unruh effect or something like that, right?
even if we are in a lift, because there is light around us. That's what you're saying.
Yes, but in principle, I mean, if we will be able to consider very large n, in principle, we may, or not.
Mm-hmm. N is the number of photons present in the field. Well, look, okay, so there's one small detail, which is very important, where in a lift, you don't have acceleration-induced transparency. So in a lift, you would mostly see resonant effects like absorption and emission. And Unruh effect would be stimulated, but it's still many orders of magnitude smaller to the resonant effect. And in our work, that's very important because acceleration-induced transparency is important because that's how we get rid of the resonant terms and we are left with only Unruh.
Okay, thank you. Thank you.
No problem.
And if I may add, the Unruh effect is very hard to measure. In fact, it's still impossible to measure as it is. And so we have to cross a lot of orders of magnitude just to make it measurable. And then to also want to measure it at small accelerations that may be pushing it.
Okay, but the message is that at least it will be possible to measure the Unruh effect even for small, or something like the Unruh effect even for small acceleration.
Yeah, in principle, if you use some super powerful laser and you can control your trajectory extremely accurately so that you can use Barbara's acceleration-induced transparency, then yes.
Okay, thank you.
So sorry to drop in, but I have a comment related to that. Actually, one of the questions that I asked Barbara was about, when you have like ensembles of atoms in these setups, but what I just thought is that usually in these light matter interaction systems, when you have like this ensemble of atoms, you get an enhancement in the coupling between light and matter just because, you have a lot of atoms. So this might be something that helps you to increase this detection sensibility or whatever in your system. So, you get some collective effects that helps you to increase the Unruh effect when you have like an accelerated cavity many body system or whatever. And actually, sorry.
I think Barbara is a little too timid here, but yesterday we had a discussion and she proposed exactly that already.
Yeah.
So it's a good idea.
Yeah, and this is actually a very appealing framework because, so people those days, they can create Bose-Einstein condensates in space. So you then just put it inside a cavity and you figure out a nice setup to see those effects. I mean, it sounds easy, but it's not easy. But you got what I mean.
Yeah. So I mean, this could be possible. This is just an idea. Yeah. In that case, you could have an enhancement due to presence of photons by the number of photons, and then you could also possibly, maybe, I mean, we don't know, have an enhancement by the number of Unruh detectors, and then you could have like I don't know, n times m enhancement where both of those numbers are large.
Yeah.
Speculative.
Yeah, and then you can even think about, okay, so like, NV centers in diamonds, or there is this system that, you have like these collective excitations of the magnetization in ferromagnets coupled to microwaves. There you also have like some sort of enhancement because, you have a macroscopic numbers of spin interacting with an electromagnetic field. So yeah, I'm actually working a lot on the field, so I have like a lot of setups in mind. So I just wanted to make the commentary.
Thank you.
Can I ask?
Just a second. We are trying to. Okay.
Yeah, I think there is a question
first. We're trying to follow by the order. So Nikolaos, you're next after Fedele. Okay, Fedele, of course. Yeah, no, never mind, Luca.
Okay.
No, you had unmuted me, but then since there was somebody else talking, I thought it was polite to mute me myself again, and then I lost it. I have a question for Achim.
I am unmuting everyone who wants to do a
No,
question.
okay, but I muted myself again, and then I couldn't unmute me again. That was all. I have a question for Achim. Ciao. And I don't see you, but I assume you are still there.
Yeah, I'm here.
Okay, ciao. The question is the following. First, a comment and then a question. And of course, your spectral view is very close to the heart of everybody that worked with the spectral action, which is exactly what we have written, basically. And actually, with Vasilevich and Kurkov, we did calculate the spectral action, resumming it in the high energy limit. So going to beyond the cutoff, and we found the 2-point functions for the graviton and for the bosons. And they are quite interesting because they are delta functions. So the 2-point function means that the particles are completely uncorrelated in the limit. So, which is what you expect because you have a cutoff. But now the question is, if you have such a radical term, what would the metric be? Would be something which is similar to the asymptotic silence, this kind of things. So I wonder how these things would, whether you can handle such a drastic. This is and I said, well, it was with Vasilevich, so heat kernel calculation with all the things, and it's done using Varisky and Vilkovisky resummation techniques. But the result is quite interesting. It would be interesting to try to go beyond. I liked your idea of that if you hit hard enough the drum, you can hear the shape of the drum. The problem there is that you can also hear the shape of the stick, because then it becomes an interaction. So I think that if you have non-linear terms, then isospectral manifolds will probably be, there will be probably more isospectral manifolds. You cannot hear the shape of the drum because there are manifolds which are isospectral. But then if you take self-interaction, which depends on the stick as well, so probably there will be other ambiguities which come. But in any case, it's very interesting, and I think one should look at this radical metrics and try to make physical sense out of them. Now you are muted.
Oh, can you not hear me?
Yes, now I can. Now I can. No, now I can't. I don't know if it's only me.
Can everybody hear me now?
Yes.
Okay, they say they can hear me.
Mm-hmm.
All right. Okay, so I understood that you have two questions here. One is this: you were referring to work of yours, and I would like to see the reference, please. This sounds very interesting, Fedele. Please send me the reference to this.
It's called High Energy Bosons Do Not Propagate.
Okay, great.
It's about 5-6 years ago. It's Vasilevich. I can send it, but you can find it.
There seem to be some differences here. You see, because in the high energy regime, I simply do not get a metric. The very notion of a metric no longer exists because I can only get the metric if the endpoint functions for n larger than 2 actually are exactly diagonal. If they're not diagonal, then I don't get exactly a metric anymore. At best, an approximation to it. But still, it would be very interesting to work out what the similarities and differences are there between those two approaches. And then regarding spectral geometry of the drum, it's very hard. This was just some intuition. I don't mean that. What happened? Okay. I just heard somebody speak there. Right. So no, I don't mean that we should hit the drum really hard. The thing is the situation is different here, because in the case of space-time, we don't need a stick to hit the space-time to vibrate. It's the quantum fluctuations that make it vibrate everywhere all the time. automatically. And that's what we do want to hear. We don't want to hear a stick, but we do want to hear the noise of the quantum fluctuations, right? I mean, the intuition is, of course, that from old spectral geometry, the intuition is that if we can hear the ringing of a manifold, then we can tell something about the shape of it. And here now, what I'm saying is that if we can hear the quantum noise, not exactly the spectrum of it, but the correlations between the quantum noise that happens, then again, the quantum noise is affected by the curvature to the extent that knowing just the quantum noise and its correlations allows us to reconstruct what the geometry is. And it's not as easy as just really hitting the drum harder. You're right. I mean, that is a too simple picture here. But what I really meant was that you need the higher point correlation functions in order to be able to do it. And typically, it's because the higher point correlation functions, at least at low energies, are diagonal in a positional basis. And once we have the positional basis, we can then write 2-point correlators in the positional basis. And from there, we do have a reconstruction formula for the metric. So it's strictly true that if you have the endpoint correlators for n larger than 2 and the correlator, then you do get the metric out of it. Whereas, yes, it's true that if we go to spectral geometry and you just take a drum and you hit it very hard, well, then you have here self-interactions, but it's not the same to just listen to a drum that's drumming non-harmonically than doing what I explained for the quantum field theory, where you take the endpoint correlators and diagonalize them as operators, then identify which basis to use, and then in that positional basis, write down the propagator from which you can then reconstruct the metric. So I was shortcutting things too much, and you caught me out. That
okay, no,
it's not just hitting it hard.
No, just a final suggestion. Mathematically, the Dirac operator is slightly better than the Laplacian, but there are isospectral manifolds which are isospectral for the Laplacian but are not for the Dirac operator.
Oh yes.
However,
I know, but Fedele, I read about this and I studied this quite a bit. You're absolutely right on this. But remember that in this case here, it's actually pretty dramatic, because if you take the spectrum of the D'Alembert operator, it contains virtually no information. D'Alembert operator, typically because it's a hyperbolic operator, has just the real line as its spectrum. And then if you put a cutoff, then you have a cutoff spectrum of the real line. The spectrum is super poor in information, and yet we can still reconstruct everything. And the trick is that you need to know how to go to a positional basis. Because if you can take your propagator and rewrite it not in its eigenbasis, which is what you do when you have its spectrum, if you can go from the eigenbasis to the positional basis, then you have the propagator in the position basis, and from there you get the metric. So it's actually a pretty complete reworking of spectral geometry, because the spectrum itself doesn't matter that much anymore. It can be just a chunk of the real line. That's all. The point is that you need the information of how to go from the eigenbasis of your operator to the positional basis, because then you have to propagate in the positional basis, and from there you get the distances, and from there, therefore, you get the metric.
We can have a chat after some time after this conference.
Absolutely.
It will be a pleasure to virtually see you again. Thank you very much. That's all.
Thank you.
So I think after that we have Nikolaos Kalogeropoulos. I don't know the pronunciation.
You're muted.
No, it's okay. It's okay. It's fine. So can you hear me?
Yep.
Yes.
Okay. Sorry. Let me make a disclaimer, if you do not mind, before I ask anything. I am not asking for anything rigorous from a mathematical viewpoint. Still, especially invertibility makes me feel, allow me to say, uncomfortable. For instance, you said that you can reconstruct. You showed a very nice formula, the metric from the 2-point correlation function, essentially. I'm not so certain whether you can do that without knowing distances. Because the question is, for instance, how do you take the limit? What is the definition of a limit if you don't have any distances. Of course, you can do it with a topology, but the topology has to basically also depend on the correlation function, right? And if you are in a sort of positive definite metric space that has a positive definite distance function, you may be able to compare topologies, but if you have something which is not really in any strict mathematical sense a metric, because as you know, Lorentzian metrics are not metrics if you ask a mathematician, because they violate pretty much everything. I'm not certain whether you can do it.
Okay, so a very good question, and let me give you a brief answer, but what I talked about today is a paper that was just recently accepted in the Frontiers, and thanks Časlav, he was the editor of the special issue there, and I will put it on the archive in the next few days. And your question in particular, I was happily addressing there in a few paragraphs, but the gist of it is this, that yes, in the Lorentzian case, we have two notions of distance here. We have the notion of distance that we need in a differentiable manifold to define epsilon neighborhoods, to define differential, and so on. Yes, I still have that notion of distance, the notion of distance that is coming, that is needed to define a differentiable manifold. That is just coordinate distance, right? And it doesn't require a metric to do it. In order to do derivatives, we don't need the metric. We only need that we have these epsilon neighborhoods that we can define continuity. Right. So that we still have. And then in the next step, we get rid of it by abandoning the concept of a manifold altogether, by describing everything in terms of the abstract correlation function.
So then you essentially do what people do in algebraic geometry, in which essentially you replace an algebraic structure or a differentiable structure in this by the set of functions having some particular properties on it, and you work essentially with some abstract spaces, some functional spaces.
Yes, that's right. The set of functions, but it's true, the set of functions, but more than that, it's the set of operators on that function.
Right, correct.
But not the algebra of all of the operators on the set.
Right.
But instead, it's in particular those endpoint correlators. They determine.
If I can ask.
Similar. The spirit is very similar, that you go from a differentiable manifold structure to something that is expressed in terms of algebraic properties of function spaces over that.
Now, I think I have seen something similar, but of course in a Euclidean domain. Therefore, what you say is totally different. And it is, I don't challenge at all the originality of the idea. I think I was reading a paper 5-6 years ago from some people in Chicago, in which they basically use the Green's metric for something which mathematicians call hyperbolic spaces, which is different from globally hyperbolic. I'm sure you know the negative sectional curvature things. And they have used this for boundaries of hyperbolic spaces and so on. The last question is, and again, this may appear probably too mathematical. Locally, I have no problem, or I could easily accept everything that you say, but globally, especially if you allow topology change, there are things, as you know, that are extremely difficult to determine, and also in principle cannot be determined. There are undecidable things that are associated with the fundamental group and so on. And so if you go to this space of correlations, I am afraid you are going to lose all of it, which, by the way, may have absolutely no meaning whatsoever for physics. It just happens that I don't think we know that, even in a conventional sense, right? That's what.
Yes, I think you're absolutely right about that. I have not considered the case of non-trivial topologies in the sense not of epsilon neighborhoods, but in the sense
right. Homotopy theory and stuff like that.
Yes, I mean, of course, spectral geometry is in principle sensitive to this, right? You know that the
maybe yes, maybe not. I know Sunada's constructions that are isospectral, but
yes. But of course, it's also known that you don't get much more than the Bethe numbers from the spectral geometry. So you don't get. I think that was your point. The spectral geometry, the traditional spectral geometry, doesn't recover everything about the topology of the manifold. It tells you something, but not everything. That's right.
Last but not least, again, I think I have monopolized everything, and I have to apologize. You said that the unitary group is smaller than the diffeomorphism group.
No, it's larger, way larger.
Larger. I was under the impression that the opposite is true.
Yeah, exactly. The unitary group is way larger than the diffeomorphism.
I thought it was the opposite, right? Because diffeomorphism is pretty much reparametrization.
No. Look, for example, yeah. But yes, but it's not enough. Consider, for example, quantum mechanics, first quantization, right? Now you can change coordinate system, right? If you change coordinate system in your three-dimensional quantum mechanics from Cartesian coordinates to polar coordinates and so on, you can represent this as a unitary transformation, right?
Right.
So coordinate changes are unitary transformation. But how about a Fourier transform? A Fourier transform.
But the Fourier, no. But the Fourier transform takes place in the cotangent bundle. It doesn't take place on the manifold. Because you have X and B's,
exactly.
Right?
That's the whole point. In the function space that lives on our space-time, that function space, you can do it.
Oh, it's a lift. Okay. Then I have no.
So you can do a Hermite transform. You can do.
Yeah. If you do a lift,
that's what I mean.
Okay, if you compare the diffeomorphism of the ground thing of the space-time, if you want, with the unitary transformation of the lift in some other space, absolutely, you are right. 100% you are right.
Exactly.
And I stand corrected.
Yes. And you see what this means is that while in general relativity we focus on on the diffeomorphism group, in quantum mechanics we routinely use the entire unitary group. And I'm that we upgrade GR to that as well.
All right. So
I think Patrick wanted to do some comment or question. You can give space to everyone. Patrick, you can.
Achim, thank you very much for a nice talk. It was really nice to hear it. I would have just one more or less technical, maybe technical questions. First, I wonder, was the partition function the only thing you aim to compute? Because for quantum theory or for quantum field theory, much more fundamental is generating function, which has sources with respect to which you can take functional derivative in order to get whatever expectation value you want to have. How you would, for example, define this generating function for green functions?
Yes, I'm very happy about your question. If you remember, I alluded to it a little bit in the very last thing that I said in my talk. You're right, of course, that what we want to do is have Schwinger sources so that we can then calculate everything, not just the partition function, but the expectation values of everything. And that amounts to doing the full path integral with Schwinger sources. And this process is usually mathematically quite ill-defined. The path integral is something that we write down and just pretend that it's well-defined when it's not. And that's why I have had a project for years actually with my colleagues Alejandro Morales and David Jackson, who are combinatorialists. And what we have done is this. We have, first of all, identified that the path integral is nothing but a Fourier transform. I mean, this has been known for a long time, but people don't pay much attention to it. But if you look at the path integral with the Schwinger sources in order to get the generating function, it is just a Fourier transform. And so it's a functional Fourier transform though. And so what we did is we made the Fourier transform more robust. And how do you do it? How do you make the Fourier transform analytically more robust? What we did is this. Imagine you want to Fourier transform a function. You can do it the usual way, but here's a new way. Take your function and expand it as a power series, a Taylor expansion of it. Now your function can be represented by its Taylor coefficient. Now consider the Fourier transform of your function and Taylor expand it. Now that resulting function can also be expanded in terms of the Taylor coefficient. So overall, the Fourier transform can be viewed now as a map, as a linear map of Taylor coefficients into Taylor coefficients. Function to function, Taylor coefficient to Taylor coefficient. But you see, mapping Taylor coefficients into Taylor coefficients is something very robust. It's basically a matrix operation, right? Now, it's not quite as easy as I make it sound here, but this is an operation that you can do. And what we showed is that the Legendre transform and the Fourier transform can be viewed as maps of Taylor coefficients to Taylor coefficients. Why is that important? Well, you see, when you have a Taylor series, it may or may not converge. Coefficients will be finite. what we have is we have reformulated the Legendre transform and the Fourier transform, and therefore the path integral, as maps of Taylor coefficients into Taylor coefficients, irrespective of whether the Taylor coefficients correspond to a series that has a finite radius of convergence or not. In quantum field theory, typically our generating functions are divergent. They have a zero radius of convergence. The coefficients of these expansions are the endpoint functions, for example, are the coefficients in the action, the exponentiated action. The coefficients are finite and make sense. So what we did is we reformulated the Fourier transform, which is the path integral, but also the Legendre transform, in such a way that it's just a map of the Fourier coefficients, of the Taylor coefficients into Taylor coefficients. And that map is more robust than the usual analytic Fourier and Legendre transforms, because it doesn't matter anymore whether these Taylor series are convergent or not. So we have a generalization of the path integral, even when what we are path integrating is not itself finite, as long as the Taylor coefficients are finite. And so that's a paper that we are going to put on the archive also within the next few days. Everybody muted?
No, yes, I think Peter muted. You can unmute now. Okay.
I think Gabriele still had a question.
Peter, okay.
Yes,
Question in the meantime.
Can I speak?
Yes, sure.
Okay. Achim, nice talk. I have a very simple question, maybe naive, but don't you think that in a reference frame, you always need a rod and clocks to make measure? So in some sense, you are not avoiding the problem. I mean, it's a general question, a conceptual problem.
Yeah, well, remember that I'm trying to no longer have to use coordinate systems or reference frames.
Okay.
I want to just have abstract correlators. And ordinarily, at low energies, those correlators will be representable as the field correlators of fields that live on a space-time manifold. But at very high energies, it would be just abstract correlators between abstract things, abstract events that we can't even think of as living in the space-time or belonging to matter degrees of freedom. It would be just abstract correlators.
I see.
So fundamentally, there would not be such a thing as exact coordinate systems, exact reference frames.
Okay.
It would only be approximations that are pretty good approximations at low energy.
So if I understood well, you should use these elements to perform measures? I mean, something like...
regarding measurements, the quantum fluctuations of a field can actually nowadays be measured. In quantum optics labs, you can rig a so-called quantum homodyne detector, for example, pretty quickly. Doesn't even take very expensive equipment. And with that, you can measure the quantum vacuum fluctuations of the electromagnetic field. And you can measure them here, and you can measure them with another apparatus over there, and then you work out what the correlation function is between the, there you have your 2-point correlator, and then you can, once you measure out your space-time using these two gadgets, you get the 2-point correlation function, and then in the limit, we have to differentiate it and take the coincidence limit. In principle, you can map out the manifold in this way.
Manifold in this way. Okay, thank you.
Okay. I will give space to, I know there are other comments, but to Giulia Mazzola, which... Yes.
Thanks. I also have a maybe conceptual naive question, but I was wondering, when you start with the correlation functions, do you already assume that you have, like, you start off with the Hilbert space, or what is the first thing you start off? And if you start off with the Hilbert space, because I'm thinking about, if you start with a manifold and look at space-time, then you kind of get to a natural Hilbert space, natural to, I don't know, like Killing field. But if you already start off with a Hilbert space, then what is your natural choice there? And does it even matter, the choice that you've made, that, or don't you need that in order to define your correlations function?
So in my talk, I started with a space-time and with a metric on it, and then reformulated that in terms of the correlators. And then I said, well, let's focus on the correlators themselves, and found that the correlators can be used as abstract objects from which you can then recover a representation in terms of matter fields living on a space-time. But in principle, everything can be expressed in terms of abstract operators, which are the abstract endpoint correlators. So I went from the concrete matter fields on space-time to this abstract description. And then I said, well, this abstract description might survive to the Planck scale, where it doesn't have a representation anymore on as quantum field correlators on the space-time. There, in the abstract regime, it's just correlation functions in the sense of operators on a Hilbert space. And yes, it would be a Hilbert space. It would be operators that act on that Hilbert space. But in that regime where we no longer have a representation as quantum fields on the space-time, it's really just that. It's just an abstract structure. It's just a Hilbert space and operators acting on them. And they don't have an interpretation at this stage of what is matter, what is space freedom. There's just no distinction between this anymore. It's just correlator operators acting on a Hilbert space. And then if we are lucky at low energies, that is representable as matter fields on space-time, but in general, it would not be.
Okay, so can I view it as like a generalization that hopefully if it's true, then in the limit, like some classical limit, it reduces to what we would consider as the natural Hilbert space. That's and the natural.
Yeah. That's right. In the low energy limit, the Hilbert space would be the Hilbert space of functions that we sum over into path inequality, and then we know what everything is there.
Thanks.
Okay, we have a comment from Alessia.
Yes. So hi, Achim. So I have several comments and questions about your work. So first, I kind of don't understand what are the pros of using correlators instead of a metric, for instance. Second, I think that intrinsically you have a metric there. I mean, any scalar is defined with the metric. The box operator is defined with the metric. In addition, you are trying to convert the path integral that is over geometries, so over metrics, in a path integral that is written in terms of some eigenvalues. And doing this, there should be a non-trivial Jacobian that I'm not sure you're taking into account, and you're not taking that into account, so you're probably switching to a different path integral than the original one. You also are using some weights function, and you say, from what we know, we can use the action. But what is that action in the case of general relativity? Because if you're using just Einstein-Hilbert without a cutoff, all of your correlators will be ill-defined. If you add the cutoff, then I don't see why we cannot just use effective field theory. And if you know instead what is a fundamental theory which makes all of your correlators well-defined, then I do not see why I cannot just use what I know, quantum field theory and general relativity. These are, say, the main questions.
Alessia, how am I supposed to answer all of these? It's like 6 or 7 of them. How am I supposed to remember them? So, okay, good points. Okay, so let's see with the first one. The first one was, what is gained by going to the 2-point correlator instead of using the metric? Now, the metric is a covariant symmetric 2 tensor, and that's what it is. Whereas it doesn't have a meaning in terms of an operator. But the 2-point correlator is not only differential geometrically speaking, it is also an operator. It is the right inverse of the D'Alembert operator. As such, it is an operator acting on a Hilbert space of fields. And as such, it is natural to calculate its eigenvalues, and these eigenvalues will not only be invariant under the diffeomorphism group, they will also be invariant under the full unitary group of that space. That's why it's advantageous to give up on the metric and to work with the two-point correlator instead, because it's an operator. Ultimately, it goes back to a very simple intuitive picture here. You see, the language of general relativity is differential geometry. The language of quantum mechanics, of quantum theory, is functional analysis. So in differential geometry is all about the metric, and differential manifolds. Functional analysis is all about operators and their spectrum. Now, spectral geometry is the discipline that links the two, that links differential geometry and functional analysis. And that's what I do here by going from the metric to the two-point correlator, because the two-point correlator is an operator. It has one leg in the differential geometry because you can get the metric from it, but on the other hand, it has a leg in functional analysis because it's an operator. So in this way, I'm linking differential geometry and functional analysis. After all, whatever the fundamental theory of quantum gravity turns out to be, it must, in the lower energy limit, reduce the general relativity, which is differential geometric, and to quantum field theory, which is functional analytics. So somehow the two disciplines must be combined, and that seems to be the shortest way to combine them. And then you seem to have a question, I don't remember exactly how it went, but you said that the metric is still contained in there somehow.
Yes, because you have scalars like a box operator or any
that's right.
scalar that you can.
Yes, you're right. Of course, the box operator, if you write it, if you write the Danon version as an operator in the positional representation, then it's full of the metric, for sure. But you see, you can also view the D'Alembert operator as an operator on the Hilbert space of fields. And as such, it has a spectrum, has an eigenbasis, and that describes it too. And you completely describe what an operator is by telling in a basis what it is, in particular by telling in an eigenbasis what it is. So doing that is equivalent to writing down the metric, it's equivalent to it, but it's not writing down the metric. It's a complete reformulation of it. You never have to refer to the metric at any point. You don't have to reconstruct the metric anymore. You could, for example, you could express the Riemann curvature tensor entirely without referring to either Christoffel symbols or the metric. You could describe the Riemann curvature tensor entirely in terms of just two-point correlate. And similarly, you can write the D'Alembert operator entirely as a differential operator without referring to the metric, but only in terms of the two-point correlator and derivatives, of course. So you can actually do this. And then you had about 3 or 4 more questions. I don't remember them all.
Yes, so for instance, when you switch from one path integral to the other, are you taking into account like the Jacobian? Is this a one-to-one map? So you are describing exactly the same thing?
Good question, but do we have to path integral in the usual representation? I don't think we have, because what we would have to have is a way to mod out the diffeomorphism group for that. So basically, what I'm saying is I'm writing things in a diffeomorphism and indeed unitary group invariant way first, so that it's just isolating what are the degrees of freedom of the Campbell field, what are the degrees of freedom of the gravity. Then I write the path integral in this way, and that's what I start with. And if I could write the path integral in a straightforward, non-ambiguous, explicit way in a positional representation, I would do it. But we've tried for 100 years to do it. So, I mean, you're right, in principle, you can take a path integral, write it in one basis and write it in a different basis, and you get a Jacobian in general, and then, you know, just like in non-abelian gauge theories, and you get this Jacobian, and the Jacobian turns into ghost fields and all of that. In principle is the case here too. You can write down, I mean, what I wrote down could be written in any basis, and then there would be a Jacobian, and then that Jacobian might lead to ghost fields in the one or the other representation. All of that still holds true. It's just that I use as the starting point a formulation which is not just diffeomorphism, but also unitary group invariant. And as I said, it's a starting point. And then from there, you can go to other representations.
Yes, it's just that I'm not sure that if you start with another path integral, what you are reproducing is the same space of theories that you would have by integrating over the space of metrics. So you are generating more, you are generating less. I don't know.
Well, I hope it's not the same, because otherwise it wouldn't be new what I do.
Okay, so you are probably doing something different. You are modifying the theory,
So,
even at the classical level.
well, yes, in particular, I think I am, because remember that I'm not just writing down the Ricci scalar as the action, but instead, by writing the gravitational action as the leading constant term in the trace, I'm implicitly writing the Einstein action plus a cosmological constant plus higher order curvature terms.
Okay, so you also have a, yes, but yeah.
Sorry, I don't want to stop you, but I think that in 5 minutes we have to start the next session. So I think I will be very happy if you want to participate to the last discussion session where you can continue. After the discussion of the session 3, you can continue freely. So
okay.
I hope you enjoy it, participate then, but we stop now for 5 minutes and then we start the first section. Thank you very much.
Thank you.
Alessio. Ah, you're muted, sorry.
Yeah, hey.
Nice whiteboard.
Ah, yes. I love it.
This is your room, right?
Yes, my apartment.
Wow, okay, that's nice.
So, Luca, are you in Tokyo or you?
Actually, in Kyoto.
Okay.
I came to visit Francesco.
Uh-huh. Fedele.
Ah, sorry. Okay.
This is unfair. You have chats in the break. Only organizers can decide who to chat. Anyway, yeah. it's a way to say hello to Alessia and other friends. So you are in Kyoto, so 7 hours ahead of us, no?
Yes, 7 hours. Yeah.
Okay, my wife is in Japan as well. And,
okay. Where?
She's in the north of Honju, in a place called Rokasho. It's nobody knows it. In the Aomori prefecture, is the place where it snows the most in the world, according to something. And Syracuse, where I was, is only the 5th. So after having boasted that I was in the most snowy place, I discovered that it's only the 5th. And above the lakes, Alessia doesn't qualify because it snows much less. The lake has an effect so that Rochester, Syracuse, Buffalo are more snowy. And Aomori, because of the sea between Hokkaido and Honju, makes the same thing. There is air that comes over land and then gets a body of water and makes more. So for you, it's quite early, it's quite during the night, no?
Yeah, what time is it? Yeah, it's still early, I would say. It's still 5 past 1. Yeah.
Okay.
Last night we finished at 4 a.m. basically, 4 and something.
Talking about jet lag.
Okay, Gaetano, I think you can. Yeah.
Instead, I can see that in Waterloo the weather should be good. or the central heating is very strong, because I can see Alessia.
Yes, I mean, so the heating somehow is off, but I feel warm.
Okay.
I always feel warm inside. Of course, I would not go outside like this.
No, because you're also like us. You are from southern. You're a southerner, so we are not that used. I mean, I have friends in the north that in the snow with short sleeves. But no, we are like us. This is what really people are missing. What I'm missing more in conferences is the chats for the coffee break and dinners and things. I started many papers in these kind of situations. In fact, the one that I was talking with Achim, with Dima Vassilievich, who lives in Brazil, was started in Corfu, I think, over coffee breaks. So the exchange, scientific exchange, is more in off the talks than the talks.
Well, in some conferences, there are these coffee breaks organized on the platform Remo, but still, I think they are not the same as in-person coffee breaks.
It's not the same. It's not the same.
Yeah, I'm sorry to interrupt this very nice conversation.
But we start again, of course.
It's time to start. It's time to start. Yeah.
Sure.
Okay. Perfect. So welcome to the last session of the second day. And in this session, we have 3 speakers. The first one is William Unruh from Columbia University. The second one is Massimo Blasone from University of Salerno. And the last one is Stephen Carlip from University of California. So let's start by the first speaker, William Unruh, who will talk about the frequency interferometry and experimental acceleration radiation. So Bill, you can start. Okay. Okay, you have 30 minutes plus 5.
Thank you very much. I presume you can see.
Yes, yes.
My transparency. Let's hope all this stuff works. Yeah, so I want to talk about basically it's measurement of acceleration radiation, but there's some neat things in this. This is all in this program of doing analog gravity, finding other physical systems, ones in which we can actually do experiments on, which might cast a little bit of light on the real system, the gravitational system, or whatever. Now, this field has gotten a lot of development over the last few years. For example, trying to see black hole evaporation, what's the equivalent of black hole evaporation in some of these analog systems. Just as Hawking predicted a temperature for black holes, one also gets a temperature for things like sonic holes, or dumb holes, as I like to call them, because they cannot speak. Which also can have horizons if one has a suitably arranged waterfall. This was an example in which one did the classical or the stimulated emission for the system by having water flowing in a tank over an obstacle. Over the obstacle, the velocity of the water is higher than the velocity of the surface waves in the water. And that then acts like a horizon, in this case, a white hole horizon, as it comes off of that top of the horizon. And one can then send waves in as per stimulated emission. And Einstein taught us that stimulated emission and spontaneous emission are very, very closely linked to each other. That if you know what the stimulated emission is, you also know what the spontaneous emission rate is. And the Hawking radiation is just the spontaneous emission rate from one of these horizons. So this, for example, was an experiment that we did in which we showed that if this horizon were to produce thermal radiation, then this factor R, which I have there, which is the square of the Bogoliubov coefficients, should be a straight line in a log plot. And I think the x's are the actual measurements, and the straight line is the best fit. That best fit gives us a temperature of about 10 to the minus 12 Kelvin, which this is done with water. We immediately realize that we will never see the spontaneous emission rate from the system, but we get a very nice exponential behavior for the stimulated emission, which tells us that it should be a thermal system. The experiment has been done in the quantum regime as well. For example, this is one of Jeff Steinhauer's early papers in which he generated a waterfall in a Bose-Einstein condensate and measured the spontaneous emission, in this case, from that waterfall, from the horizons of that produced by that waterfall for the sound waves in the Bose-Einstein condensate, and found something which was at least consistent with a thermal emission. The errors are too large for me to really be able to say that you can see a thermal spectrum, but it's not inconsistent with a thermal spectrum. Now, there's another effect that in the paper that I wrote just after Hawking presented his results, where I argued that I was interested in understanding what in the world were particles in a quantum field theory. And I came up basically with the mantra that a particle is what a particle detector detects. It at least focuses the mind in a different direction than one usually did in trying to understand what particles are, which were very mathematical sorts of descriptions, doing Fourier transforms, looking at the time dependence of those Fourier transforms, etc., to define what particles were. In this case, one uses an experimentalist definition, which is you grab a particle detector, which works properly in regimes in which you understand it. For example, you send particles at it and you see whether or not it clicks. And put this in an unusual situation, for example, by sticking it near a black hole. Or one of the interesting cases is by accelerating it and discovering that it produces it clicks as though it were immersed in a thermal bath. So this is, for example, a brief sketch. The detector in my paper was basically a particle in a box, which has various energy levels, and one can ask what is the probability of being excited from the bottom, from the base energy level to one of the excited levels. Bryce DeWitt then generalized this idea, basically going back to Glauber, who had also worried about what is a photon in quantum electrodynamics as an elementary two-level system, which if one excites that two-level system into its excited state, that means that it's detected a photon. And one of the amazing results that certainly surprised me was that this thing behaves, if I accelerate it, exactly as though it were immersed in a thermal bath with a temperature proportional to the acceleration. Unfortunately, if you stick in the figures, you need an acceleration of about 10 to the 23rd centimeters per second squared to get 1 degree Kelvin temperature. So it's really, really hard to measure. Can this be measured in an analog system where, for example, the velocity of light is much lower, the accelerations therefore need to be much lower? For example, we know that sound waves in a fluid, let's say like a Bose-Einstein condensate, have a spectrum which, at least at low frequencies, looks the same as the spectrum, the relativistic spectrum that one gets in for example, quantum electrodynamics for the electromagnetic radiation. Now, if one had to do constant acceleration for this, of course, the velocity would very rapidly approach the velocity of sound in the analog system or light in the other one. And you need many such time scales in order to really be able to measure the particles. And that's very hard to keep the detector in the lab. If one accelerates this particle, it very rapidly is traveling at the velocity of light. And even in the biggest lab that one can imagine, this particle detector would very rapidly shoot out of it and head off towards the moon or Jupiter or wherever on timescales of less than a second. The second problem in the analog systems is that the effect depends not only on acceleration, but also on relativistic time dilation. And part of the problems in the analogs is that there is no relativistic time dilation. Time in the analog, time for the detectors, is simply ordinary Newtonian or Galilean or whoever you want time. It's not a relativistic. It doesn't give you the time dilation with respect to the velocity of sound. Finally, analogs have a very non-trivial dispersion relationship, especially at high frequencies. Although they look like a relativistic dispersion relationship at low frequencies, at higher frequencies, they don't at all. In a Bose-Einstein condensate, the velocity, either phase or group velocity, increase much higher than the velocity of sound at low frequencies. In water or fluids like that, the dispersion relationship folds over and the group velocity crashes down to, at some cases, down to zero. So that dispersion relationship could mess things up, and says that your experiment wants to be done at low frequencies where this thing models a relativistic system. Now, in 1983 to 1985, Bell and Linnaeus looked at circular acceleration. Circular acceleration is another case where one gets constant, at least magnitude of acceleration. And they asked themselves, is it possible that that system also has the same kind of effect? Now, the behavior of particles in, for example, a storage ring had been analyzed already in the 70s by people like J.D. Jackson. They found a result. If they looked at the spin of the system, they found that they couldn't polarize the electron, let us say, completely. It also had some depolarization in it. And Bell and Linnaeus said, could that depolarization be interpreted as the spin of the electron acting like a thermometer for this thermal bath that is caused by the acceleration? And the answer was yes. If one looks at the electron storage rings that one has, you get acceleration temperatures of about 1000 Kelvin, which is a lot better than linear acceleration. The spin of the electron in the storage ring is a two-level kind of system, just like this, the UDW kind of detectors. And the measurement of the depolarization of the spin gives the temperature. I gave a talk on this in one of Piss-and-Chen's Monterey meetings in the 90s, and J.D. Jackson was there, and he just didn't believe it. And one of the reasons he didn't believe it was that the depolarization of the spin doesn't look like a thermal function of the G factor, the ratio between the the magnetic dipole moment of the electron and the spin of the electron. It doesn't look like a thermal function of the G factor. And I redid the calculation and discovered that there are essentially two thermometers in that system. One is the spin, and the other one is the oscillation of the detector in the Z direction. The Z direction is like a harmonic trap, which keeps the electron on its planar path around the storage ring. And that Z oscillation is, it's like a harmonic oscillator with multiple levels. It also acts like a thermometer. And the problem is that the Z oscillation has accelerations associated with it. The particle bounces up and down in that trap. And those accelerations, just due to the Thomas precession, cause spin flips in the electron. i.e. you get couplings between these two thermometers. And since they're coherently excited by exactly the same electromagnetic field, it's the electromagnetic field in that storage ring, not the constant one, but the wave electromagnetic field that excites both of those guys and makes it look like you've got a thermometer. And it's the interference between the two that gives the wiggles in the curve that Jackson was concerned about. For example, down here, this thing doesn't look very much like thermal. Thermal should just basically be a tangent function. This is displaced from 0 by a small amount. This part of the curve is different from this part of the curve. So that doesn't look like a thermal factor. And what I showed was that this arose precisely because of these interference between these Z oscillations of the electron in the storage ring and the spin flips of the spin of the electron itself. However, the circularly accelerated particle really does act like a thermal, as if it's seeing a thermal bath. A thermal bath which doesn't have the same temperature at every frequency. It's a thermal bath which has a mild change in the temperature as a function of frequency. So that if one, and the problem is that the G factor both determines the energy splitting of the electron, which gives the frequency, and it's also caused by the same magnetic field that bends the electron in the storage ring and therefore gives the acceleration. So that the electron really only is sensitive to a single frequency in this thermal distribution. However, one could imagine changing the G factor. In nature, that's pretty hard to do. Although you could, for example, take different atoms which have very different nuclear G factors and accelerate those. And so get spot measurements on this curve. But this at least theoretically shows one what's happening, and it really is looking pretty thermal. This temperature at low frequencies is within about 20% of the temperature it would have with exactly the same temperature, but being linearly accelerated. At high frequencies, it comes more like a factor of 80 or 70% rather than just 20% at low frequencies. Notice that it's often claimed that the temperature of an accelerated detector is due to a horizon, and there is no horizon for circular acceleration. So it's not the horizon that gives one that temperature. That's just an aside. How does one measure it in an analog system? One needs a system, and in our case, we're going to look at a Bose-Einstein condensate. We have to accelerate that detector, i.e., we have to drag it through the fluid. And by grabbing a hold of it and dragging it, one is almost certain to start causing excitations in the fluid. And this makes the measurement of acceleration radiation, in fact, much harder than it is for measuring Hawking radiation, where one does the measurement far away from the horizon. The detector one places very far away from the horizon, which produces the radiation. And so one doesn't affect the flow of the fluid near the horizon where these particles are being created. Now, one of the examples of a comment that we just heard in the break is Jörg Schmidtmeyer and I were at a workshop in Nottingham that had been organized. And in the hallways afterwards, chatting away, Jörg said, could we use a laser to somehow measure it? And my immediate reaction was sure. And it took us a few years, and it's now been published, to show that that was actually right. And it's a new kind of detector, or rather it's a transducer or a transformer, in which one transduces the sound waves in the fluid into light waves, frequency modulated white light waves that come out through the from going through the BEC. The second thing is that we had to invent a new kind of interferometer, an interferometer in frequency space rather than in real space. The two arms of the interferometer are the light traveling at two different frequencies rather than along two different paths in real space. So the detector is a laser spot, and that laser spot is swept over the Bose-Einstein condensate. The density of the Bose-Einstein condensate at the laser spot gives a phase shift because of the refractive index of the Bose-Einstein condensate and the polarizability of the atoms inside the Bose-Einstein condensate. And so the density as a function of time at the laser spot is transferred into phase fluctuations in the laser beam that went through the BEC. And the laser beam is a coherent beam at some well-defined frequency. And so one can measure these phase fluctuations, the frequency modulation, if you will, of the laser beam as a measurement of the phonons in the Bose-Einstein condensate. There's no two-level system. It's rather like a multi-level system because this transducer operates over a wide band of frequencies, from low frequencies, hertz, up to high frequencies, let's say kilohertz. That's all we're interested in the Bose-Einstein condensate, is that there's very, very low frequencies. So it's a very broad band transducer rather than a single energy level kind of transducer that the usual detectors have. The second thing is that the polarizability of the medium depends on resonances. And as we all know, when we shake a harmonic oscillator at low frequencies, the oscillator moves with one's shaking of it. So if I'm wiggling the support of the oscillator just moves with that shaking of the support. At high frequencies, they go in opposite directions. It's out of phase. So by going on either side of a resonance in the atom, one gets that the refractive index of the medium goes from being a positive refractive index to effectively being a negative refractive index. And so the result of the shaking means that these lasers at these two frequencies are sensitive to the density fluctuations in opposite directions, which is great because we know from LIGO, which is sensitive to the phase shifts, the frequency modulation due to the motion of the mirrors, it's because those two mirrors are moving in opposite directions that one can cancel out large amounts of the noise introduced by the laser and so forth. So what we can do now is to split the beam, not spatially. We want this beam to go through exactly the same part of the Bose-Einstein condensate because we want to measure the density fluctuations at that point in the Bose-Einstein condensate. But we now have two laser beams, one at a higher frequency than the other one. This is great because we can use that to balance the forces on the medium. One's always heard about laser tweezers. Well, laser tweezers are exactly operate at a higher frequency than the resonance in the object that one wants to grab a hold of, so that the laser beam attracts those particles into the laser beam because the refractive index is lower. And so by having these two beams, one higher and one lower, the forces on the medium cancel out so that the laser beam doesn't affect the Bose-Einstein condensate as one waves it around in the Bose-Einstein condensate. And the effect of the density fluctuations is an opposite sign, and one can use that to cancel out noise sources in the laser beam. This is just the same as in LIGO, where one is looking for differential motion of the two ends of the laser beam. When this one moves in, this one moves out. That's what that's what LIGO is sensitive to. You shine a bright laser beam in it, and the motion of these endpoint mirrors frequency modulates or phase modulates the reflected beam. By running it through an interferometer, you can therefore look at the output port of the interferometer and see fluctuations, amplitude fluctuations in the signal coming out of this output beam, and therefore measure what the difference in path length is on the laser. Similarly, in our case, this is the paper which has now been published in PhysRev Letters, where we want to do this for a Bose-Einstein condensate. We have a laser beam coming in here. We have a modulator which splits it up into two separate frequencies. We filter out the center band so that that's not going to affect the Bose-Einstein condensate. We shine these two beams through the Bose-Einstein condensate. I've got them, these beams follow exactly the same path. And we can now go ahead and sample the Bose-Einstein condensates at different points by simply moving the laser beam around. For example, a little deflector here, which deflects the beam onto the circular trajectory. And so we can therefore sample the BEC at different points, at different times, just as though this were a detector that was moving on a circular path inside the Bose-Einstein condensate. And one can easily get this beam to be traveling in such a way that it's traveling at the velocity of sound or just under the velocity of sound waves in the Bose-Einstein condensate, i.e. getting the super relativistic behavior of a detector being accelerated in a circular beam. We then recombine the beams with this lens onto a photodetector and look at the oscillations, the amplitude oscillations, in particular at frequencies of twice this omega, the frequency splitting that was introduced in the modulator, which is going to be, let's say, at microwave kind of frequencies, gigahertz. The laser is, of course, at 10 to the 15 hertz. The splitting is at the gigahertz range, and one is looking for the fluctuations at the hertz range, from hertz to kilohertz kind of range. So one has well separated frequencies that one can look at, which is an incredible advantage in this system. So this acts like the half-silvered mirror in the laser interferometer.
Sorry, you have 5 minutes left. 5 minutes.
Thank you. This operates as the gets rid of the center band. The two frequencies are the interferometer, and the photodetector is the combination. And by looking at twice this modulation frequency is like looking at one of the ports of the interferometer, which is separate, which is sensitive to the difference between the two beams. So in frequency space, it just looks like this. The electromagnetic field before and after, I can expand it. These are the annihilation and the operators, and the Hermitian conjugate are the creation operators for the electromagnetic field. When it goes through the BEC, when it goes through the BEC, that causes a phase shift. And if, for example, we model the BEC as a Gross-Piatowski equation, then the D of nu are the annihilation operators along the laser beam. And we find that the relationship between the output of the laser, the fluctuations of the laser, and the Gross-Piatowski fluctuations are given by an equation like this. Notice that the side bands, which are of higher frequency than these main frequencies, get damped. Those that are lower get amplified. And these Bogoliubov coefficients is a non-trivial Bogoliubov transformation because it has an annihilation operator here in the Y band and a creation operator. It mixes an annihilation operator with a creation operator, so that acts like an amplifier. The upper band and lower band, however, cancel out on their effect on the of the Bose-Einstein condensate, so they don't affect the Bose-Einstein condensate except to add a little bit of extra noise. This is a sort of a diagram of these various frequencies. This is 10 to the 15 hertz. This is 10 to the 9th hertz. And this is about 100 hertz that we're looking at here. And these are the X's, the linear combination of this part of the band and this part of the band. This is the Y, the lower parts of the bands. So one also separates the D, the Bose-Einstein condensate effects into the two frequency bands of X and Y. And so one can separately measure the annihilation and the creation operators for the Bose-Einstein condensate. Since I've got 2 minutes left. So this is very similar to LIGO. Unlike LIGO, where the signal is a classical signal, namely the gravity wave that's coming through, in the BEC, it's a quantum signal. One is directly looking for the quantum mechanics of the Bose-Einstein condensate. This noise that one introduces tends to travel away from the spot at the velocity of sound. So we get rid of it by it going away. And if we use reasonable parameters for the Bose-Einstein condensate, we showed in this paper that the signal is probably just detectable, let's say at the level of about signal to noise ratio of 1 to 10, which is great. The detector is not a two-level system. It's broadband. It can measure the frequency fluctuations, the density fluctuations over a very wide bandwidth. And the BE signal is transformed into a light signal over a whole bandwidth. And light is far, far easier to detect than our sound waves in the Bose-Einstein condensate. This is a plot of the signal to noise that we found for some parameters, not unreasonable parameters for the Bose-Einstein condensate, and for the velocity of the laser beam in terms of the velocity of sound running around this Bose-Einstein condensate. So we're getting signal to noise ratio of something like 3, 4, 5, which is certainly detectable. With the next year or two, we should at least be able to get an indication that these parameters are actually all achievable together. All of those parameters have been achieved in separate experiments in Bose-Einstein condensates. The question is making it all work at the same time in one system. So the hope is that in addition to the measurement of black hole radiation in an analog system, we will also have the first measurement of acceleration radiation on a circular trajectory in an analog system, which will help us to understand better what this kind of system works as. Plus, we'll have a very new way of measuring density fluctuations in the Bose-Einstein condensates. Typically, what happens is that one does the experiment, one slams the whole Bose-Einstein condensate with a laser beam or turns off the support for the Bose-Einstein condensate and measures the momentum distribution of the Bose-Einstein condensates afterwards to measure the momentum or to measure the density. One slams the whole thing with a laser beam and looks for the phase fluctuations in the output laser beam as we did, only we're doing it in a single spot rather than in a big system. That, of course, destroys the Bose-Einstein condensate, and we cannot look at the time development of the Bose-Einstein condensate as one can with this technique in one single system. So watch the space for the experiment that we hope to do in the next while, modulo funding, although that's looking really good. And the ability of the experimentalists. Jörg is one of the best Bose-Einstein condensate people interested in correlations in Bose-Einstein condensates, etc., in the world. So I think we've got that at hand as well. So it's very hopeful that soon we'll be able to measure acceleration radiation in an accelerated system as a measurement of acceleration radiation in an analog system, as well as Hawking radiation. Thank you.
Thank you for your very interesting talk. And we have time for maybe 1 or 2 short questions. Well, in the meanwhile, I have a very brief comment. Let me say that I spent most of my PhD working on your effect. So my wish is that please try your best to detect it.
Well, we certainly are trying our best.
Sure.
It's not easy.
Sure, sure.
And one needs graduate students, and one needs to make sure that the experiment is such that the graduate students can actually finish it in a few years. Most graduate students, you know, as with LIGO, when the feeling was that LIGO might detect one event every century or every decade, most graduate students don't want to stick around for that length of time. But if we can do this on a short time scale, like a few years, that's really hopeful that this will actually get done. First of all, what we will try to do is to use this as a thermometer, where one simply looks at one point in the Bose-Einstein condensate and looks for the density fluctuations due to the thermal temperature of the BEC. Since you can't actually cool most BECs down to absolute zero temperature, they will have a temperature of 10 to the minus 10 or something Kelvin. One wants to be able to measure that temperature at a single spot before trying to see the acceleration radiation temperature to make sure that everything works. And that experiment one should be able to do in the not too far distant future. So we're hopeful of at least being able to test this technique in the next few years.
Well, I can see any question from the audience. Guys, do you see any question in the chat or somewhere else? No? Okay, so if there is no question, maybe we have more time in the final discussion session. Let's thank Unruh again for this very nice talk. Thank you, Bid. And let's move to the next speaker, who is Massimo Blasone. And he will talk about neutrino oscillation in the Unruh radiation. So
thank you very much, Gaetano. And in the meanwhile, I shared the presentation. I would like to really thank the organizers, because I'm happy that a group of young people, young researchers, they were actually all students from Salerno University a few years ago, and they've taken such an initiative with also with such a Goliardic spirit, I would say, that they still carry on. Okay, so my talk is about Unruh radiation, but from a quite theoretical perspective, and in some sense, it's will be I will explain a sort of theoretical tool to understand some basic features of neutrinos in this case. This is mainly based on the title is the same of the second of these 3 works we have done with Gaetano, our chairman today, Luciano Pedruziello and Gaetano Lambiase, which are all here. And but other aspects of this work, which I will discuss, have been done in collaboration with mainly Giuseppe Vitiello in the years, and Luca Smaldone and Nick Mavromatos, which are also in this conference, so I would like to mention them as well. Okay. So these are the topics. I hope to be able to say something in all of these sections, but maybe some of the material I will skip for reasons of time. So the first thing I want to talk about is this issue of the accelerated proton decay, which was raised a few years ago as a sort of a theoretical tool, theoretical proof of the existence of auroral radiation, and which is based on work which is not from us, but it's well known. And then we will see the role of neutrino mixing in such a context, and how this relates to a line of research which actually we are carrying on since a long time. This one from my PhD thesis. I can just add to what Gaetano said. And on the other hand, also some particular features, non-thermal characteristic of Unruh effect for mixed particles came before these works that I'm talking about and that they are related to. Okay, let me introduce the topic. The framework in which we work, the arena, comes from this very nice series of work. Here I quote the first one by Matsas, Vanzella, and the collaborators, where they, based on previous work by Müller, they were exploring the issue of the accelerated proton decay to test the consistency of quantum field theory in curved background and having a positive result in the sense that Unruh effect is an indispensable ingredient to keep the consistency of quantum field theory and the general covariance. So this is the main message from their papers. But recently, more recently in 2016, people raised the problem that such a very nice result could be spoiled by the mixing of neutrino, which was not taken into account in the original treatment. And so we entered in this kind of discussion because actually we have for a long time we are considering this problem of the what is really the fundamental entity in the moment the neutrinos are mixed as it appears from experiment, if flavor states or mass eigenstates are the flavor entities. And this is not trivial and has phenomenological consequences, as I will show. So what means proton decay? Proton in the framework of standard model is stable. We have baryon number conservation, and lifetime is at least 10 to 28 years or some like this, so much more than age of universe. But however, as was pointed out by Müller, beautiful paper some years ago, in general, I mean, decay properties of particles are not universal in the sense that if we move to non-inertial frames, they may change. Okay, one can measure different decay rates. Okay, this is clearly a theoretical result. Then accelerations required for this are quite big, but it follows quite clearly, and I think nobody discusses the theoretical validity of this. So in the case of proton, this is particularly strong, this statement, because the proton is stable, and so it could decay in the moment it's being accelerated, as in this nice cartoon by Gaetano. Okay, so in the calculation of Matsas and Vanzella, it's rather simplified because calculations are quite heavy. They become in later on we will see, but they considered a very simple situation, which first of all they consider two-dimensional theory, then they consider massless neutrinos, then they take this condition in order to have I mean, to keep other approximations treatable. And then, of course, if the acceleration is quite small, There are several approximations, I would say. I mean, I don't want to enter in this very much, but current Fermi theory is justified if the acceleration, of course, is smaller than the mass of W and Z0. And at this point, of course, this is not normalizable, but they do the calculation at 3 level, which is sufficient to study the equivalence in the 2 frames. Okay. So basically, the proton and the neutron are represented semi-classically in terms of a trajectory which is the one of an accelerated particle as implied by this delta function. So basically here they do 2 calculations, one in the laboratory frame, which is an inertial frame, in which, according to Müller, the proton at some point, then they integrate, of course, up to infinity and divide by the proper time. And the proton is at some point decaying, and this is the process which is relevant at 3 level in this case. Here the calculations are rather straightforward. This is a matrix element, and this is the decay rate that they consider. Okay, it takes this form. Here the field quantization is the usual one in cosmic space-time. On the other end, in the comoving frame, the proton is at rest. So why it should decay? Since the decay rate here it's an invariant, it's a quantity which cannot depend on the observer. So this should necessarily happen in the other frame, in the non-inertial frame, and in fact it happens, but via completely different processes, which are the absorption and interaction of particles from the Unruh thermal bath. So here now, the calculation involves quantization of field, fermionic field in this case, in Rindler space-time, and in the moment the amplitude is calculated for the 3 processes, convolution of these differential transition rates once integrated with the absorption and emission, I mean the populations of the states which are responsible for the particles absorbed and emitted, and these are regulated by the Fermi-Dirac distribution, and we are talking about the neutrinos and the electrons and the acceleration. So the acceleration here, I would like to point out this technical point, enters in two parts: in the field, because of the Rindler modes here, and in the distribution function, in the Fermi distribution function. Well, one does this calculation, sums up these 3 diagrams, and what they found exactly the same result, first numerically, and then analytically. This was really tour de force by Suzuki Yamada a few years later, in 4 dimensions with massive neutrinos, showing that the result is exactly the same. And so the consistency of the theory really demands, forces us to consider Unruh effect. And this is, I personally find this beautiful. Well, but this idyllic picture was a bit spoiled after a few years, because in this paper, Alwali and collaborators, they raised the point, which is correct. Okay, neutrinos, we know that they are mixed. So in the moment we put the mixing into the game, you see in the first, let me go back, in the first decay in the laboratory frame here, clearly a flavor eigenstate comes out together with the electron here, okay? So what happens in the other frame? In the other frame, we should pick up particles from the thermal bath, and in these particles there are also neutrinos. Well, they argue that here necessarily mass eigenstates should be present because of the KMS condition, which is the thermal condition. Okay, so we did the calculations using the flavor neutrinos. I will try to motivate this choice, and we found similar results to what they have in before, but a new term, which is an interference term between the mass eigenstates, both in the laboratory frame and in the comoving frame. Okay, here calculations become, the results are not possible analytically, but in some approximation we were able to show that, which is also reasonable for neutrinos because it is the time over m which is small, but we were able to show that the two terms, they agree. And so we find the consistency of the theory. Exactly the same day, we put this on the archive. Another paper by the group of Mazzas with Fulling, Cozzella, and Landolfo, Lanzella as well, did the same calculation using mass eigenstates. Well, they argue that this is necessary because of the consistency of the theory, and they motivate this as a necessity, among the other things, because of it's impossible to construct a Fock space for flavor neutrinos. This is one of their motivations. Anyway, let me summarize the sort of discussion which started after that. Well, for us, what is fundamental is flavor states. First of all, physical Fock space for flavor neutrinos can be defined, and we have done this many years ago. I will show very briefly. And on the other hand, using mass eigenstates in the vertex produce a violation of flavor charge. This can be shown. I will also briefly show. And then what is perhaps the most inconsistent feature of their treatment is the inability of reproduce flavor oscillations. They arise because of this interference term. In the moment they sum incoherently over the two different channels belonging to mass eigenstates, of course, they can never appear. So this is why the title of this seminar. We went on and we calculated the additional process which is present actually, and which is shown here. So in which the neutrino emitted can really oscillate as it does. And so this, together with the other one, actually consistently give the sum over flavors, give the sum over masses. So we are okay. Very briefly, I want to show what is the situation in the co-moving frame, in the co-accelerating frame. This is has to do with oscillations of neutrinos which are present in the thermal bath. So they have necessarily to oscillate. It means that flavor neutrinos are present there. Okay, this is why, let's say, we indicate the title. Finally, and this is, okay, becomes much more complicated, but if we extend the treatment that we have done in this other paper to 3 flavors, including CP violation, we find also a CP asymmetry in the radiation, which is particularly interesting, but we didn't explore more. We only found out this result. Okay, so to summarize, general covariance can be saved in not in the Valley approach, where they don't find the agreement between the decay rates, but both in the Mazzas group and in our approach. On the other hand, here the difference is evident because we give up KMS condition, and they give up, of course, neutrino oscillations and perhaps CP violation. Let me say now a few words about the mixing of neutrinos in quantum field theory and show how it's possible to create, to define, construct explicitly a Hilbert space for mixed neutrinos. So this, in the simple picture of neutrino oscillations in alla Pontecorvo, let's say, in quantum mechanics, we don't have any problem because this is just a rotation. We start from mass eigenstates, and the time evolution does the job, and we find the oscillation. But in the standard model, you see, we have a mixing for Dirac field. Let's consider Dirac can be done also from Majorana, of course. And this actually diagonalizes the mass term of the Hamiltonian, let's say. So in the moment that we plug in the expansions for these fields, first of all, you see, we can find exactly the generator for this object, for this rotation. And this is based on the anti-commutation relations for the fermion fields in E1 and E2. It's this object here. And once we plug in the annihilation and creation operator, we see very interesting feature here. We discovered with Giuseppe many years ago. I was his student. We discovered that this does not annihilate the vacuum for the mass eigenstates. So there is an orthogonality. There are inequivalent representations which arise here. So inequivalent Hilbert spaces, which arise essentially because the wave functions for particle and antiparticles with different masses, as anybody can check the Dirac spinors, they are not orthogonal. They are not orthogonal. So there is an overlap, and this overlap makes the Bogoliubov coefficients. So this can happen in quantum field theory, but not in quantum mechanics. But we are in quantum field theory. We know very well these things are permitted. And the vacuum is a very complicated object when you expand. It's classified as an SU2 coherent state, a la Perelomov. And there is a condensation density of the particles inside this. But I want to show, most interestingly, the structure of the annihilation operators for flavor fields. So this is what destroys or creates, if you dagger this, the flavor neutrino. It's a rotation in black, you see. And this is the Bogoliubov contribution, sorry, the rotation, the Pontecorvo contribution. But then there is a red part, which is nested, and this is a Bogoliubov. Okay. So when we try to disentangle this, we actually here we have two elements, algebraically speaking. One is a rotation, and this is Pontecorvo. And this other is the Bogoliubov, which is necessary, it arises from the structure of the fields. Now, what happens is that the generator, the one which generates the field mixing, is made of a combination of these, you see. And here you cannot commute this because they don't commute these two operators. Okay, so you have to keep in this form. The Bogoliubov, however, does not annihilate the vacuum. It's responsible for the vacuum structure, as well known. This is similar to BCS, for example, while the rotation is trivial on the vacuum. So if we want to have a take-home message, the thing is like that. Bogoliubov and Pontecorvo do not commute. And you see, if it was only for Pontecorvo, this would be only a simple rotation. But the Bogoliubov part makes this non-trivial. And the non-triviality arises just because of this commutator. So we have the usual vacuum plus a modification, which is induced by this term. At first order, it looks like this. Then the exact form, we have done all exact computations, of course. System is quadratic, you can solve everything. Okay, then I will skip this, but just to say that the relevant observables, because one can say, okay, that's formal, but what do we do with this? Well, we can define the states. First of all, from Nader's theorem, we define the charges associated to flavor, and these are time dependent, of course, because they oscillate. Once however, we want to find eigenstates of this. If we expand these fields here, these structures, these flavor Nader charges, we find that they are exactly diagonal in the operators we have found before. And so we can define our flavor states as eigenstates of this flavor charge. Notice here that these are created on the flavor vacuum, which is orthogonal to the vacuum for massive fields. So here it comes the violation of the flavor for any construction, any treatment which is based on the vacuum for massive fields. You can never construct a flavor state. You will violate the charge in any case at 3 level, which is in contrast with standard model. Okay, so oscillation formulas are modified and they get additional terms, oscillation terms, which, however, they are relevant only in the non-relativistic regime. But you know, neutrinos are quite relativistic, and in all applications. Although there is some hope that, especially for cosmic neutrino background, some access will be available to the non-relativistic region. Yeah, here is the violation of Ponte. So one can say, okay, Pontecorvo states are not good. No, they are good. They are good flavor states. They coincide with the flavor states in the relativistic limit. So they are perfectly well defined, the flavor eigenstates in the relativistic limit where we normally operate. And these states we have been using as input in our discussion before I have shown. So we didn't even dare to put the full flavor states because it's extremely complicated to deal with that structures. Although already we had to do some approximations. Now we derived many results from this on this line, and I want just to mention most recent things like the idea of generating dynamically fermion mixing because it is associated to a condensate. So following a bit the idea of an ambiguous Lasinio, and this we did with Peter Isba and Nick Mavromatos and with Luca Smaldone, and other developments which are also quite recent, but I cannot mention for reason of time. Now, let me go very briefly to the last part, which I think is fundamental for our discussion, and which will clarify why we can be not worried somehow, because we anticipated the fact that we do not fulfill KMS condition, which is related to thermality. Well, actually, this is actually the thesis of Gaetano Luciano, our chairman here. So what he did was the quantization of the fields of bosonic, then later also fermionic fields in Rindler space-time. Well, first of all, one, just to touch the points of this, one express the fields following this reference, which is was very useful, Takagi, express the fields in the hyperbolic basis in Minkowski. So this is Minkowskian, although we use already Rindler coordinates here. Then one can find a relation with the expansion in Rindler modes, and then, as well known, one gets the Bogolyubov. The Bogolyubov, which takes into account the effect of acceleration, which is in the metric, and this will produce the well-known result by Unruh, Fulling, and Davis. Also, they found similar results. Now, the point is, this is well known. We are repeating just a textbook and celebrated results. The point is, in the moment we know now that mixing also is associated to a Bogolyubov transformation. This was our question. How do these two Bogolyubov transformations, they combine? And the moment we quantize mixed field in accelerated frame. And I give you directly the answer without going. They combine in this way. It's quite complicated, but there is let's look directly at the observable condensation density of the particles. You have the usual Bose-Einstein distribution plus correction terms, which depend on the mixing. So there is the thermality is spoiled. This is even more evident in a very recent, we just put on the archive a few days ago, short paper that we wrote, and in which the modification of the Bose-Einstein distribution induced by mixing is related to Tzallis thermostatics. This is very interesting because with this Tzallis entropy, which is here described in terms of this deformed logarithm, you see, you generalize the Bose-Einstein distribution, which is recovered, of course, for Q equal 1. Now, if one expands this function for around Q equal 1, one gets an expansion of this kind. If we expand the spectrum of for the mixed particles, the one which we have shown, we find also there a similar expansion, which is quite striking. We get very, very similar function. And this allows us to identify the Q parameter, which tells us that we are in presence of a superadditive regime, in which because this is not extensive, in which the entropy of the sum of the system which is made, the two systems is bigger of the one of the sum of the two. And this is very interesting, very suggestive, because thank you very much. Okay, thank you. Because we had in mind a picture very, okay, perhaps we should not talk about event horizon as after Unruh's remark, but the idea that sort of thermal radiation is induced by the loss of information due to the particle-antiparticle couples popping up across the horizon. In our scheme is modified clearly, because we don't have only one kind of particle-antiparticle pairs, but we have also different one-to-one. And this can only increase the entropy if you think a bit. So this is very qualitative, but it agrees here is quantitative. I mean, we know how much this deviates from the Bose-Einstein. Of course, these are tiny deviations, But just to say how we already knew that there should be non-thermal, there should be a contribution. So we were not worried about this point, which instead was somehow a problem for the other authors I showed in the initial part. Okay, let me come to the conclusions. So the main message here is that mixing transformations, not only for fermions, also for bosons, but you know, for fermions they are fundamental in the standard model. They are not trivial. They are not trivial because they are associated to inequivalent representations. And the vacuum is a very complicated object for this, which, however, can be calculated because here we take only the quadratic part of the Lagrangian. And this allows us to define exactly flavor neutrino states. Of course, we have to give up something I cannot discuss here, and this something has to do with Poincare invariance. But yeah, this is a matter of another talk. And on the other hand, we have found that flavor states are necessary for the general covariance of the theory in the moment we consider Gedanken experiment like this about proton decay, accelerated proton decay. And the conclusion is that the Unruh radiation will contain this flavor of neutrinos which oscillate inevitably. As perspectives, we have several directions. Perhaps the most obvious, although very difficult, is to include full QFT flavor states in the calculation we have done, but I am afraid this is not so easy. And then also to look at Hawking radiation in terms of mixed fields. Particularly the issue of ZIP evaluation here I find very intriguing because, of course, this will introduce an asymmetry between particles and antiparticle. Okay, that's all. Thank you.
Thank you, Massimo, for your nice presentation. We have enough time for questions or comments or criticisms.
Yeah. Perhaps I interrupt. Yeah. Or maybe I should not have done because I.
Okay. Okay. So we have a question by Victor.
Oh, thanks a lot for the nice talk. I have a question regarding flavor entanglement. So what happens in these accelerated frames with the flavor entanglement?
We don't know. we have not considered it. Yeah, this is also a very interesting line which surely we can consider.
Okay, thanks.
Okay, we have another question by Dario Grasso. Please, Dario.
Yes. First of all, thank you for a very interesting talk. So you treated, I guess, the neutrino oscillation as a vacuum oscillation, right? Sure. But since you are in a thermal bath due to the acceleration, this, in a sense, should produce a sort of an effective potential for the neutrinos. So in a sense, neutrino oscillation should be treated as a neutrino oscillation in matter. In fact, matter oscillation can be treated in with thermal field theory. So I don't know if this can have any relevant effect, or it's, in a sense, is already included in your treatment or not.
I want to focus on the question because you are talking about the modification to the oscillation formula, which we use. I have shown in the second part of the talk. Or to the first part where we have the accelerated proton decay, because in both there are oscillations. And in the first part we don't have it's different because in the case of the, let's say, the quantum field theory formula, of course we consider the evolution of the flavor states, which is an excitation of the flavor vacuum. So you can regard this as a quasi-particle with respect to this vacuum, and this, in this sense, the vacuum is empty for that particle. So this is you see, there is no problem. In the other case, of course, but there is more difficult to talk about oscillations of these particles, which are sort of virtual. They are real in the moment they interact with the accelerated proton, with the proton which is in the Unruh detector, let's say. which is in the accelerated frame, but I don't know if one should consider temperature. There, temperature appears just as a multiplicative factor concerning the Fermi-Dirac distribution, so I don't think I should.
Okay, thank you.
I have to think about it. Yeah,
Okay, we have time for other question. Luca?
No, I wanted just to do a comment to the Victor question, actually. I don't know if Victor is...
Victor is here.
Okay, but we can do in the discussion if you...
Yeah, okay, we can say also. This is related to the question I was saying to you before.
Yeah, I thought about that.
Doing boost, we don't know what happens to neutrino entanglement. And so it would be very nice to study this point, because I think no one studied really. It is something about neutrino oscillation in gravitational gravitational fields. And in that case, there's a phase shift or something like that. It's just changing of phase.
But you have to use wave packets. I mean,
yeah, no, okay. But for work they did, there are a group of I think Kushbo Dixit and others in India that did this work in on gravitational fields, and what you have is modification of phase, but nothing very strong. I think in the case of accelerated frames, it's almost the same. Actually, by equivalence principle, I can say it's...
So I think we can also discuss afterwards, if there are no more.
Okay, I think that there is time for one more question. Luca, please.
No, I think it's I mean, just I don't know if it's a comment or a question, but the last slide where you show some perspective about the Hawking radiation, I think we'll be very interested in the computation also to discuss something about equivalence principle, because just to see how the basically the formula of the correction to the Hawking formula looks like, because if you get some
the same thing at the same thing at the end.
Sorry?
I thought that the very same thing at the end of the Massimo.
Yeah, because I mean, you discussed about like mixed neutrinos in the Unruh radiation and try to maintain general covariance, and you show that basically it happened.
That is exactly the reason why I put there that. So
yeah, it would be nice, because it may happen that you get some, I don't know, different correction, and then mixed fields can really induce some kind of violation. So it would be nice to see what happens.
Let's see.
Okay, thank you, Luca. Thank you, Massimo, again for your nice presentation. If there are no more questions, let's thank the speaker again. And okay, let's move to the last speaker of this session. Okay, so let's move to the last speaker of this session, who is Stephen Carlip, and he will talk about space-time form and the cosmological constant. Please, Stephen, you can start whenever you want.
Okay. Are my slides visible?
Yeah, perfect.
Yeah. Okay, good. After a year, I'm still not entirely confident with Zoom. So I'm going to talk about something completely different, although maybe the connection is that this is also an issue that Bill Unruh has thought about, which is to describe a really crazy idea for dealing with the cosmological constant, not by forcing lambda to be small, but by perhaps hiding the effects of a large cosmological constant. So to do this, I'm going to have to start with a little bit of ancient history. Back about the time I was born, so really ancient history, John Wheeler suggested that quantum fluctuations of the metric near the Planck scale should be of order 1. If that's true, and there are hand-waving arguments for this, it means that we would expect a very irregular, very highly curved, very geometrically and possibly topologically complicated space-time near the Planck scale. And Wheeler suggested that this is something that should be taken into account in understanding the infinities of quantum field theory, which would include what we now call the cosmological constant problem. Now, we have no idea whether this picture of space-time foam is right or not, but it's interesting to ask, if it is, what does this tell us? Does this Planck scale structure have any macroscopic implications? So let me assume that this picture of Wheeler's is right. And for simplicity, though it doesn't sound simpler, I'm going to assume that there are fluctuations in topology and not just in geometry. This just makes things a little bit easier to visualize. It's not really an essential part of the argument. So let's look at a typical spatial slice, space at some fixed time in any time coordinate you like. Mathematically, there is an old theorem that says that if you have a topologically complicated three-manifold, it has a nearly unique decomposition, unique if it's orientable, into elementary topological pieces called prime manifolds. These pieces are attached together by what mathematicians would call a connected sum, which to a physicist just means that they're attached by wormholes. What makes this interesting is a more recent result by Crucial, Eisenberg, and Pollack. I'll call this CIP in the future just to save syllables, who showed that this connected sum or wormhole decomposition also extends to geometric data. So let me explain for a second what I mean by that. Recall that the description of a three-manifold in general relativity that's sitting inside a space-time involves two basic ingredients. It involves an intrinsic metric and an extrinsic curvature, or equivalently, a metric and its time derivative, or a metric and its canonical momentum. But these aren't independent. They are related by a set of constraints. And good geometric data means a metric and an extrinsic curvature that obey these constraints. What CIP showed was that if you have two three-manifolds with good geometric data, you can join them in a connected sum, attach them through a wormhole, in such a way that the data changes only in an arbitrarily small area of the mouth of the wormhole. So this allows you to sew together elementary three manifolds to make something arbitrarily complicated. Now, there's one other point that I want to make about the constraints, which is obvious, but is going to be relevant, which is that there is a time reversal symmetry. That is that if you have a solution with a metric and an extrinsic curvature, then if you simply switch the sign of the extrinsic curvature, that's an equally good solution of the constraints. So now let's look at our time slice, space at a particular time. It's foamy. It's made up of this complicated connected sum of elementary pieces. These pieces are presumably created by quantum fluctuations. This is, of course, a sort of rough description of a deeper quantum process. But that's the way that we usually visualize this. Let's make one more assumption, which is that gravity, quantum gravity, doesn't have a preferred direction of time at the Planck scale. If that's true, then our spatial manifold, which is made from these elementary pieces, for any given piece, the geometric data of a metric and an extrinsic curvature, or the metric and minus the same extrinsic curvature, are equally likely. So if you just sew together two identical pieces, but with opposite extrinsic curvatures, then it's pretty obvious that any sensible definition of the average extrinsic curvature would give you 0. If instead you're gluing together some huge set of these elementary pieces, but with random signs of the extrinsic curvature, then I would argue that any reasonable definition of an average is still going to give you something close to 0. And remember that a cubic centimeter contains about a googol Planck volumes. So if these fluctuations are at the Planck scale, there are an awful lot of them. And there are an awful lot of varying signs that have the opportunity to cancel each other. So this gives us at least a huge class of, on the slide I call it initial data, but that you don't have to think of it that way. It's geometric data, just the data on a spatial slice, for which the average extrinsic curvature vanishes. So why does this matter? It matters because the extrinsic curvature is the way that we observe a cosmological constant. The trace of the extrinsic curvature is the expansion in the mathematical sense, but also in the physical sense. It's the logarithmic derivative of the volume. The trace-free part of the extrinsic curvature is the local shear. And so this gives you a set of data for which on this slice, the average expansion and shear are small, even with an arbitrarily large cosmological constant. So an obvious question is how typical this is. And the answer is that I don't think that anybody knows now. For a fixed topology, the particular construction of CIP is fairly special. On the other hand, presumably for an arbitrary manifold, you can always cut it up into smaller pieces that are joined by connected sums. So in a more general sense, this is a very general way of describing Planck scale fluctuations. For fluctuations in topology, this connected sum decomposition always exists. And in 3 dimensions, it's unique, except for non-orientable manifolds where there's one small non-unique factor. And physically, it seems at least plausible that a quantum theory of gravity is going to be time reversal invariant. And so fluctuations at the Planck scale should come with arbitrary signs. Now that's a pretty picture, but it is pretty far from the overall answer, because this was based on a slice at a fixed time, and we have to ask about the evolution. Naively, there are 2 expectations that you might have. One is that, well, expanding regions are expanding, contracting regions are contracting. So over time, you expect the expanding regions to get relatively bigger. The expansion is going to win. A second intuition, though, is that there's nothing special about the spatial slice that we chose. So if these fluctuations are produced by quantum fluctuations of gravity, then maybe we should expect them to reproduce in evolution, that if you have an expanding region, it should fill up itself with quantum fluctuations. I should also mention that if the cosmological constant is negative, as Unruh and Wang have emphasized, then you don't have to worry about expanding regions dominating, because these regions are going to expand and then contract. But then you have to worry about them passing through singularities. So if you try to actually do the classical analysis, the first thing you find is that the question is very hard to pose, because if you're talking about averages, even over small regions in a space-time in which there are expanding and contracting regions, then it seems very hard to find a physically preferred time slicing. And the averages can differ very highly depending on what time slicing you choose. So it's not clear how to formulate the question even in a good diffeomorphism invariant way. But the other thing that you learn classically is that you're not going to find a classical answer, that there's the usual problem with wormholes. Wormholes collapse. The connected sum construction that I've described here contains marginally outer trapped surfaces in the centers of the connecting wormholes. Those are basically black hole horizons, and standard singularity theorems tell you that classically you're going to quickly evolve to singularities. So that's telling us that this is fundamentally a question for quantum gravity. That's not surprising, since the starting point was this assumption about quantum fluctuations, but it's a little discouraging because we don't have a quantum theory of gravity. There is, however, an intermediate step that you can take, which is to look at MIDI superspaces. That is, situations in which you freeze out many of the metric degrees of freedom, but keep enough to make the situation interesting. And in that case, you can get simple enough models that you can seriously analyze the quantum theory. So what I've been working on most recently is locally spherically symmetric collections of metrics. Your first reaction may be that that's too much symmetry, that's too simple. That doesn't Birkhoff's theorem tell us that if you have spherical symmetry, then you necessarily have Schwarzschild or Schwarzschild de Sitter or some very small set of possible spacetimes? The answer is that it doesn't. There's a beautiful series of papers by Morrow, Jones, Witt, and Schleich who show that this local spherically symmetric system is much richer than you would expect. Birkhoff's theorem says that the spacetimes are locally isometric for positive cosmological constants, say to Schwarzschild de Sitter. But these local Schwarzschild de Sitter patches can come from any region of Schwarzschild de Sitter and can be sewn together in a way that gives you much more complicated geometries and topologies. So how do you make a foamy space-time that's that's retaining this spherical symmetry? The answer is that you design something like an onion. That is, that you have, for simplicity, I'm going to talk about a space with the topology of S2 cross S1, just because it's mathematically the simplest thing to deal with and is enough to give some idea of what's going on. So you make an S2 cross S1 by taking a solid ball, cutting out a ball in the center, and then identifying the inside and the outside boundaries. And of course, if your ball is embedded in a flat space, you can't identify the inside and outside isometrically. The outside boundary has a larger area. But if you don't try to embed things in a flat space, then there's no problem doing that. That gives you an S2 cross S1, but you can also divide the space into layers that each have their own geometry, that are connected by a connected sum, and still have a good set of solutions of the constraints. Specifically, you can write the spatial metric with this symmetry depending on two functions of psi, which I'll call h and f. And what Morrow, Jones, and Witt showed was a completely explicit way of generating solutions of the constraints. So classically, you can solve the constraints in closed form, given any function h and any function f. The constraints determine the extrinsic curvatures, but they only determine them up to sign. There's this sign ambiguity. And you can use their results to very explicitly construct spacetimes in which these layers can be expanding or contracting. They're glued together in a connected sum, and you get a completely explicit MIDI superspace version of this CIP construction. So that's classical, and that says that classically you can write down models of space-time foam with this very simple structure. But you can also quantize this. You can write down both a time-dependent Wheeler-DeWitt equation and then a stationary state version of the Wheeler-DeWitt equation. I've written it down just to show you that I can. For experts, a couple of technical notes. The time that I'm using is the dust time of Brown and Kukoc, in which time is measured as proper time along trajectories of freely falling test particles. I have solved the momentum constraint, I just didn't show that here. And because this is a Schrodinger type equation, it makes sense to treat the modulus squared of the wave function as a probability density. There aren't sign problems or anything like that. Although it's probable that there is a non-trivial measure coming from the fact that the inner product needs to be gauge fixed. And that part I don't claim to completely understand yet. Okay, so what can this tell us about space-time foam and maybe the cosmological constant? Well, we can look for WKB approximation solutions of the stationary state Wheeler-DeWitt equation. And first order can be solved exactly. Again, I've just written this to show that I can, but it really is an exact solution. The one factor in this solution that is important for the general picture is this term sigma. Sigma is a sign, it's plus or minus 1. And you can check by writing the extrinsic curvature as an operator acting on these wave functions, for instance, that sigma is just the sign of the extrinsic curvature. Now in WKB, we know that there's always an e to the plus is and an e to the minus is solution, that there's always an undetermined sign at first order. The difference here is that this sign can change, and very specifically, it can change exactly at the points that classically you would glue together expanding and contracting regions. So there is a wave function that describes this classical picture of an onion-like layer of expanding and contracting regions with a sign that reflects the expansion or contraction. And you can simply choose, just as classically, the constraints don't determine the sign of the extrinsic curvature. Quantum mechanically, they don't either. You can choose a wave function with any collection of signs. Now, this isn't quite the whole story yet either. We have stationary states, so it's tempting to say, okay, that's the answer, that this structure does reproduce itself in time. I'm teaching undergraduate quantum mechanics right now and just getting to WKB. And one of the things you learn from the WKB approximation in ordinary quantum mechanics is that you can have stationary states that represent bound states, and those really are time independent. But you can also have stationary states that represent scattering states, things like e to the ikx, which, although they're technically time independent, they show something that is dynamical. They show a dynamical process of scattering. In ordinary quantum mechanics, the way you distinguish those is by looking at the probability current. You can do the same thing here. There is a well-defined probability current. You can look at its moments. For de Sitter-like regions, it gives the ordinary expansion rate, with sigma being the sign telling you whether it's expansion or contraction. But for these onion-like configurations, you get a sum of terms with different signs, and typically the moments of the probability current are extremely small. So for a typical wave function, you also get a very low flow of probability in this superspace. You can go on and actually solve the next order WKB to an extremely good, well, actually exactly, up to an ambiguity in regularization, but you can use something like heat kernel regularization. Again, I've written the answer just to show you that I can, but you can read off the qualitative behavior. What you find is that regions that join layers, that join these separate layers, have relatively high probabilities, while regions of large expansion or high extrinsic curvature are suppressed. And there's also a large phase space volume for these many layered configurations in some sense. Every wave function has support on all of these metrics.
Steven, sorry,
but
5 minutes left.
Okay, good. That's almost exactly how much time I have left to talk anyway. So for these onion-like configurations, a typical wave function is going to have random signs for the various layers. And that means that that although there are special wave functions for which all of the signs are positive or all are negative, so you just get expansion or just get contraction, a typical wave function will have this combination. So these foamy metrics seem to be fairly highly probable, modulo this question of the measure and the inner product. And they seem to quite probably have a mixture of expanding and contracting regions. So where are we? We don't know whether this space-time foam of Wheeler's exists or not. That would take a full quantum theory of gravity. But in this MIDI superspace model, it does. And it appears with a high probability. The WKB approximation appears to prefer foamy multi-layered configurations. The wave function certainly allows them, giving stationary states with low probability currents. An extension to more complicated topologies and to a negative cosmological constant, for instance, both of those should be fairly easy. More complicated topologies are technically more difficult because it's harder to write down the coordinate identifications, but there's nothing in principle to stop that. And there are certainly many open questions. There's a question of what the proper inner product is. There's a question of finding more observables, seeing whether you can construct wave packets in this formalism. There's also another way of approaching this process of having you can think of this process as having contracting regions appear as bubbles in expanding regions and vice versa. And for that, there ought to be an instanton calculation to get the probabilities. So far, all I can say about that is that it seems that instantons that represent such transitions exist, but I haven't worked out the actions or the probabilities. Okay, so work in progress, but I think going in interesting directions, and I'll stop here.
Okay, thank you, Stephen, for your very interesting talk. Let me see if there is any question from the audience. Yes, Luca Smaldone, please. Luca, you can ask.
Hello, thank you for the talk, and I have just a couple of curiosities. First of all, what's the difference between this scheme of discretization respect to other approaches to quantum gravity? I would say like loop quantum gravity, where their discretization naturally come from the discrete eigenvalues of volume area operators and so on, or other approaches. And second, in fact, more about, you mentioned in the very last slide about the structure of your Hilbert space when you do quantum approach.
Okay, so for the first question, this isn't a discretization in the sense that the term is ordinarily used. This is a construction of a set of classical metric configurations that are exact smooth configurations that just have this structure that there are some regions that are expanding and there are some regions that are contracting. And in the mini superspace, it looks discrete because those regions come in layers, but there's no sharp division between the layers. The division is simply that the extrinsic curvature goes through zero at the points that they're connected. And everything's perfectly smooth. It's simply a way of constructing solutions, and every solution every classical metric configuration with these symmetries will have that form, just that some of them will only have one layer, some will have two. For the Hilbert space, the wave functions from this WKB approximation carried out to the next order are exact solutions of the constraints. And they are essentially the unique exact solutions of the constraints. Wave functions are labeled by this function sigma, which tells you a wave function is a function of the metric, which means it's a function of f and h. This sigma tells you for every possible metric what the sign of the extrinsic curvature is in each region of that metric. So there are an infinite number of wave functions labeled by sigma. My guess is that they are all orthogonal, but I am not sure of that, because in order to answer that, you need to really understand the inner product. The inner product is going to be some sort of a functional integral over h and f, but it has to be gauge fixed because these wave functions are solutions of the constraints, and the integral over h and f is going to include an integral over infinitely many copies of diffeomorphism equivalent wave functions. For the momentum constraint, I think that's pretty easy. For the Hamiltonian constraint, it's hard, and I don't have the answer yet.
So you mean the diffeomorphism invariant can manage to regularize such functional integrals, probably?
Yes.
Yeah, I see.
There's a beautiful paper by Richard Woodard from about maybe 20 years back called, I'm not going to get the title exactly right, but it's something like Solving the Wheeler-DeWitt Equation the Easy Way, but which is really about the need to gauge fix the inner product on solutions of the Wheeler-DeWitt equation.
Thank you very much.
Okay. We have time for one more question for Stephen. Otherwise, we can start the final discussion with all the speakers of this session, and in general with all the speakers of the three sessions of this day. For sure, we give priority as well as usual to the speaker of the last session. But if you have any question for any other of the speaker, please, you are welcome as well. There is no question from the audience. Guys, do you see any question from the audience or in chat? No.
Oh, just for completeness, I'd like to say that Luca added the work that Stephen was mentioning before in the chat. So if everyone's interested, the work by Luca.
Ah, yeah. I mean, it was for Luca Smaldone, let's say.
Yeah.
Luca is the one in the chat.
Yeah. I have seen. I'm scared to open everything, but
okay.
I don't want to move too much to.
In the meanwhile, just a curiosity for Stephen. Stephen, I'm sorry for the ingenious question. I'm not in the field, so please forgive me. Can we say something phenomenologically about your formalism, your consideration? And first question. Second question is, what happens if we change dimension in your formalism?
Let me answer the second question first, because that's the simple answer. I don't know. I haven't looked at that for 2+1 dimensions. There is a whole bunch of interesting work on sums over topologies that's mostly inconclusive. For higher dimensions, the connected sum decomposition isn't unique. I just don't know. Phenomenological, so the obvious question, one obvious question at least, is whether you can get an estimate of the size of the cosmological constant from this kind of argument. And again, the answer is that I don't know. There is an interesting idea of Sorkin's that might be adaptable to this case, although the details are different enough that I'm not confident. But Sorkin basically pointed out that if you simply count the number of Planck volumes in our past light cone, call that n, and you say that the cosmological constant or the expansion is random in each of those Planck volumes, then you expect that the cosmological constant on average should be order of 1/√n times, say, the Planck value. And that actually gives the right answer. That gives the cosmological constant we observe. Sorkin actually predicted this value before the observations of lambda. It doesn't tell you whether it should be positive or negative. It suggests that it would change over time. It doesn't quite fit this picture, but there still should be something like that where you can estimate the statistical fluctuations and see what value to expect. Beyond that, there's been some work on quantum field theory in a space-time foam background. Some of that goes back to old papers by Hawking, but I don't think that there is anything very solid phenomenologically at this point.
Okay, thank you. Let me see if we have any question. I don't see any question. Okay, well, in the meanwhile, if I can make a question to Massimo.
Yeah.
Yeah, my curiosity, my question is, you talked about this controversy, between mass and flavor states. Do you have any idea if we can say something, if some experiments can help us in discriminating between these two representations or not?
Yeah, okay, yeah, I was mentioning that the corrections, at least the ones we find to the oscillation formula, but also, for example, to the beta decay spectrum, these are relevant for low energy. So perhaps there is a possibility. I have been last year, the very last conference in February last year, when it was still possible to travel to a conference organized by people which are in this experiment catering, and they were quite interested to see what is the prediction of our model, because there is a difference with respect to the scheme in which you have the two mass eigenstate which enter in the tail of the beta decay spectrum. But we, as you know, I mean, we work together. We like also this issue of the consistency of the theory, testing fundamental or using fundamental principles to test the consistency of the theory and see how far we can stress this. I think this is very, very nice. I try to transmit this kind of feeling that we share.
Okay, thank you. We have a question by Luca Buoninfante.
Yeah, actually, just a quick comment on what you said. I think that, so if I understood well, this modified Ponte-Corvo formulas for the oscillation, the modification is relevant for non-relativistic neutrinos, right?
Yeah.
Okay. So I think that in the future, I don't know, with like if we really observe C nu B, like a cosmic neutrino.
Yeah, but there is in fact there were I was talking with people from Ptolemy, and which is this new experiment that they forecast. Okay, mainly you will have neutrinos which are completely decoherent, so you wouldn't see this. But perhaps there are other effects. For example, we are also looking at actually an interesting thing is that for non-relativistic neutrinos, also the chiral oscillations they come into play. And there is a nice interplay of chiral and flavor oscillation. This was studied a long time ago by Alex Bernardini. In fact, using Dirac equation, you find basically the same result we find using quantized kernel field. So they were deriving the formula we found, which has the two oscillation frequencies. But this is also obvious from a classical point of view. I mean, if you start with two frequencies, omega-1 and omega-2, you know, why you get only omega-1 minus omega-2 as in the oscillation formula by Ponte-Corvo. I mean, you have also the other frequency, but this is typically suppressed because it gets a coefficient which is going to zero for high energies. And this is the same which happens with chiral oscillations. And it's, they have never been considered because you should go to a region which is not accessible for the moment.
Mm-hmm. Yeah, actually, since Gaetano mentioned this flavor.
With Victor is not perhaps anymore. Unfortunately, it's a bit late, so people are dropping.
No, yeah, just one. I mean, since you mentioned this, I'm not an expert on neutrino, so but since you mentioned this flavor mass day neutrino, so just a provocative question. So let's suppose that one day we manage to see really that the flavor construction that you proposed does not work. Okay. In that case, what would that mean? I mean, like which starting assumption?
Okay, but
no, there would be, I mean, some starting assumption which would fail.
If you for construction, by construction, the standard model conserves at 3 levels, conserves strictly the flavor charge in the vertices. This is by construction, it's not me. But, so it means that there you have something to change, I mean, somehow.
So you would have some violation of this.
I'm not talking about loop correction, which are present and which are extremely suppressed in presence of neutrinos with mass, but just the 3 level. In fact, this is quite obvious from some point of view. On the other hand, if you want to conserve flavor, you have to pay a price with respect to Lorentz invariance, because the point is that the flavor charge and the Hamiltonian, the energy momentum tensor, they don't commute. There is nothing to do. So one of the two, you can choose only one eigenstate. You see, you cannot have common eigenstates. You can have common eigenstates of the commuting observables. That's all. They are exclusive. And this is why with Luca we were doing this flavor energy uncertainty relations, speculating that the neutrino. I mean, it's also interesting the concept of a particle which is not stable, or an asymptotic particle which is not stable. This is also quite intriguing because we build all the theory with asymptotic particles which are stable states, representations of the Poincare group, etc., etc. But what about an extension? I mean, one should enlarge the group to accommodate this, or should use other ideas as we also were proposing. I mean, it's all open. It's a possibility. At the moment, we cannot, I think, swear on any of the two. I wouldn't be.
Okay.
Any other question? Okay, please.
To what Massimo was saying. the point is exactly this uncertainty relation, you know, that you have to make choice. I mean, how the key question is, how can you manage to measure neutrino mass? I mean, neutrino always interacts as a flavor in terms of flavor eigenstate. And so when someone before said, probably Unruh said that a particle is what you measure with the detector. I mean, when you measure with the detector neutrinos, what you measure are substantially the charged lepton associated, and so you can detect the flavor of the neutrino. The only way I see to measure neutrino mass is through gravitational interaction, and you can understand this. I think it's very complicated to measure gravitational interaction of any fundamental particle, but for neutrinos in particular. So I will say, in that case, you should not have a definite flavor. It's a matter of choice, but in all experiments we can do where measurements of flavor are involved, the only relevant object must be flavor neutrino states. I think this is unavoidable from an experimental point of view for a moment.
Okay, thank you both, Luca. Let me check if there is any other question. I don't see any question. Maybe I have a question and a kind of Luciano, okay.
Okay, you can go first.
No, don't worry, please.
No, never mind. Really.
Okay, my question was for Bill Unruh. I don't know, Bill, are you still there?
Yes, I'm still here.
Okay. Yes, a question and a kind of provocation. The question is, well, if you can, explain a bit more in detail the status of experiments about your effect, and the provocation. Let me say, kind of provocation is, there are many group of research which basically states that the Unruh effect does not exist, is not real, is just an artifact of quantum field theory. And so my question is, what is your feedback or your feeling about this position?
Well, let me answer the second one first, and I'll try and get back to the first one. So this effect is not something extra. It's not something on top of, quantum field theory or on top of quantum electrodynamics and so forth. And as we all know, one can often look at the same thing from many different points of view, and those different points of view can make them look very different from each other. We've learned that lesson in spades with special relativity, for example, with all the so-called paradoxes and so forth. So the fact, as I said, Jackson, etc., had done the experiment, had done the calculation, in quantum electrodynamics for an accelerated charge, or in particular an accelerated charge in a circular beam. So from that point of view, there are many ways of looking at it, which all come to the same answer. If you take seriously the fact that these things acting as a detector actually are what you're going to use to define the particle, then you could go back to Jackson's kind of calculations as well and see that there is some sort of spectrum, and it looks like a thermal spectrum, a frequency dependent, but a thermal spectrum that these particles see. The experimental situation, the nice thing about the Bell and Linnaeus work was it suggested that maybe you could measure it in these synchrotron accelerators. One of the problems with thermal waiting for something to come into thermal equilibrium, the magnetic dipole moment coupling is very, very weak. So it takes a long time for it to come into thermal equilibrium. If one had to do this with linear acceleration, you would need a linear accelerator that was longer than the diameter of the solar system, which I doubt that they're going to fund anytime soon. Circular ones, however, you can hold stuff in storage rings for hours, and so it can come to equilibrium. The problem, of course, in a storage ring is that there are all kinds of other possible perturbations of, you know, things that perturb the magnetic field in the storage ring, which could also induce transitions. So it becomes rather difficult to actually measure in details, plus the problem that you only measure anything at exactly one frequency. So there's only one value that you can extract from this, which can make things somewhat ambiguous. Our experiment is still in the proposal stage. There are some suggestions that in the next, you know, within this year, we'll try building detectors that will actually test some of the ideas, whether or not we can get the kind of accuracy, let's say, in a Bose-Einstein condensate. This procedure could work on many other kinds of systems. For example, there's another proposal of using surface waves on liquid helium, and looking, you know, that also produces refractive index changes. The problem there is that you can't play this trick of the, you know, being above and below a resonance, because the resonances in helium are up in the ultraviolet, and finding lasers that you can use and mix in the far ultraviolet is rather difficult. But there are some proposals for using that kind of a system as well for looking at the effect. So there are a number of, and there is money available to do that. And there's a group in Nottingham with Silke Weinfurtner that is actively pursuing that to try and see whether or not they can see some of these effects on liquid helium. Whether that will be good enough to be able to see the analog of the acceleration radiation is still unclear.
Thank you so much.
By the way, those some of the arguments that the thermal effect, etc., doesn't exist. Steve Fulling and I wrote a paper about 10 years ago where we pointed out some of the problems in those arguments that you might want to have a look at. I couldn't give you the exact reference right now, but it's about the only paper I've written in the last 20 years with Steve. So.
Okay, thank you. So, Luciano, do you want to make your question?
Oh, all right. Yeah, it was just one kind of open question for Bill as well. Well, hopefully, first of all, I hope that in the next few years we will be able to have some positive replies from all the promising experiments that have been acting in these years to detect the effect. But my question was more theoretical in a sense, because okay, we know, I've known for many years the effect, so your effect, the Hawking radiation, and so on and so forth. So I would like to ask you if, in general, there is some sort of idea how to go from quantum field theory in curved space-time to quantum gravity from a bottom-up approach, in a sense, because typically when we hear of string theory or quantum gravity, I tend to look at it mostly from a top-down, in the sense that there's the theory that then should recover quantum field theory in curved space-time in a certain limit, in a sense. But if we want to start with quantum field theory in curved space-time and we want to go up, so it depends, this up, because it can be up in the energy and down at the scales, in a sense. But in a sense, how should we move on if we want to stick to a bottom-up approach? starting from what we know from quantum theory from space-time? I know it's quite a vague question, but
right. I don't have a good answer for that. I mean, most of the sort of really real quantum gravity effects are, as always, going to be so small that it becomes really hard to get a handle on it. And, you know, how to answer that question becomes hard. I mean, one of the things that you could look for example, is theoretically is the effect of this radiation on the horizon, you know, location of the horizon, and on the argument that Hawking basically gave for producing the thermal radiation as some sort of clue as to what kind of things could happen near the horizon. The problem is all of these theoretical approaches are almost certainly going to be highly perturbative kind of approaches, where one is not sure at all what one is neglecting in the approximation scheme that one is using. So one is going to be very unsure about the results that one gets from any kind of such a scheme, whether it's really true or whether one has just simply overlooked absolutely crucial effects that one should have taken into account in doing the calculation. Experiments would be extremely helpful for this. And that's one of the reasons why the analog program, in a sense, is interesting, because there the quantum effects of the background, you know, the fluid flow and so forth, are approachable. I mean, we do see quantum effects in laboratory systems, you know, even in bulk laboratory systems. And so one can ask questions about, you know, what is the back reaction of the quantum system on the background flow, etc. Now, that doesn't directly answer quantum gravity, because these systems do not look like gravity at all once one looks at the background equations, etc. But it sort of gives one, it may at least give one a clue as to how robust they are. Namely, if you discover that the effect is still there, and this is one of the reasons why I got into the analog system, was to ask the question, you know, one has these thermal effects on the sort of semi-classical base level. Are they actually there when one gets into a more quantum regime? And, you know, if one discovers in these kinds of systems, both either experimentally or theoretically, that the effect is robust against the sort of quantization of the background as well, then that gives one a lot more hope, at least, that the same will be true in the gravitational case. So that's sort of the best answer that I can come up with for the first part of your question.
Thank you.
Okay, we have another question by Alessia.
Okay, so can you hear me? Yes.
Yeah, perfect.
For William, this already somewhat related to just said. So I have to say the analog models, and I interesting, but at the same time completely clear to me. The reason is that there are some systems that behave similarly, our manifestation of causality of some physical phenomena, but the holds in which regimes, because it is regimes the analog sources, but let's say if one then finds a negative result, might not necessarily imply that the analogy fails. How do I know this a priori? So can you comment on that?
Right. I had real trouble because your voice kept breaking up. I don't know if that happened to everybody else as well.
Yes,
so
yes. Your
I
voice.
can only get a feeling. It's certainly true that the analog systems are simply analogies. And there are places where that analogy, the relationship between the analog and the system one really wants to understand, namely the quantum gravity system, becomes bad. And if one finds experimentally that you're getting a result that's in disagreement with your prejudices, that may be because your prejudices are wrong, which is, of course, the interesting case, and that will actually teach us something about gravity, or it could just be that the analogy has failed and it's telling you absolutely nothing about your prejudices about the other system, and giving you no clues for the other system. I don't know what to say about that. One could argue that if it keeps failing for all kinds of analogs, then you would expect the analogs, different analogs, to at least sort of cover interesting, slightly different aspects of the central thing that you're trying to understand. And if it keeps failing, then you start believing that maybe your prejudices were wrong in the first place, and you learn something about the gravity system. But yeah, this is always a problem with the analog system. So in a sense, they're stronger in the proof or in giving one faith than they are at destroying one's faith. And that's a problem with them.
Okay. So essentially, it's not possible failing or failing.
Yeah, I lost over half of that in the breakup of the sound. But the few words there.
Maybe if you can type your question in the chat.
1 second.
Okay, thank you. Okay, so my question is, if one gets a negative, let me just read the question for all the speaker. Sorry, Bill. If one gets a negative result, how do I know if it is the theory failing or the analogy of the two systems that does not hold in that regime?
Yeah, I mean, as I said, that's a problem. I agree. If you have loads of different analogies, especially very different analogies, where the analog system is very different from each other, then you might say that, okay, the analogies are going to overlap with the real system in different ways, and therefore sort of probing how the real system behaves in different ways. And if they all keep failing, then you start worrying about the original, the system that you're actually interested in. Any individual failing, on the other hand, as you say, could be a problem with the analogy. And then you would like to look, I guess what you would like to do is to really look at the analog system see where that analogy could be failing. Does it make sense that the analogy is failing in precisely this regime? Or is it really reflecting some of the common features between the system that you want to look at and the analog? I mean, ultimately, the analog is not the original system. So, you know, you can learn as much as you want about the analog, and it ultimately is not the original system, and the original system could certainly surprise you, which would be great. On the other hand, in cases where you have zero experiments on the original system, having some way of at least experimentally getting a handle on stuff would be great. For example, you know, theoretically in the analogs, it makes it clear that what's happening, you know, in Hawking radiation is not a high frequency effect. It really is a low frequency effect. The high frequencies become adiabatic, and so it doesn't tend to matter what happens at high frequencies. And it's what's going on there is a low frequency effect where you really expect the analogy to work very well. And if it failed there, then you would feel that you're in real trouble.
Thank you.
Okay, thank you. Maybe we have another question by the brave Luca.
Actually, it's not a question, it's just maybe kind of like, it's a question to maybe, it's a comment to Unruh, to Bill Unruh, and also to Barbara Soto, because I don't know if Bill Unruh was following the previous session, and there was this new proposal by Barbara, where she was proposing basically a new way to test the Unruh effect, but with a very small acceleration. So she spoke about this acceleration-induced transparency effect. So I don't know, Unruh, if you, both you and Barbara can comment, maybe you, Unruh, if you can comment on it. What is your opinion, for instance?
Yeah, I don't know it, so I can't answer.
Okay. Maybe Barbara, you want to say something?
I would tend to doubt it, but
I can summarize it. So, we stimulate the Unruh effect by the presence of photons in the field, and we get, at the same time, we get rid of the resonant terms in interaction with the new effect, acceleration-induced transparency. So we can increase the probability of transitions by a very large number, the number of photons in the field, and it will be clean because we get rid of you know, absorption and emission, and we're only left with strong Unruh effect, whatever you want to call it. So yeah.
I mean, is that? I mean, the thing that comes to mind is stimulated emission, that you're doing a stimulated emission experiment rather than a spontaneous emission or spontaneous absorption.
Yeah, so we have, you know, that's a point. We increase the probability of transition due to non-resonant terms, which are responsible for the Unruh effect. We increase them by having the photons present in the field. At the same time, we get rid of the resonant terms, you know, the sigma plus A, sigma minus A dagger. We get rid of them using acceleration-induced transparency. And this is work with Achim, so maybe Achim wants to comment something as well.
If he's still there.
There
he is.
Can you? Okay. Now you can.
Right? You're unmuted. You can talk. Again.
Oh, right. Yes, I tried to unmute me, but I wasn't allowed to. Right. Yeah. So, Bill, yeah, it's exactly as Barbara said. So the overall idea is that there's the following observation. It's a pity that you missed her talk, but she explained it super well. The overall observation. There are two overall very important observations here, namely that the resonant terms, the resonant terms, that is to say the rotating wave terms, are very much affected by acceleration. And you can use this in order to, in fact, suppress absorption and emission if you so choose. You can choose trajectory such that resonant emission or absorption is inhibited. And that's what Barbara discovered, and it's what we call the acceleration-induced transparency. And then, in addition, we have that the counter-rotating terms, that is to say, the non-rotating terms that are responsible for your effect, for the Unruh effect, the non-rotating, the counter-rotating terms, the non-resonant terms, can be stimulated, right? Now, ordinarily, when we stimulate the Unruh effect, or the Hawking effect for that matter, if we stimulate the Unruh effect, then we would expect that this is not so useful because at the same time we are also stimulating ordinary emission and absorption, which would mask the Unruh effect. But this is where Barbara's acceleration-induced transparency comes in, because what she showed is that you can at the same time amplify the Unruh effect through stimulation and at the same time suppress the resonant effects by choosing your acceleration very carefully so that you have actually this transparency, so that, as I said, the acceleration will inhibit the ordinary resonant effects. And so the hope is that if experimentalists are having a good control over the trajectory, then you can combine the stimulation with the acceleration-induced transparency, and the whole thing might be, your effect might be more visible and easier to measure.
Right. So if you could send me at least a link to the paper.
Oh, for sure. Yeah. Barbara, can you please send it?
Yep.
Maybe just put it in the chat.
Just email it to me is better than a chat, which disappears immediately anyways. So.
Right. Yeah. Yeah, so the paper is on the archive, but it's not yet published. It's with the journal.
Okay, good.
Okay, thank you. We have another question by Gaetano Fiore. Please, Gaetano, you can ask.
Thank you. Achim, it's again a question for you. What is, what is the remnant, so to say, of causality in your approach? Is it clearly visible somehow? The fact that the analog of the fact that field operators pertaining to space-like separated region compute with each other. What is the trace, the remnant of this, if any?
Yes, so this is now encoded in the low energy regime. It's encoded in the fact that the higher point correlators are local in space-time. So you have that all interactions are strictly local, and therefore you don't have violations of microcausality. Whereas in the case of the high energies, when you go all the way to the Planckian regime, the endpoint correlators may not be diagonalizable. The vertices may not be in any basis, in any system, just products of Dirac deltas. And then in principle, if this was happening in a theory of a space-time with fields on it, then if the vertices are non-local, then that would have to be interpreted as a violation of microcausality. But in the framework that I was talking about, we do not have, in this case, fields living on a background space-time and therefore violations of microcausality. But instead, what we would have is still endpoint correlators, abstract endpoint correlators, which simply cannot be represented as matter fields living on a space-time. And therefore, we just can't ask the question whether microcausality is fulfilled or violated, because we don't have the notion of locality accurately enough to specify that question. Instead, what we then can only ask is, are the endpoint correlators consistent with each other? right? Because the notion of a space-time stage and the matter actors, they have just melded together in just a bunch of correlators and the information that they define.
Yeah, but I would expect that something remains, a remnant, at least
Yes,
something like causal effects, so that.
Yes, I agree with you. And it would be super interesting to find out what that remnant is, because it would be encoded in the structure of these endpoint correlators, right? I guess what you're saying is that we should be able to read off from the structure of the endpoint correlators, even in that Planckian regime where everything else fails, we should still have some remnant of microcausality there. I can't tell you what it is, but it would be super interesting, and it's an information theoretic question once you formulate it for the endpoint correlators.
Okay, thanks.
Thank you, Gaetano. There is another question by Luca. Smaldone.
Yes. Okay. Now I wanted to do a comment slash question to Achim about his talk. Actually, I will say that spiritually or philosophically, I agree with you about unification, unifying view of geometry and matter. I mean, of gravity and matter in a sense. And because here in Prague, we are actually working in same directions in some time, but we arrived there from different, slightly different kind of reasoning. No, you started from, at least as you presented, from the problem of roads and clocks compared to space and time, and we started actually here from Bekenstein bound, or you can do the same thing actually from holographic bound. It is a work of some years ago by Carroll, Bow, and Singh, for example, which argued that structure of the Hilbert space, when you include gravity, of any local system, so should be finite dimensional. And this is should be a consequence of Bekenstein bound, exactly. But in fact, it's known that if you want to get Bekenstein bound, there is a paper of Orazio Cassini, for example. In quantum field theory, you have to use some cutoffs and tricks and so on. And the most natural thing is if you start with system which is genuinely finite dimensional Hilbert space. And another consideration is that bound is saturated for substantially only for black holes. And in that case, the idea that we had here is that you are really counting all degrees of freedom. You have to count all degrees of freedom, both, I would say, matter degrees of freedom and geometry degrees of freedom when you compute the entropy. And so only in the case of black holes, all this kind of degrees of freedom should be all excited and should be counted at the same level without any distinction, I would say. That's the point. And this led us to an idea we call such fundamental degrees of freedom, which do not distinguish between matter and space-time at fundamental level. We call them exons. And you can listen to talk about this. Is the last talk of this conference by Giovanni Acquaviva. So I recommend you. And so about this, I wanted. This was a consideration. The comment about this, I wanted to ask you.
You're not the speaker of this session, so try to be more.
Sure. No, I wanted to ask a question now about this. Can you address such kind of question with this with your approach computing? I know black hole entropy, or trying to look at Bekenstein bound, because I think that we came from the opposite direction, but you can come there from your direction let's say?
A very good question. First of all, please send me references and the link. No, actually, no, I have the link, of course, to your talk. Yeah, please send me the references that you were mentioning.
Yes, I can send you an email.
Yeah, thank you. The question is a good one, and I'm afraid I don't have a good answer, though. So far, my approach is not developed enough that I could consider black holes and their entropies and so on. I just can't do that at the moment. In that sense, it's great that you do what you do because you are doing it from another perspective. And yes, at some point, hopefully we meet somewhere, right? That would be great. But at the moment, I can't do what you do. So yeah, I don't know how to do that.
And just another maybe stupid consideration, because I have no control of your approach in particular. But just a curiosity, in your approach, it seems to me your fundamental objects are the two-point correlators, actually.
Well, endpoint correlators, two and n.
Or n function in general. But you started looking at 2 points, and then but then you try to define some path integral to quantize everything there. But an approach which integrates over a green function exists is the one which is used for compute effective action of bounded system, for example. Why not trying to path integrate directly on correlation function? I would say, like you do, for example, when you treat bosonization.
So what exactly was the question here?
No, I mean, why do you construct path integral in that way? For example, I was thinking during your talk that natural way of defining quantum version is to integrate direct path integrate on correlation function directly, as you do when you treat bosonization, for example. Is the Jacques or other effective action approach?
Right. So in my approach, where you're right, I'm considering the correlators to be the fundamental quantities, and yeah, I mean they carry the information about the matter, about the space-time, and they are information theoretic in nature. And then the question arises: where do they come from? How do we describe their structure? And my argument there was this. Any correlator is a sum over possible configurations multiplied with their probabilities, with their weight functions. And this, just by its nature, has the form of a path integral. And the weight function can be identified in the low energy regime that we are familiar with e to the power I times the action. So that's how it arises naturally in this case.
I see. Thank you.
Okay, I think that there are no more questions. Can you confirm these, guys?
I don't see any.
No, I don't see anything.
Okay, so I would say that's the right time to stop here. This very nice discussion session. Let me thank again all the speakers of this session, but also for the previous session. And let me thank also the survived participants for their involvement, their question, and their role. So, well, I think that we can stop here. Let's see. I hope to see you again tomorrow at 12 a.m. in Central European Summer Time. And, well, do you have any...
Tomorrow and the following days, I would say.
Sure. Let's start by tomorrow then. Okay, so guys, do you have anything else to add? No?
I guess not.
You don't have, I stopped the YouTube live.
Okay. I guess you can.
Okay. Thank you again and see you again tomorrow.
See you tomorrow.
Have a nice day or nice night or afternoon.
Bye, everybody.